Hello guys, welcome back to my channel. Today we are going to explore flash attention. Now we are going to explore flash attention from first principle, which means that not only we will code flash attention, we will actually derive it. So we pretend that the flash attention paper never existed, and we look at the attention computation and we look at the problem it has and we try to solve it step by step, pretending that the flash attention never existed. This will give us a deep understanding of how it works, and also we will combine theory with practice because we will code it. Now, in order to code flash attention, we will need to write a kernel for our GPU, and in our specific case I will be using an NVIDIA GPU, so a CUDA kernel. But instead of writing C++ code, we will use Triton, which is a way of converting Python directly into CUDA kernels that can run directly on the GPU. And Triton, you can think of it as a compiler that takes in Python and converts it into something that can run on the GPU. So let's look at the topics for today. First of all, I will give an introduction to multi-head attention because we need to look at what is attention and how it's computed and what are the problems in computing this attention. Then we will look at actually the most critical part of the attention computation is this Softmax and how it impacts the computation and complexity. We will look at what is the online Softmax. Then we will explore what is the GPU, because we are going to write a kernel that will run on the GPU. So we need to understand what is the difference, for example, the CPU and the GPU, and what is a kernel and how it differs from a normal program that you write for the CPU. We will look at how tensors are laid out in memory, so row major layout, column major layout, or etc. Strides. We are going to look at block matrix multiplication, Triton, software pipeline, all the optimization that Triton does to our code. Finally, we will be able to code the flash attention forward pass. But of course, we are not satisfied only by coding the forward pass. We also want to code the backward pass. But in order to code the backward pass, we also need to understand how Autograd works and the gradient descent works in the case of custom operations. So we need to understand what are derivatives, what are gradients, what are Jacobians, and then we calculate the gradient of the common operations that we use in flash attention. And finally, we will have enough knowledge to code the backward pass. For this reason, this video is going to be super long, but I hope you don't mind because we are going to learn a lot. Of course, you may be wondering, all of this requires a lot of knowledge that you may not have, but that's not a problem, because that's my problem, because in this video, I will make sure that if you only have high school calculus, so you know what are derivatives, you have basics of linear algebra, like you know what is matrix multiplication, or what is the transpose of a matrix, and you have a basic knowledge of attention mechanism, so like, for example, you have watched my previous video on the attention is all you need paper, and you have a lot of patience. That should be enough to understand all of this video, because all the topics that I will introduce, I will always introduce them in such a way that I pretend that you don't know anything about that topic. So we try to derive everything from first principle, everything from scratch. Okay, now that we have seen the introduction, let's go see the first part of the video, which is the multi-head attention. Alright, let's talk about multi-head attention. Now, I am using the slides from my previous video, attention is all you need, so we can look at very fast at what multi-head attention is and how it works. I hope you remember the formula softmax of the query multiplied by the transpose of the key divided by dk all multiplied by v, because we will be using that a lot throughout the video. Now, multi-head attention starts from an input sequence or two input sequence in case we are talking about cross attention. In the simple case of self-attention, we have one input sequence, which is a sequence of, in the case of language model, a sequence of tokens, where we have a sec number of tokens, and each token is represented by an embedding, so a vector with d-model dimensions. The first thing that we do is we convert this input sequence into query key and values through three linear projections, one called WQ, one called WK, one called WV, which in PyTorch are represented through linear layers. And these linear layers are of d model by d model, so they do not change the shape of the input tensor. And after we do this job of projecting them, they become three different sequences, one called query, one called key, and one called value. So here I'm calling them Q prime, K prime, and V prime. Then we divide them into smaller embeddings. So each of this token, which is made up of d model dimensions, we divide it into smaller tokens. Each one, suppose we have 4 heads, each one will have d model divided by 4 dimensions. So this one is a sequence of tokens where each token is not the entire token but a part of the embedding of each token, and this one is another part of the embedding of the tokens, and this one is another part of the embedding of the token, etc. And we do this job for the query, key, and value sequence. Then we compute the attention as follows. So the softmax of the query multiplied by the transpose of the key divided by the square root of dk, where dk is the dimension of each head, so how many dimensions each head is working with. And then we do the multiplication with the v, and this will give us the output of the attention mechanism for each head, and this job is done independently for each head. This should be clear to you. If it's not, please watch my previous video on the attention mechanism, because we will be working with this scenario a lot. Now, then we take this O, the output of each head, and then we concatenate it back in order to get the representation of each token as a full embedding. So before we split this embedding into smaller embeddings, this one here is called the Q1, Q2, Q3, Q4. Then after we compute the attention, we get back the output of each head and we concatenate it together to get back the full embedding dimension, which is this H here. We run it through another linear projection called WO, which will be the output of the multi-head attention. Now, flash attention is not concerned with all of these operations actually. Flash attention is only concerned with the operations that require optimization, and the operations that require optimizations are this one. So the softmax of the query multiplied by the transpose of the key divided by the square root of dk multiplied by v, which means that the projection of the input sequence through WQ, WK, and WV is not something that flash attention is concerned about, because that's a matrix multiplication. So when you use a linear layer, it's just a matrix multiplication of the input with the weight matrix of the linear layer. And this kind of operation, so the matrix multiplication, is one of the most optimized operation that we have in the GPU, because the manufacturer of the GPU usually also releases the necessary library for computing the matrix multiplication. So actually these are quite fast and they do not require any optimization. So flash attention will pretend that the query has already been passed through by WQ, and the key has already passed through WK, and the V has already passed from WV. Moreover, flash attention will not be concerned with the projection with the WO, because that's also a matrix multiplication, because the WO is always represented in PyTorch as a linear layer, so it's a matrix multiplication. And matrix multiplication, as we have seen, are very optimized, so there is nothing to optimize there. But what we need to optimize in terms of speed is this operation here. Softmax of the query multiplied by the transpose of the keys divided by the square root of dk multiplied by v. Alright guys, so now we have rehearsed what is multi-head attention. I also want to give you a lot of visualization, which is basically here in the paper of the multi-head attention, we can see that we have the input that is v, k, and q, so q, k, and v. Each of them runs through a linear layer, which is the WQ, WK, and WV. Then we do the scaled dot product attention, which is done independently for each head. So each head will do query multiplied by the transpose of the key divided by the square root of dk, where each query and each key is not the full embedding of each token, but a part of the embedding of the token, because we split them into smaller embeddings. And eventually we take all the output of each of these heads, which are computed in parallel. So that's why you see this dimension h in the depth. We concatenate them and then we run them through WO. What are we concerned with? We are concerned with optimizing this particular block here, the scaled dot product attention. So let's start our journey. One thing that is very important to understand is why do we even need a better implementation of the attention mechanism. And if you look at the flash attention paper, you will notice the following part. This is the paper flash attention 1, and in the flash attention 1 paper, they describe the attention implementation as it's done naively when using PyTorch. So first we do the multiplication of the query multiplied by the transpose of the keys. Then we apply the softmax to the output of this operation, and finally we multiply the output of the softmax with the V matrix to obtain the output of the attention. The way this implementation is done by PyTorch without any optimization is as follows. So we load the, first of all, this tensors are residing in the GPU. The GPU is made up of two main memories. One is called the HBM, which is the DRAM, which is the RAM of the GPU, which is the 40 gigabyte of the A100, for example. So it's the biggest memory that we have in the GPU. And then there is the shared memory. So the problem of the GPU is that accessing this HBM, so the global, it's also called the global memory, it's very, very slow compared to the shared memory. However, the shared memory, it's much, much smaller compared to the HBM. And what they claim in the flash attention paper is that the operation of the attention is I/O bound, meaning that if we keep accessing the global memory, the overall operation of computing the attention is not because computing all these operations is slow, but because we keep accessing the global memory, which is slow. So we call this kind of operations I/O bound. So the only way to improve this situation is to compute the attention inside the shared memory of the GPU, which is much smaller, which is much closer to the cores that actually do the computation. So we will need to kind of also split the attention computation into smaller blocks that can reside in the shared memory. And we will see later in how this is possible through block matrix multiplication. And this is in the paper here, they call it the tiling, and it's a very how to say, use the technique when doing when writing kernels for the GPU, which are usually involve some kind of matrix multiplication. So now we know what problem the flash attention is trying to solve. It's trying to make sure that we do not need to access the HBM, so the high bandwidth memory, when computing the attention, but copying only a part of each matrix inside the local memory, so the shared memory of the GPU that is closer to the cores, and computing a part of the output matrix there, then copying that part to the output that is residing in the HBM, and keep doing it for all the blocks in which we can divide these query, key, and value matrices. And later we will see how this blocked computation is done, but also we will see that the biggest problem in computing this blocked computation is the softmax, because the softmax needs to access all the row of the S matrix to apply the softmax, because the softmax needs to have a normalization factor, which is the sum of all the exponentials of all the values to which it is applied row-wise. And we will see later how we will solve this problem. So let's move on. All right, guys. Okay, when I say guys, I mean guys and girls, because I don't know, usually I just say guys to, but please, girls, don't feel excluded. So we saw that first of all, flash attention is only concerned in optimizing this softmax of the transpose of softmax of the query multiplied by 3 divided by the square root of dk multiplied by v. And we need to introduce a little bit of notation so that we don't get lost in the future slides. First of all, this is the formulas I took from the flash attention paper, but for now let's pretend flash attention never existed. So we are trying to solve the problem step by step. Now, we should treat this queue as something that has, as the sequence that is the output of the input sequence that has already passed through WQ, the K as something that has already passed through WK, and V as something that has already passed through WV, because we don't want to optimize the matrix multiplication because it's already fast enough. Another thing is, let's talk about what are the dimensions of these matrices, so we can then understand what is the dimensions of the output of these operations. We will treat Q as a sequence of tokens with n tokens, so n tokens, where each token is has d dimensions, so lowercase d dimensions. Why? Because usually we take the queries and then we split them into multiple heads. So we pretend we have already done this splitting. So we pretend we already took our input sequence, we already run it through WQ, and then we have already split it into multiple heads. And each of these head will do the following operation. So the one we already saw, and so the usual formula, query multiply the transpose of the keys, and each of these head will work with these dimensions for the query, for the key, and for the value sequence. So now let's look at the dimensions of the output. So the first operation that we will do is the query multiplied by the transpose of the keys, where the transpose of the keys is a matrix that originally is n by d, but with the transpose will be d by n, so d by n, and the result will be a matrix that is n by n, because in a matrix multiplication the outer dimensions become the dimension of the output matrix. What is the next operation that we do? We take the output of this operation, so the query multiplied by the transpose of the keys, and we run it through a softmax operation, and we will see what is the softmax operation, which preserves the shape of the input. So it doesn't change the shape of the input matrix, it just changes the values of it. And then we take the output of this softmax and we multiply it by v, which will change the of course the shape, because the P matrix is n by n, so this one is n by n, and V is n by d, so this one, the output will be n by d, the outer dimensions of this matrix multiplication. Now let's look at the details of each of these operations. So when we do query multiplied by the transpose of the keys, we will get a matrix that is n by n, where each value in this matrix is a dot product of a row of Q and a column of K. In particular, the first element of this matrix will be the dot product of the first query with the first key vector. The second element will be the dot product of the first query with the second key vector. And the third element will be the first query with the third key, etc., etc. And let's say the last row of this matrix will be the dot product of the last query with the first key, then the last query with the second key, the last query with the third key, etc., etc., until the last query with the last key. You may also notice that here I have written query transpose the key, because when we what is Q1 first of all? Q1 is the first row of the query matrix. So little bit of background on matrix multiplication. So we know that when we do matrix multiplication, each output element is one row of the first matrix with one column of the second matrix. But we are doing the product of the first matrix with the transpose of the second. So it will be the dot product of the one row of the query matrix with one row of the key matrix, because we are doing the multiplication with key K transposed. When you take a vector from a matrix, the usual notation, so in mathematics, in a linear algebra, we always pretend that a vector is a column vector. So we cannot just write Q multiplied by K, because that would mean we are doing the dot product of we are doing the kind of the matrix multiplication of one column matrix with one column matrix. That is not possible because the shapes do not match. So as a notation, we write that we do the dot product of the first matrix transpose, which is a column vector, but we transpose it so it becomes a row vector, with the second vector. This is just because of notation, guys. So you just need to pretend that this is the first query with the first key, then the first query with the second key, the first query with the third key, etc., etc., etc. So we are doing dot products of vectors. Then we apply this softmax operation. The softmax operation, what it will do? It will transform each of these dot products, which are scalars. So the output of a dot product is a scalar. And it will transform each of these numbers in such a way that they become kind of a probability distribution row-wise, which means that each of these numbers is between 0 and 1, and when we sum up these numbers together, they are sum up to 1. And this condition, this property, will be valid for each row. So this row also will sum up to 1, this row will sum up to 1, and this row will sum up to 1, etc., etc., etc. Let's see what is the softmax operation. Now, given a vector, so let's call it x, which is made up of n dimensions, the softmax is defined as follows. So it is the softmax basically transforms this vector into another vector with the same dimension, where each item of the output vector is calculated as follows. So the ith element of the output vector is the exponential of the input element divided by the summation of all the exponentials of all the dimensions of the vector. Basically, this is called the normalization factor. To make it all these numbers between 0 and 1, we usually normalize. That's why it's called the normalization factor. And we use the softmax because we want each of these numbers to be positive. We don't want the output of this operation to be negative, so that's why we use the exponential. But there is a problem. The problem is, imagine our input vector is made up of many numbers that are maybe large. So for example, let's say x1 is equal to 100, x2 is equal to 200, x3 is equal to 300, which can happen. If we do the exponential of these numbers, so the exponential of 100, that is going to be a huge number. It's going to very close to infinity. At least compared to what we can store in a computer. So the output of exponential of 100 may not fit into a floating point 32 or a floating point 16 number, or even an integer of 32-bit. So we cannot compute it because it will overflow our variable, our integer that is storing this value, this output. So we talk in this case about numerical instability. So every time you hear the term numerical instability in computer science, it means that the number cannot be represented within a fixed representation with the bits we have available, which are usually 32-bit or 16-bit. We have also 64-bit, but that will be too expensive to use. So let's try to find a solution to make this stuff here computable and numerically stable. In order to make this softmax operation numerically stable, which means that we want these numbers to not explode or to become too small, that they are not representable, we need to find a solution. And luckily it's quite easy. So the softmax, as we have seen before, it is the following formula. So each number is exponentiated and then we divide it by this normalization factor, which is just the sum of the exponential of each input dimension of the input vector. If we multiply the numerator and the denominator of a fraction with a constant, with a number, then the fraction will not change. So that's what we are going to do. We are multiplying the numerator and the denominator with this factor c, as long as c is not equal to 0, of course. Then we can take this c and by using the distributive property of the product with respect to the sum, we can bring this c inside of the summation, as you can see here. Then we can also write every number as the exponential of the log of itself, because the exponential and the log will cancel out. And then we can, by using the properties of the exponentials, we know that the product of two exponential is equal to the sum is equal to the exponential of the sum of the arguments of each exponential, and we do it on the numerator and in the denominator. Then we just call this quantity minus log c equal to k, or k is equal to minus k is equal to log c. So we can replace this quantity with k. We can do that because this is a constant that we have chosen, and we just are assigning it to another constant. So basically, by doing this derivation, we can see that we can sneak in a value inside of this exponential that, if chosen carefully, can reduce the argument of this exponential. And we will choose this k equal to the maximum element inside of the input vector that we are applying the softmax to, so that each of these argument will be either 0 in case xi is equal to the maximum element that we are processing of the vector, or it will be less than 0, and we know that the exponential, when it's equal to 0, will be equal to the output of the exponential will be 1, so the argument when it's 0 it will be equal to 1, and when it's smaller than 0, so it's in the negative range, it will be between 0 and 1, so which is easily representable with floating point 32, for example. So this exponential will not explode anymore. So basically, to apply the softmax to a vector in a numerically safe way, we need to find a k constant, which is the maximum value of this vector, and when we apply it, we need to subtract each element minus this constant that we have chosen. So let's look at the algorithm to compute the softmax. So first of all, given a vector or given an n by n matrix, because we want to apply the softmax to this matrix here, which is n by n, we need to go through each row of this matrix, and for each row we need to find the maximum value among the elements, which takes time complexity linear with respect to the size of the vector, to the size of the row to which we are applying the softmax. Then we need to compute the normalization factor, which is this stuff here. And we cannot compute it before the step number 1 because we need to have the maximum element to compute this summation here. And after we have calculated the normalization factor, we can then divide each element's exponential by the normalization factor. And we cannot do the step number 3 before calculating the normalization factor because we need to divide each number by the normalization factor. So if you like pseudocode for algorithms, this is an algorithm for computing the softmax that we have seen right now. So first we find the maximum of the row to which we are applying the softmax. Then we compute the normalization factor, and then we apply the softmax to each element, which means that we compute the exponential of each element minus the maximum value of the vector divided by the normalization factor. Now, this pseudocode is an algorithm that is quite slow because look at a practical example. Imagine we have this vector here. First, we need to do step 1, find the maximum value in this vector, which is number 5, and this takes linear time computation. Then we need to calculate the normalization constant, which is the sum of the exponential of each element minus the maximum value, so e to the power of 3 minus 5 plus e to the power of 2 minus 5, etc., etc. And this we will call it L, and then we need to go again through this vector again and take the exponential of each element minus the maximum divided by the normalization factor. So to apply the softmax to an n by n matrix, we need to go through each element of this matrix 3 times, and these operations must be done sequentially. So we cannot start operation 2 until we have done operation 1, and we cannot start operation 3 until we have done 1 and 2. So this is quite slow, only to apply an operation that doesn't even change the shape of the matrix, it's just normalizing the values. So there must be a better way that does not involve 3 sequential operations in which we need to go through this matrix 3 times. Let's see. Alright guys, let's rehearse what is the problem that we are trying to solve. The problem statement is the following. Can we find a better way to compute the softmax that does not involve going through the vector 3 times? Because let's look at the pseudocode of the algorithm for computing the softmax that we have found so far. Imagine we have a vector made up of 4 elements. The first thing that we need to do is to compute the maximum element in this vector, which means going through this for loop here that allows us to compute the maximum element in this vector, which means that we start from the left side of the vector and iteratively go to the right side. So we start from the first element, arrive to the end, and we compare the previously found maximum with the current element to find the global maximum. Basically, this means that I know that this is very simple. I'm probably sure that you don't need to do this example, but making this example will help us understand what we will do next. So please bear with me, even if it's super simple what I'm doing. Okay, at the beginning m0 is equal to minus infinity. M1 is basically the for loop at the iteration number 1, which means that M1 will be equal to the maximum of the previous estimate of the M, which is minus infinity, with the current element, which is 3, so it will become equal to 3. Then M2 will be equal to the maximum of the previously computed maximum, so M1, so 3, with the current element, which is 2, so it will be equal to 3. M3 will be equal to the maximum of the previously computed maximum, so 3, with the current element, which is 5, so it will be equal to 5, and M4 will be equal to the maximum of the previously computed maximum and the current element, so it will be equal to 5. So this allows us to compute the maximum element. So at the 4th iteration, we will have the global maximum, independently of what is the input array. Delete. Okay, after we have computed the maximum, which we know is 5, we can compute the normalization factor. So let's start with the L0. L0 is equal to 0. L1 will be equal to the exponential of L0. So actually, sorry, it will be L0 plus the exponential of the current element, so 3, minus the maximum element we have found in the previous for loop, so 5. Then L2 will be equal to L1 plus the exponential of the the current element, so it's 2 minus the maximum, then L3 will be equal to L2 plus the exponential of the current element 5 minus 5, then L4 will be equal to the L3 plus exponential of 1 minus 5. If you expand this L, this will be basically equal to e to the power of 3 minus 5 plus e to the power of 2 minus 5 plus e to the power of 5 minus 5 plus e to the power of 1 minus 5. After we have computed this normalization factor, we can use it to normalize each element in the input vector, which means that the x new x1, so x1 prime, let's say, will be equal to e to the power of, what's the first element? 3 minus 5 divided by L that we computed in the previous for loop, so the L at the fourth iteration. The new x2, so x2 prime, will be equal to the e to the power of 2 minus 5 divided by L4, and x3 prime will be equal to the e to the power of 5 minus 5 divided by L4, etc., for all the elements. I know this is super simple, but it will help us later. So, in this for loop, we have that we need to go through the vector 3 times, because first we need to compute this for loop, then we need to compute this for loop, and then we need to compute another for loop. We cannot do them not in this sequence, because in order to compute this for loop, we need to have the maximum element, because we need it here. And we cannot compute this for loop until we have computed the previous one, because we need to have the normalization factor. However, we are stubborn, and let's try to fuse these two operations into one for loop, which means that we go through the array and simultaneously compute mi, and in the same iteration we also try to compute lj. Of course, we will not be able to compute lj because we don't have the global maximum, because we didn't go through all the array yet. However, let's try to use the locally, whatever estimate we have of the maximum so far. So let's try to use, instead of mn, let's try to use mi, so the local maximum that we have computed so far. So if we apply the softmax in this way, in this fused way to this vector, we will have the following iterations. So this is our array or vector, and the first step is mi, so m1 will be equal to the previous maximum, which is minus infinity, with the current element, so the maximum minus infinity and the current element is equal to 3. And L1 will be equal to the previous L, so L0, which starts from 0, plus e to the power of the current element minus, we should be using the global maximum, but we don't have the global maximum, so let's use the whatever maximum we have so far, so we can use 3. Now, at the second iteration, we are at this element of the vector, and we compute the maximum so far. So the maximum so far is the previous maximum and the current element. So the maximum of the previous maximum and the current element, which is the maximum between 3 and 2, which is 3. And the normalization factor is the previous normalization factor plus exponential of 2 minus 3, which is the current element, minus whatever maximum we have so far. Now, if our array were made only of these two elements, so 3 and 2, then whatever we have computed is actually correct, because the maximum that we have found is 3, and it's actually the global maximum, and the normalization factor that we have computed is actually correct, because each of the exponential has been computed with the global maximum, because the first element was computed using 3 as the with the argument minus 3. And also the second element was computed with the argument having minus 3 in the argument, which is the global maximum of the vector. However, when we arrive at the third iteration, so let me delete this vector. So when we arrive here at the third iteration, the maximum will change, which will also cause our normalization factor to be wrong, because we arrive at the element number 3. So the number 5 here, and we computed the maximum. So the maximum is the comparison of the previous maximum and the current element. So the new maximum becomes 5. And the normalization factor is the previous normalization factor, so L2 plus the exponential of the current element minus the current estimate of the maximum, which is 5. However, if you look at this L3, this is wrong, Why? Because L3 is equal to, if you expand this summation, it will be equal to e to the power of 3 minus 3 plus e to the power of 2 minus 3 plus e to the power of 5 minus 5. This exponential here is using 5 as the global maximum. This exponential here is using 3 as the global maximum, and this one is using 3 as the global maximum. So the first two elements have been computed thinking that the global maximum is 3, but actually later we found a better global maximum, which is 5, so which makes this normalization factor wrong. However, can we fix at the third iteration whatever normalization we have computed so far up to the second iteration? Actually, we can. Because if we expand this, so as we have here, we have expanded it, what we need here is here to have a minus 5, because that's actually the global maximum that we have found so far, not the minus 3 that we had at the previous iteration. So, and here we also need to fix this, replace this minus 3 with minus 5. How can we do that? Well, if we multiply this one here and this one here with a correction factor that will sneak in a new maximum inside of this exponential, then we solve the problem. And actually this correction factor is very easy to calculate, because at the third iteration, if we multiply L2, so the previously computed normalization factor, with this factor here, which is the exponential of the previous estimate of the maximum minus the current estimate of the maximum, so 5, we will see that by the properties of the exponentials, this one here will become e to the power of 3 minus 3 plus 3 minus 5. So this minus 3 will cancel out with this 3. And also the second factor will have this 3 will cancel out with this minus 3 will cancel out with this 3. And they will become e to the power of 3 minus 5 and 2 to the power of e to the power of 2 minus 5, which is actually correct, because at the third iteration we should be actually we should be using minus 5 as the maximum of the array so far. So basically what we have found is a way to fix whatever normalization factor we have computed so far while iterating through the array when we find a better maximum compared to what we have so far. And when we don't need to fix anything, then the formula still stands, because what we did here as a multiplication, as a correction factor, so this is the correction factor. This correction factor is nothing more than the previous maximum, so the previous estimate of the maximum, minus the current estimate of the maximum at the current iteration, so the current max. So this is basically m of I minus 1, and this is m of I, so the current maximum at the current iteration. And let me delete it, otherwise it remains forever in my slides. So basically when we arrive to the last element, we will see that the maximum doesn't change, because we compare the previous maximum with the current element, which is less than the previous maximum, so the maximum doesn't change. And we don't need to fix anything, because the previous L3, so the previously computed normalization factor, is correct, because they have all been using the minus 5. So when we don't need to fix anything, we just multiply by e to the power of the previous maximum minus the current maximum, which is e to the power of 0 in this case, so it's not fixing anything. So we have found a way to fix the previously computed normalization factor while going through the array, even if at the current iteration we don't have the global maximum yet. So that every time the maximum changes, we can fix, and every time it doesn't change, we just multiply with e to the power of 0, which is like multiplying with 1. So the new algorithm that we have found for the softmax is the following. So we start with m0 equal to minus infinity. We start with L0 equal to 0. We go through the array. We compute the local maximum, so the maximum so far from the 0th element to the ith element, so to the element at which we are doing the iteration. And the previously computed Li can be fixed by using this correction factor, which is e to the power of the previous maximum minus the current maximum, plus the exponential of the current element minus the current estimate of the maximum. In this way, we go through the array only once, and we obtain two values, the global maximum at the end, at the same time, the the normalization factor, and then we can use it to compute the softmax. So we transformed the 3 passes through the array into 2 passes through the array. And this is very important, and we will see how we actually use it to derive flash attention. The example that I have given you so far is not really a proof that our algorithm will work in every case, because we made a very simple example by using a vector made up of 4 elements. But does our new algorithm work in every single case with whatever the numbers are? We need to prove that. So we will prove that by induction. So first of all, what are we trying to prove? We have fused the first 2 for loops into one for loop, as you can see here. What we expect is that at the end of this for loop, this mn, so the m at the last iteration, will be actually the global maximum in the vector, and this ln, so the L at the last iteration, will be equal to the sum of all the exponential of all the elements minus the maximum element of the vector, so the global maximum of the vector. And we need to prove that, because what I did before was an example, and that was not really a rigorous proof. And the way we will prove it is by induction, which is a typical way of proving this kind of theorems. Now, proof by induction basically works in the following way. We need to prove that our algorithm works for a base case, for example, with n equal to 1, and then we assume that the algorithm works on n, and we need to prove that it also works for n plus 1. If this holds, then we have proven our algorithm for every possible n, because it will work for the base case, so for example n equal to 1, and then by using the induction step, we say, so this if it works for n, then it also works for n plus 1, then it means that it will also work for 2. But then if it works for 2, then it should also work for 3, because of the induction step that we will prove. And if it works for 3, then it will also work for 4, etc., up to infinity. So let's prove it for the base case, which is n equal to 1. It's very simple. So at n equal to 1, this for loop will only have one iteration, so m1 and l1. m1 will be the maximum of the previous m, which is minus infinity, because we initialize m0 equal to minus infinity. So it will be equal to the maximum of the previous m and the current element, which is x1. So it will be equal to x1, whatever x1 is. X1 usually will never be equal, it cannot be equal to minus infinity, because it's a number in a fixed representation, so it cannot be minus infinity. So the m1 at the end, so it will, because we have only one element, n equal to 1, this is m1 is also the last m of this for loop. It will be equal to the global maximum of the vector made up of only one element. And L1 will be equal to the previous L, which we start from 0, so L0, multiplied by a correction factor, which will be, in this case, e to the power of minus infinity, because the correction factor is the previous estimate of the max minus the current estimate of the max, but the previous estimate of the max is minus infinity, minus x1, it is equal to minus infinity. So this one will be cancelled out. And then plus e to the power of x1 minus the current maximum, which is x1, so m1. And if this one will be equal to the sum of all the elements of the vector, which is made up of only one element, minus the maximum element in the array, which is x1. So we have proven that it works for n equal to 1. Now we assume that it works for n. Does it also work for an array of vector or with a vector of size n plus 1? So let's see what happens at the n plus 1th iteration. At the n plus 1th iteration, we will be doing the maximum of the previous estimate of m, which is the m at the nth iteration, and the current element, so xn of plus 1. This, by the properties of the max function, it will be actually equal to the maximum of the global vector up to n plus 1. Because the maximum will choose whatever is the maximum between the previous estimate and the current estimate. And Ln+1, which is the normalization factor at the n+1th iteration, will be equal to the Ln, so the previous estimate, not previous estimate, but the previous normalization factor at the nth iteration, multiplied by the correction factor, which is the previous maximum minus the current maximum, plus the exponential of x, the current element, minus the current estimate of the maximum. But Ln, we assume that this property, so this algorithm works up to n. So Ln is for sure equal to the sum of all the exponentials of the previous of the vector up to n minus the local maximum of the vector up to the nth element, which is mn. We multiply it by the correction factor if there is something to correct, which will be the previous maximum minus the current maximum plus the exponential of the current element minus the current estimate of the maximum. Now, by the properties of the exponentials, so we can bring this one inside of the summation, and we will see that this mn and this mn will cancel out because it will be exponential of xj minus mn plus mn minus mn plus 1. So this mn and this mn will cancel out, and we obtain this one plus this factor here that remains unchanged. However, you can see that this stuff here is exactly the argument of this summation for at the iteration n+1. So it is, this one is e to the power of xj, where j is going from 1 to n, minus mn plus 1, plus e to the power of xn plus 1 minus mn plus 1. So the j only appears here, and it's equal maximum to n, and this is similar to being a j with n plus 1. So we can increase the index of this summation by 1, and it will be the same, and it will result in the same summation. So we have proven that also at the n+1th iteration, we will have that the L will be equal to the sum of all the elements of the array, the exponential of all the elements of the array up to the n+1th element, minus the maximum up to the n+1 element. So we have proven that if it works for n, then it also works for n+1. This is enough to prove that it works for all size of arrays. Don't worry if you didn't get the proof by induction. It is if it's the first time you are seeing this kind of proof, it may take a little bit to get it. If you want to learn a little bit more about proof by induction, I recommend watching some other proof. It's very simple. It's just you need to get into the right mindset. Anyway, let's move forward. All right. Let's talk about block matrix multiplication. I know that you want to jump to the code immediately, and we will go there. We just need a little more theory, actually. So imagine we are doing a matrix multiplication. So we have a matrix A. We want to multiply it with a matrix B, and it will produce an output matrix C. Imagine the dimensions of the first matrix are m by k. The second matrix is a k by n. It will produce an output matrix that is m by n. Now, imagine we want to parallelize the computation of this output matrix. I know that I didn't talk about GPUs yet, so we will not talk about the GPUs. We will talk about parallelization in the case of a multi-core CPU, with which you are very probably familiar with, because right now, nowadays, when you buy a computer, you have a CPU, and usually you can buy a single core CPU or multi-core, like a 2-core, 4-core, 8-core, etc., etc. Each of these cores are actually kind of small CPUs inside your CPU that can execute operations in parallel. How to parallelize the matrix multiplication? Imagine you have this matrix multiplication to parallelize. Each of the output element in this C matrix is a dot product of a row of the A matrix with a column of the B matrix. For example, this element on the top left is the dot product of the first row of A and the first column of B. This element on the top right of C is the dot product of the first row of A and the last column of B. This element on the bottom left is the dot product of the last row of A and the first column of B, etc., etc., for all the other elements. Now, to parallelize this computation, we need as many cores as there are elements in C if we want to parallelize it. So if M and N are very small, then maybe we have enough cores. But imagine M and N are quite big. We imagine like 100 by 100. We don't have 10,000 cores right now in the CPUs. So how can we parallelize a matrix operation by using less cores than there are elements in the matrix itself? That's when we talk about block matrix multiplication. Basically, block matrix multiplication means that you can divide the original matrix into smaller blocks of elements, and then the operations of matrix multiplication can be computed between these blocks. For example, imagine we have a matrix that is 8 by 4. It means that it has 8 rows and 4 columns, which means that it has 32 elements. And then we are multiplying it with another matrix that is 4 by 8. So it has 4 rows and 8 columns. So it also has 32 elements. The output matrix should have 64 elements. We don't have 64 cores. So how can we parallelize it? Imagine we only have 8 cores. Now, with 8 cores, we can divide this original matrix A into 4 blocks, where the first block is this top left block of 4 by 2 elements. So, 8 elements on the top left, and then 8 elements on the top right of this matrix, then 8 elements on the bottom left, and 8 elements in the bottom right of this matrix. These are 4 blocks. Then we divide also the B matrix into 8 blocks, where each block is made up of 4 elements. So this B11 is the top left 4 elements in the original matrix. This B4 is the top right 4 elements in the original matrix. This B21 is the bottom left 4 elements in the original matrix, etc., etc., etc. How do we do this block matrix multiplication? We can watch these matrices as made only by their blocks. So we can view this matrix here as made up only by its blocks. We can view this matrix here as made up only by its blocks. And the output of this multiplication will be a matrices that is computed in the same way as the original matrix, but where the output of each dot product will not be a single element of the output matrix, but it will be a block of elements of the output matrix. For example, the top left block here is the dot product of the first row of this matrix with the first column of this matrix, and it will be computed as follows. So it will be A11 multiplied by B11 plus A12 multiplied by B21, and this output will not be a single scalar, but it will be well, let me count. It should be 8 elements, so it should be 4 made up. It should be a block of 4 elements. Or 8 elements. Let me count actually. So because we have 8 blocks and it should be made up of 8 elements. We can see that here. How to find the dimensions of this output block? Well, we can check what is A11. A11 is 4 by 2, so it's 8 elements as a smaller matrix made up of 8 elements, where the elements are distributed in 4 rows and 2 columns. We are multiplying it by B11, which is a smaller matrix compared to the original, made up of 2 by 2 elements, so 4 elements. So when we multiply 4 by 2 multiplied by 2 by 2, it will produce a 4 by 2 output block matrix, so block. So if we do this computation here block by block, it will produce a block of output elements of the original matrix. So not a single scalar, but a block of outputs, which makes it very easy to parallelize, because if we have only 8 cores, we can assign each output block to one core, and each core will not produce one output element of the original matrix, but it will produce 8 elements of the original matrix as a 4 by 2 matrix. So basically block matrix allow us to to do the matrix multiplication either by element, so like in the original matrix, so each row with each column, or blocks by blocks in the same way like we do normal matrix multiplication, because the matrix multiplication that we are doing between blocks is the same way as we do matrix multiplication with the original matrix, and it will produce not a scalar but a block. And now let's see why this is very important for us. So, why should we care about block matrix multiplication? Because we are trying to compute the following operation. So the query multiplied by the transpose of the keys, and then we should apply the softmax of this operation, and then we should multiply the output of the softmax with v. For now, let's ignore the softmax. Let's pretend that we are not going to apply any softmax. So we take the output of the query multiplied by the transpose of the keys, and we just multiply it by v to obtain the output of the attention, which is wrong, of course, but it simplifies our tractation of what we are going to do next. So for this moment, let's pretend that we are not going to apply any softmax. So we just do the query multiplied by the transpose of the keys, and directly we multiply the result of this operation with v. This will result in a matrix that is n by d, so n tokens, each made up of an embedding of d dimensions, so lowercase d dimensions. And we know that query key and values are themselves matrices of n by d dimensions, so the n tokens which made up of an embedding of d dimensions. So imagine we have a query matrix and the key and the value matrix that are 8 by 128. So we have 8 tokens, each token is made up of 128 dimensions. We can divide, as we have seen, when we compute a matrix multiplication, we can divide our matrix into blocks. How we choose the blocks is up to us, as long as the shapes of the blocks match when doing the matrix multiplication. So for example, in the previous case, we divided our matrix A into blocks such that the shape of the block matrix, so the matrix that is made up only of the blocks, is compatible with the block matrix B, so that this operation is possible. So this is the only requirement that we need to be aware when doing the block matrix multiplication. The shapes of the blocked matrix, so the matrix that is made only of the blocks, should match in the matrix multiplication. For the rest, it doesn't matter how we divide it. So imagine that we choose to divide this query matrix into blocks of rows, and we can do that. We don't have to necessarily divide also the columns. We can just divide the rows, so that each queue is not a single row, but it's a group of 2 rows. So Q1 is a group of the first 2 rows of the queue matrix, of the queue sequence. Q2 is the group of the second 2 rows of the queue sequence, etc., etc. And we do the same also for V. For k, we don't do it because we are actually going to multiply with k transposed, so we do this subdivision directly on k transposed. So we have the queue, which has been divided into groups of rows, and then we have a k transposed, which is a matrix that is 108 by 8, because it's the transpose of the keys, which is 8 by 108. And we decide to divide each of the group of columns of k into a single block. So the k1 is the first 2 columns of k transposed, k2 is the second group of 2 columns in k transposed, etc., etc., until k4, which is the last 2 columns in k transposed. The first operation that we do is the multiplication query multiplied by the transpose of the keys, which basically means that we need to multiply each query with all the keys, then the second query with all the keys, etc., etc. Now, each query is not a single row of the queue sequence, it's a group of 2 rows of the queue sequence, and each k is not a single column of k transposed, it's a group of 2 columns of k transposed. But doesn't matter, because we have seen that the matrix multiplication, if we write the matrices as made up of blocks, we just compute it in the same way when we do normal matrix multiplication. So we are multiplying this matrix by this matrix, and for what we know, this matrix here is made up of 4 rows with some dimensions, which is 128 dimensions. And this one here is made up of how many rows? 128 rows and 4 columns. I didn't draw the columns because it's too many to draw here, but you need to pretend it's a lot of dimensions, one for each, 128 for each vector. And here you need to pretend that this is 128 rows. When we do the matrix multiplication, we apply the normal matrix multiplication procedure, which is each output element. So this, first of all, the output shape of this matrix multiplication will be 4 by 4 because it's the outer dimensions of the two matrices that they are multiplying. The first element of the output will be the dot product of this vector here with this vector here. The second element, so this one here, will be the dot product of this vector here with this vector here. However, this is not vector and this is not a vector, so it's actually a matrix multiplication. In this case, this element here is not a scalar, it is a group of elements of the output matrix because we are doing block matrix multiplication. And how many elements it will be? Well, we know that the original Q1 is 2 by 128, the K1 is 108 by 2, so it will be a group of 2 by 2 elements of the output matrix. So we are doing the matrix multiplication of the Q1 with K1, then Q1 with K2, then Q1 with K3, Q1 with K4, etc., for the first row. And then the second row will be Q2 with all the Ks, and the Q3 with all the Ks, and Q4 with all the Ks. So as you can see, when we do matrix multiplication, we don't even care if what is underlying is a block or a vector or a scalar. We just apply the same procedure. First, row of the block matrix multiplication with the first column of the matrix of the second matrix, and then the first row with the second column, the first row with the third column, etc., etc. Let's then multiply, because the formula says that we need to multiply query with the transpose of the keys and then multiply by v. All of these are block matrices. Now, as you can see from my using of colors, every time I refer to the original matrix, I use the blue color, and every time I refer to the block matrix, I use the pink color. So we need to multiply the output of the query multiplied by the transpose of the key, then by v, because we are skipping for now the softmax, and later we will see why. So if we want to do this multiplication, we need to do the following. So it will be this matrix is made up of blocks, and block matrix multiplication just ignores this fact and just does the matrix multiplication like it is a normal matrix multiplication. So we do the first row with the first column, then the first row with the second column, then the third row, the first row with the third column, etc., etc. So the first block of row, how is going to be calculated, this output in the output matrix of this matrix multiplication? Well, it will be the first row, so the dot product of the first row, the dot product, because it's not really a dot product, it's actually the matrix multiplication of the first row, but in a dot product way, let's say, with the first column, which is made up of V1, V2, V3, and V4. So it will be this element with V1 plus this element with V2 plus this element with V3 plus this element with V4, and this will be the first output element. The second output block will be this row with this column, which will be this element with V1, this element plus this element with V2, plus this element with V3, plus this element with V4, and this will produce the second output block, etc., etc., also for the third and the fourth block output. Let's look at what is each block made up of. So each block is made up of the first element, so query 1 multiplied by key 1, because it's the result of the query multiplied by the keys, with the V1 of the second matrix plus this element with this one, plus this element with this one, plus this element with this one. So the pseudocode for generating this output of this attention mechanism, which is not really attention mechanism because we skip the softmax, but I just want you to get into the habit of thinking in terms of blocks, is the following. So we take each query block, we go through each query, and as you can see, let's look at actually what this output is made up of. It is made up of the query 1 multiplied by key 1 and the result multiplied by V1. Then the query 1 with K2, then the result multiplied by V2. Then the query 1 with the K3 and the result multiplied by V3, plus the query 1 with the K4 and the result multiplied by V4. This is basically what we are doing, is the dot product of this row with this column made up of blocks. So the pseudocode for generating this first row is the query is then query number 1, and then we iterate through the keys and the values from 1 to 4, and we sum iteratively. So for each block, basically, to generate this output matrix, and if you for each row, we will see that it's a different query with all the keys and values, and then this will be the query number 3 with all the keys and values, and this will be the query 4 with all the keys and values. So to generate this output matrix, we iterate through the queries, and this will be one row of this output matrix, and then we need to do this iterative sum of the query I that we are iterating through, multiplied by the jth, k, and v, and we keep summing them iteratively, and that will produce the output matrix, or you can see here. I know that what I have done so far is not useful for Flash attention, but it's useful for us to get into the mindset of computing this product by blocks, because later we will use it also with the Softmax. Alright guys, I know that what we have computed so far is not really the softmax operation, is not, really the attention mechanism, because we have skipped the softmax. So somehow we need to restore it. And the following few, I think 10-20 minutes, we are going to be really challenging, because I am going to do a lot of operations that will involve a lot of different blocks and a lot of different matrix multiplication and variants of the softmax. So it may be difficult to follow. However, don't give up. You can watch this part twice, 3 times, and every time it will have a better understanding. I also recommend watch it until we reach the flash attention algorithm before restarting to go back to rewatch it. Because you watch it, we reach the flash attention algorithm, and it will give you a better understanding of what have happened so far, and then you can rewatch it to deepen your understanding. Another thing that I recommend is take pen and paper and write exactly the operations that you are seeing, and write the shapes of each of these blocks, of these elements that are made that are part in these matrix multiplications, so that you better understand what is happening, and you better remember when I refer to a particular element or a particular block. Okay. After giving this small motivational speech, let's start. So what we have done so far was query multiplied by the transpose of the keys. However, each query is not a single row of the query sequence, but it's a block of queries. It's a block of rows. In our particular case, this Q1 is not one row of the query sequence, it's 2 rows of the query sequence, because we have chosen as a block size a group of 2 rows. And this K transposed 1 is not one column of the K transposed matrix, is 2 columns of the K transposed matrix, because we have chosen it like this. And if you don't remember, let's go back to see it. Here we have chosen K1 is 2 columns, and Q1 is 2 rows of the query original matrix. And every time I use the blue color, I am referring to the original shape, and every time I'm using the pink or violet, whatever it is, I am referring to the block matrix. So it's a block of elements of the original matrix. Okay, now the first thing that we have done was a query multiplied by the transpose of the keys, and this produces a block matrix as output that we will call S, where each element Sij, so the S11 element of this matrix, will be the query 1 with the K transposed 1, the S12 will be query 1 with K transposed 2, S13 will be query 1 with K transposed 3, etc., for all the rows and for all the columns. Then we should be applying the softmax, because if you remember, the formula is softmax of the query multiplied by the transpose of the keys. However, I want to restore the softmax operation, but with a twist, which means that we will apply the simplified version of the softmax, and we will call it softmax star, which is just the softmax without the normalization. So let me write it for you what it means. Let's do it with the same color that I chose for the softmax, which is orange. So the softmax, if you remember correctly, if we remember, it's the softmax of of a vector, we apply it element-wise. So each element is modified according to the following formula. So the ith element of the output vector to which we are applying the softmax is equal to the exponential of the ith element of the input vector minus the maximum element in the input vector divided by a normalization factor that is calculated according to this summation, that is going from j equal to 1 up to n of the exponential of xi minus x max. So basically we are doing the exponential of each element minus this x max. And why are, if you remember correctly, why are we subtracting this x max? To make this exponential numerically stable, computable, because otherwise it will explode. And because we are applying it to the numerator, we also need to apply it to the denominator. Okay, the softmax star operation is exactly like the softmax, but without the normalization part, which means that it's just the numerator of the softmax. So we will modify each element of the vector to which we apply the softmax star according to this formula. Let me move it more aligned, like this. So we just do element-wise operation, that is the exponential of each element minus the maximum of the vector to which we are applying softmax star. Okay, now, why did I introduce this softmax star operation? Because we will be applying it to the matrix that we have computed so far, which is this S matrix. So we apply the softmax star to each element of this S matrix, but each element of this S matrix is itself a matrix because it's a block matrix. And each element of this S matrix, so for example, the element S11 is a 2 by 2 matrix because it is coming from the product of two matrices, which are a group of rows and a group of columns from the Q and the K. So for example, this S11 is what? Let's draw it actually. This S11 will be, for example, made up of 4 elements. Let's call it, I don't know, A of S11. Let's choose better naming. Let's call it, I don't know, A, B, C, and D. Just the generic elements. When we apply the softmax star to this S11, it will result, so let's apply the softmax star. Softmax star. It will result in a matrix that is each element, the exponential of each element minus the maximum for each row. Now, we don't know which is the maximum, so let's choose one. Suppose that the maximum for this row is A and the maximum for this row is D. The first element of the output of this softmax star applied to this block S11 will be the exponential of A minus A, because that's what we chose as the maximum for this row. The second element will be the exponential of B minus A, because it's the maximum for that row. Then in the bottom row, it will be the exponential of C minus D, because that's the maximum for the bottom row, and this will be the exponential of D minus D, and that's the exponential. That's how the softmax star will modify each block in this block matrix. Let me delete this stuff, otherwise it will remain in my slides forever, and later I want to share the slides with you guys so you can use my same slides. So delete, delete, delete. Okay. After we have applied the softmax to each of the elements in this S matrix, we will call it the P matrix. And each element P11 will again be a block of 2 by 2 elements. So P11 will be the softmax. So P11 will be the softmax star applied to S11, where S11 is what? Is query 1 K transpose 1. And the P12 will be the softmax star applied to S12, where S12 is what? Is query 1 multiplied by K transpose 2, etc., etc., etc. for all the elements of S. Okay, now that we have applied this softmax star operation, the next operation that we should be doing, according to the formula of the attention, is the softmax of the query multiplied by the transpose of the keys, then the result of the softmax multiplied by V. I know that we didn't apply the real softmax, we applied the softmax star, which is a softmax without the normalization. Later we will see how to compensate this lack of normalization, because we will do it at the end, and it's something that we can do. Okay, so we take this P matrix, which is the result of the softmax star applied to this S matrix, and we multiply it by V. How do we do it? Well, it's a block, it's a matrix made up of blocks of matrices. So P11 is actually not a scalar, but it's a matrix of 2 by 2 elements. And we need to multiply it by V, but we don't multiply with the original sequence V, but with the blocked sequence V, just like before, where each V is not one row of V, but it's a group of rows of V. And how many rows is it? It is 2 rows of V. For now, please ignore completely whatever I have written here, because we will use it later. So we need to do this product of this matrix here, which is made up of blocks, remember, with this matrix here, which is made up of blocks. It is made up of 4 rows, where each row is not really a row, it is a block of rows. And this one, it is made up of 4 by 4 elements, where each element is not really a scalar, but it's a matrix. So, as you remember, in the block matrix multiplication, the algorithm for computing the matrix multiplication is the same as the normal matrix multiplication, except that we use blocks. So what I am doing is, guys, the following operation. So let's write it somewhere. Let's say O is equal to P multiplied by V. Okay. So the first output row, because it's not really a row, but it's a block row, will be computed as follows. The first row of this block matrix with the first column of this V matrix, and we are treating it like a block matrix, so it will be P11 multiplied by V1 plus P12 multiplied by V2 plus P13 multiplied by V3 plus P14 multiplied by V4. This will produce the first output row of O, but it's not really a row because it's made up of 2 rows. So this stuff here is not 1 row, it is 2 rows. And we can prove that, because what is P11? P11 is, let's write it somewhere. So P11 is a 2 by 2 matrix. 2 by 2, and we are multiplying it with V1, which is a block of 2 rows of V. So it is a 2 rows by 128 dimensions, so it is equal to 2 by 128. So this stuff here is 2 by 128. So this block here, the output block that we are computing, is a block of 2 rows of the output matrix that we are computing. I know this is really difficult to follow, because we are involving blocks, so we need to visualize at the same time matrix as blocks and as the original matrix. That's why I highly recommend you to pause the video, think it through, write down whatever you need to write down, because it's not easy to follow it just by memorizing the shapes. So you actually need to write down things. Anyway, we are computing the first output block of the output O matrix. Now, if you remember, this output here should be the output of the softmax multiplied by V. Now, this softmax has not been applied to the entire row of this matrix here, S matrix here. Basically, to compute this softmax star, what we did was to compute the softmax star at each block independently from the other blocks, which means that the maximum that we are using to compute each softmax star is not the global maximum for the row of this S matrix, but the local maximum of each block. And this is wrong, actually, because when we compute the softmax, we apply the softmax, we should be using the global row. I want to give you an example without using blocks, because otherwise I think it's not easy to follow. So when we do the normal attention, so we have a query multiplied by the transpose of the keys. This produces a matrix that is n by n, so sequence by sequence, where each element of this matrix, so let's say 3, 4, 5, 6, I don't know how many is 1, 2, 3, 4, 5, 6, yeah, 6, 2, 3, 4, and 5, 6 should be 1, 2, 3, 4, 5, 6, okay. This one here should be the dot product of the first query with the first, let me use, because query 1 transpose the key 1. This is because, as I said before, when we do the product of two vectors, we always treat them as column vectors. So when you want to write the dot product, you cannot multiply two column vectors. You need to multiply one row vector with one column vector. That's why we transpose this one. If it confuses you, you can also write Q1, K1. That's totally fine. It's just wrong from a notation point of view. Anyway, the first one will be the dot product of the query 1 with the K1. The second element will be the dot product of the query 1 with the K2. The third will be the query 1 with the K3, etc., etc., etc. So this is a Q1 with the K1, Q1 with the K2, K2, and the Q1 with the K3, Q1 with the K4. Anyway, when we do the softmax, we actually calculate the maximum on this entire row. However, what we are doing is we are actually doing a block matrix multiplication. And as you remember, when we do by blocks, we are grouping together rows of queries and rows of keys. And in this particular case, we are grouping the two queries together to create one group of queries and two keys together to create one block of keys. So we need another row of this one. So it's the, let me choose query 1, query 2, K1. This should be query 2, K1, query 2, K2, query 2, K3, query 2, K4, query 2, K5, and query 2, K6. When we each of this block here is computing, this block here is computing 2 by 2 elements of the original matrix if we had never applied the blocks. So it is computing these 4 elements here. And if we apply the softmax star to each of these blocks, we are not using the maximum element in this row. We are only using the maximum element in each block, which means that when we will use it in the downstream product with V matrix, we will be summing values that are wrong because each of these values here will be based on a maximum that is not the global maximum for this row. It is the local maximum of this block here, and this block here will have the global, it will use the local maximum of this block here, and this block here will use the local maximum of this block here, etc., etc., etc. So what I'm trying to say is that when you sum P11 with V1, P11 may have some maximum, local maximum that is different than from the local maximum of P12, and P13 may have a different maximum, local maximum that of P11 and P12. So we need to find a way to fix the maximum that was used to compute the exponential here with the maximum found here in case the maximum here is higher than the one local to P11. So if we have found, for example, here a maximum that is higher than the maximum used here, then we need to fix this one and this one, because that maximum in the softmax should be the maximum for all the row, not the one belonging to each block. And this leads to our next step, how to fix this. First of all, let me introduce a little pseudocode for computing this output matrix here, which is an output block matrix. And later we will use this pseudocode to adjust the error that we have made in some blocks in case the future blocks, so the P13, has a better maximum than P11 or P12. So to compute this output matrix O, we go through, so for example, to compute the first row, we choose, well, P11 is what? Let's go back, P11 is, let me delete also this one, it's not needed anymore. P11 is the softmax star of Q1, K1, P12 is the softmax star of Q1, K2, P13 is the softmax star of Q1, K3, P14 is the softmax star of Q1, K4, which means that to compute this block here, we first need to compute the P11. What is P11? Well, P11 is the softmax star of a block of Q and another block of K, which in the case of the first row of the output matrix means that it is the query 1 with the softmax star of the query 1 with K1, the softmax star of the query 1 with K2, the softmax star of the query 1 with K3, the softmax star of the query 1 with K4, which means that we need to make a for loop through all the keys while keeping the query fixed. So to compute the first output row, we need to do the softmax star. To produce P11, we need to do the softmax star of query 1 K1, and we sum it initially to zeros because we don't we need to initialize our output somehow, and we initialize it with zeros. Then we sum the next P12, which is the query 1 with the K2, and then we sum the next P13, which is the query 1 with the K3, etc., etc. That's why we have this inner loop here. All right, so however, this output that we are computing is wrong because I told you we have computed the softmax star using a statistics, the maximum value that is belonging to each block and not the one that is the overall row of the original matrix. How to fix that? We have a tool actually. We have computed before an algorithm called the online softmax. I don't know if I referred to it before as the online softmax, but it's called the online softmax, that allows to fix previous iterations when we are computing the current iteration. Based how? Well, let's review the online softmax. We start, imagine we are working with one single vector. So we are a vector made up of n elements. What we do is we do a for loop where we compute iteratively the maximum up to the ith element, and we fix the normalization factor computed in previous iteration in case we found a better maximum at the current element. If this is not clear, guys, go back and watch the online softmax because this is very important, because this is what we are going to use to fix this P11, P12 blocks in case we found better maximum in P13 or P14, etc. So let's see how to apply this online softmax to this case here so that we can compute. So you may be wondering, why are we going through all these troubles? I mean, why? The real reason is first of all, why did we introduce block matrix multiplication? Because we want to compute matrix multiplication in parallel. So you can think that each of these P11, because they are independent from each other and because each of them are using the maximum belonging to each block, they can be computed independently from each other. Then, however, we need to somehow aggregate their value. And to aggregate the value, we need to fix the values that have been calculated independently, because we didn't, when computing values independently, we don't have a global view. We have a local view. So we compute local blocks, P11, P12, P13, etc., etc. And then when we aggregate these values, we need to fix them. So that's why we are trying to come up with this system of fixing values that have been calculated independently. So how to fix this? Let's look at the following algorithm. First of all, this O block here, as I said before, it is a block of 2 rows, where each row is made up of 128 dimensions. And we have seen that before by checking the dimensions of P11 and V1, the result of P11, V1. Which means that for each output block, we need to take care of 2 maximums and 2 normalization factors. So up to now, I didn't use the normalization factor. We said that we are applying the softmax star, which is the softmax without the normalization, but eventually we will need to compute this normalization. So we want to create an algorithm that fixes the maximum used to compute each of these P11 and also computes simultaneously the normalization factor, and at the end we will apply this normalization factor. And the way we will do it is as follows. We start with initializing the maximum to minus infinity, one for each row that we are computing. So our output block is made up of 2 rows, so we need one maximum for the top row and one maximum for the bottom row, and also the normalization factor, which we initialize with 0 because we didn't sum anything for now. And the output, we initialize it with all zeros because we didn't sum anything to this output for now. We compute to compute the output row, so this output block here, we need to go through all the keys to produce this P11, P12, P13, P14, while the query is the query number 1, the query block number 1. So the first step that we do is we compute the maximum of the first block P11, which is the row max, so the maximum for each row of the block Q1, K1. This is not P11, it's S1. Sorry guys, this is S11. So we compute the maximum of this one, and we call it actually S1, as you can see here. Then we can calculate P11, which is the softmax star, which is the exponential of the query 1 K1, so S1, minus the maximum in the local group S1. And we add it to our output. For now, the output is initialized with 0, so for now, ignore this part here. I will explain it later. So for now, O1 should be equal only to P11 V1. Now, at the step number 2, we may find in the local group S12, so this one is S12, we may find a better maximum for the top row and the bottom row. And this maximum is the M2, which may be better than the previous maximum for each of these 2 rows, but may also not be. So we need to find a way to fix in case it's better and to not fix anything in case it's not better. And the way we will do it is this. So we compute the new maximum of the current local row, query 2. We calculate the P12, which is the softmax star of S2, which is S2 minus M2, which is the local maximum. And then we need to add it to the output. However, in this case, we may have found a better maximum. So how to fix the O1, which only use the maximum that was local to S1? Well, we know that we can fix that by using exponentials, because each of these elements of O1 is just an exponential without the normalization, because we are applying softmax star. So how to fix an exponential with another exponential? So basically we are saying that we multiply O1, which is a matrix. So let me show you what is this matrix. So O1 is a matrix made up of 2 rows. So as you can see here, I have the shape of O1. It's a 2 by 128 matrix. So this is the top row. So O11, O12, blah, 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 until O1, 128. Then O21, O22, blah, 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 and O2, 128. We need to fix this value. How? We basically just using the exponential that we have used in the online softmax that we have seen before. So if we multiply this matrix here by a diagonal matrix that is made as follows, it's a diagonal matrix made up of 2 elements, because the exponential of m1 minus m2 will be a vector of 2 elements, and the exponential of a element-wise exponential is another vector of 2 elements. And this diag basically means the diagonal matrix, where in the diagonal we have the elements of the vector to which we are applying this diag operation, which means that this value here will be the exponential of the first element of m1. So let me show you how to write it. Exponential of m1 minus m2 2, so the first element, so let's call it 1 here. Here is a 0, here will be 0, and let's delete this one and we write another one here. Exponential m1 minus m2, but the second element of this vector. So basically the diag, this notation here, diag, means basically just take the vector and distribute it over a n by n matrix, where n is the size of the vector to which it is applied, and all the other elements of this matrix should be zeros. This is what this diag means. If we do this operation here, we will see that the output of this multiplication will fix each element of the top row using this exponential and the bottom row with this exponential, which will basically cancel out this m1 that was computed in the previous iteration and introduce the m2 that we have computed in the current iteration in each of these elements in this O block matrix. Okay, so this output will be this element will multiply by this one, so it will fix O11 with this factor here, and O21 will not be fixed by, will be multiplied by 0, so it will not contribute to this first output element. So this element here will only depend on O11 fixed by the exponential of m1 minus m2, but the first element of this vector. And then O12 will also be fixed by O12 will be fixed by this exponential here, but not by this one. And all the dimensions of the first row will be fixed by this exponential, and all the dimensions of the second row here will be fixed by this exponential here. This scalar here, which is the second element of the vector exp of m1 minus m2. Okay, it was really challenging, this one. So what we are doing is we compute P12 and we fix all the elements in P1 by multiplying by this matrix here, by multiplying by this factor here, matrix factor here. And when we will compute step 3, we will fix step 2, etc, etc, etc. Now let's talk about the normalization factor, because for now we have been ignoring it. The normalization factor is something that we can compute while computing these maximums, because it is provided in the pseudocode of the online algorithm that we have seen before for the Softmax. So while computing the maximum, we can actually compute the normalization factor by fixing the normalization factor of the previous iteration, and this is exactly what we are doing here. So at the first iteration we computed the normalization factor using the local maximum, and at the second iteration, so you can for now ignore this one because we are not fixing L0 with anything, because L0 will be 0. So we are just basically we are just computing this summation here, so L0 will be 0, so this factor here will be 0. And when computing L2, so the normalization step at the second iteration, we will fix L1 with an exponential, which, guess what, it's exactly the same exponential that fixes the maximum, the P11. So it is the previous estimation of the maximum minus the current estimation of the maximum plus the new normalization factor using the local maximum. And we keep doing this job. At the end, we will obtain a correct output for this matrix, for this block here, but without the normalization. How to apply the normalization? Well, the normalization is something that is, we need to divide each element of this O by the normalization factor. But because we are keeping, while iterating through these for loops, we also calculate the normalization factor. We keep accumulating it until we reach the end of the iteration, and then we apply the normalization factor. So we take the last output and we just divide it by L4, which is the normalization factor calculated at the fourth iteration, and that will fix the softmax. Alright guys, so now that we have derived the algorithm of how to compute this output of the attention blockwise while also fixing the softmax, which is done independently in each single block, we know that the normalization is done at the end. I want to also prove it. So what we done when we introduced this algorithm that computes the softmax in an online way, we proved by induction that this algorithm is correct. So at the end of this algorithm, this L of the last iteration will actually be the normalization factor that we can apply to get the softmax. So we don't apply the normalization while computing this output in an online way, iteratively way, by multiplying the query with all the blocks of keys. We apply it at the end of this for iteration. And at the end of this for iteration, we will have the last output. And we also know that the last L will contain the exact normalization factor that we need to apply to each row, because this O of 4 is a block of output rows, which is, if you remember from the attention mechanism, each output, the output of the attention has the same shape as the input query vector, which is a sequence of tokens. So this O is a sequence of tokens that we need to apply the normalization to. And we know that the correct factor is L4. So let's prove this simple formula. L4 is a vector, that contains as many elements as there are rows in O4. So in this O block of rows. Suppose that it contains 2 rows, like in the algorithm that I have described so far, in which we pretend that we are grouping 2 rows of queries with 2 columns of keys together. So the output O, the block O, will contain 2 rows of the output. So we will have 2 normalization factor in this L4 vector here. What we are doing with this formula is we are taking this L4 vector and we are creating a diagonal matrix with it, and then we are computing the inverse of this diagonal matrix. So L4 is a vector that contains 2 normalization factors, so it's I don't know, let's call it L4 element 1 and L4 element 2. This is our L4 vector. Then we have O4. O4 is a matrix, as you can see from the shape, is a 2 by 128 matrix. So O is, let's copy it actually. Oh no, let's not copy it. O4 is a matrix that is 2 rows with 128 elements. So the first row with 128 dimensions and the second row with 128 dimensions. The first thing that we are doing with this L4 is we are converting it into a diagonal matrix, which will be a diagonal matrix 2 by 2 because it contains 2 elements. So it will become something like this. So it will be L4, the first element of L4, 0, and then 0, L4, the second element of this vector. Then we are computing the inverse of this matrix. The inverse of a diagonal matrix is just the diagonal matrix with each element on the diagonal that becomes its reciprocal. This is from linear algebra. It's not, I'm making this up. So the inverse of this matrix here is equal to the same diagonal matrix, but where each element is 1 over L4, the first element of L4, 0, 0, and 1 over L4, the second element of L4. And then we are multiplying this stuff here. So let me delete some stuff. So this stuff here is getting multiplied by O, which is a matrix that is 2 by 128. So we are doing this multiplication now. Multiply. Now, the output of this, so this is 2, let me write it, 2 by 2 multiplied by 2 by 128 will be a matrix that is 2 by 128, where the first dimension of the first row of the output of this operation will be the dot product of this row here with the first column. So basically we are dividing this element here by L4, the first element of L4. The second output element here will be the dot product of this row with the second column. So we are only dividing the second element here of this input vector here by L4, the first element of L4, because all the elements of the second row will be multiplied by 0. So they will not contribute to this output row. while the second output row will be the this element here will be the dot product of this row with the first column. The first element here is multiplied by 0, so it will not contribute to this output. So it's only the second element, the first row of the second, this first element of the second row of the input matrix here will be divided by L for 2. So basically this will be applied, will divide all the elements in the second row, and this will divide all the elements in the first row in producing this one here, which is exactly what we need to do when we want to normalize. We need to apply this normalization factor. And this should help you better visualize why this operation is normalizing the vectors of the output at the end and still obtaining the same result. Now let's proceed further. Alright guys, finally we are ready to see the flash attention forward pass by also comparing it with what we have derived so far. So if you look at the flash attention paper, first of all, this is the flash attention 2 forward pass, and later I will explain what are the differences between the flash attention 1 and the flash attention 2. I didn't want to jump directly to this forward pass because I believe that even if the derivation, like the derivation was a little difficult to follow, I believe that it gave you some intuition into what is happening. So even if you understand 50% of it, that's enough, because later we will also code it and you should reach like a 90% of understanding. So every time we introduce some new information, it should improve your understanding. So basically in flash attention, what we are, in flash attention 2 especially, we take our, as input we have our query key and values, which are a sequence of tokens. Each token is made up of a vector of d dimensions and d lowercase d dimensions. And we divide this query, guess what, into blocks. In how many blocks? Well, depending on this parameter br, which is the size of the query block that we want to choose. So how many rows of query we want to group together into one block. And we also do it with the k and v, and we divided that into blocks of depending on this parameter bc. Then we also initialize the output, which is the output that we want to produce. So what is the flash attention computing? Well, the flash attention is computing the following. So it's computing the softmax of the query multiplied by the transpose of the keys divided by some normalization factor, multiply that by v, and so that's what it's going to compute, and it's going to compute it this way. First of all, there is an outer loop through the queries, which corresponds to the same pseudocode that we have seen before, because we want to compute each block of the output matrix in parallel with respect to the others. So basically we want to compute this output block and this output block independently. This output block here depends on the query 1 and all the keys. This output block here depends on the query 2 and all the keys. This output block here depends on the query 3 and all the keys, where query 1 is not the first query, but it's the first group of queries or first block of queries. Query 2 is not the first, query 2 is not the second row of the query metric, but it's the second block of the query matrix, etc., etc. So that's why we have this outer iteration among all the blocks, because we want to compute all those blocks of the output matrix in parallel. But to compute each of these output block, we need to go to an iteration among all the keys. That's why we have an inner loop on the keys, and we do exactly the same operation that we have done so far by hand. So first we compute the S matrix, which is what? Each block of query with the corresponding block of the keys. Then we compute the local maximum to the current S block. This is the local maximum, and we compare it with the maximum of the previous iteration, because that's what we do in the online softmax. Then we compute the P block, which is the softmax star of the S block, minus the local maximum of the S block. Then we compute the normalization factor. What is the normalization factor? It is the summation of all the exponential of the softmax star, but by fixing the normalization factor of the previous step, and we know how to fix the normalization factor because we just multiply by an exponential, which is the previous maximum minus the current maximum. That's what this factor is. And then we compute the output exactly using the same correction factor that we have seen before, which is the diagonal matrix made up of the diagonal, where on the diagonal you have the elements of this vector here, which is the exponential of the previous maximum minus the current maximum, multiplied by the output of the previous step, because we want to fix the previous step because it was based on the previous P, which was using the maximum of the local previous P, plus the current PV, which is based on the current local maximum, and it will be fixed by the next iteration. Okay, and at the end, after we have gone through all the Ks, so we have computed all the output block, but we didn't apply the normalization factor, and it's applied at the end because while going through each key, we are calculating the L normalization factor for the softmax, because inside of this for loop, we are just computing the softmax star, so we are not normalizing each value. So at the end, someone has to normalize it, and it will be this instruction here, which is use the normalization factor that we have computed over all the iterations and apply it to each element of O, because the difference between the softmax star and the actual softmax is just the division by the normalization factor. And this instruction here is actually dividing each O with the corresponding normalization factor, one for each row of the block, each row in the output block that we are computing. Later we will see also what do we do, what is this SRAM, what is the HBM. For now I just want you to concentrate on the operations that we are doing, and they are exactly the same operations that we have done so far. Later we will see also why do we need to save this stuff here, and etc, etc. But for now you should have enough knowledge to be able to follow what is written in the flash attention paper with respect to the forward pass algorithm. And what we are doing basically is just block matrix multiplication, and while computing this block we fix the previous block by using tricks of the exponential. Alright, now that we have seen forward pass of the flash attention, before we can implement it, we still lack a little bit of knowledge, because we don't know anything about the GPUs, and we don't know anything about CUDA, and we don't know anything about Triton, so that's what we are going to see next. Alright guys, it's time for us to explore finally the GPU and the CUDA programming model. Well, let's start by comparing the CPU and the GPU, and this will let us understand how CUDA works then. So first of all, what is the CUDA and what is the GPU? The GPU is the hardware unit that we buy, and CUDA is a software stack made by NVIDIA to write software for this GPU that they sell. AMD has its own software stack, and other manufacturers have their own. In this particular video, we will be seeing example of CUDA kernels, but the knowledge that you will get can apply also to other GPUs. Now, the first difference between a CPU and a GPU is its purpose. Your computer is right now running on a CPU, and your operating system is interfacing with the CPU using the so-called scheduler. So right now, probably you are running a browser. You are also running some other software on your computer, and the scheduler is tasked with switching between them very fast on your CPU in such a way that it looks like to you that the processes are running concurrently. This actually is a fake kind of parallelism, unless your CPU also has multiple cores, which nowadays CPUs do have. So a CPU usually has one or multiple cores, but not so many of them. So you usually have dual core or quad core or 8 core CPU, and each of these cores can execute instructions in parallel. The CPU is tasked, the main purpose of the CPU is to execute many different tasks and switching between them very fast. So maybe you have a browser that is running a small game, and then you have another movie player, but then you have a word processor, and then you maybe have some utility to manage your, to download files, etc. So most of these programs actually are not compute intensive, are actually IO bound, meaning that most of the time they are either waiting for the network or they are waiting for the disk. And they are very different from each other in the purpose. So the browser is completely different from a movie player, and it's completely different from a word processor. So the job of the CPU is to actually reduce the latencies of processing all these operations, and it's highly optimized to optimize each of these execution units called the cores. Which means that each core has a part that is tasked to understand, first of all, what is the next instruction to run, or to predict the branch of how what the next operation may be based on the conditions that you are running. For example, if you have a if condition, the branch predictor can understand what is the most likely next instruction, and can do some optimizations. Also, the CPU has a lot of caches to reduce the latencies in loading data from all the devices it can interface with. It can interface with the RAM for sure, but it can also interface with the disk. It can also interface with some peripherals like the printer, like the mouse, like the keyboard, etc., etc. On the other hand, the GPU is not tasked to do many different things at the same time, but it's tasked to do one thing or few things, but on a massive amount of data. So the operations that we do on the GPU are requires a lot of computation, and for this reason, most of the area, so the physical area of the GPU, is dedicated to compute units. So this green stuff that you can see here, and these are called cores. And you can see that the part that is dedicated to the control area, so the part that is tasked with understanding what is the next instruction to run or to do some optimization in the program, is very little. You may be thinking, well, does it make the GPU less fast compared to the GPU to the CPU? Well, not really, because we have many more cores that can compensate for this higher latencies. Okay, I can give you a lot of knowledge about the GPU from a theoretical point of view. I think the best way to understand the CUDA programming model is just to jump into the code, so we don't get bored. Okay, imagine we have a very simple task, and we have a vector. We have two vectors, A and B, and we want to calculate the sum of these two vectors and save the result into another vector, C, where each item is the element-wise sum of the corresponding item of A and B. How would you proceed with this task on the CPU? Well, you would do a for loop, for example. So, for example, you would make a for loop that starts from the first index, so the index is 0, and C of 0 is equal to A of 0 plus B of 0. Then C of 1 is equal to A of 1 plus B of 1, etc. And you do a for loop on all the elements of this vector. In the GPU, we want to do the same operation, but in parallel, because we have a lot of compute units called cores, and we want all of them to work in parallel. So the first thing that we need to understand is how to divide the work that we are going to do into sub-units of work and dedicate each core to one subunit. One simple subdivision would be, okay, the first core should do this summation, the second core should do this summation, the third core should do this summation, etc., etc. So imagine we have a 8-element vector. We need 8 cores to do this element-wise summation. We will call the cores threads, because it should also remind you of the multi-threading that we already use in operating systems. So multiple threads work concurrently on the same or similar job in the GPU. Let's look at the code. Now, the code that I am going to show you is a CUDA kernel, and it's written in C, but you don't have to understand C, and you don't have to understand this code. What I want you to understand is the intuition behind it, because later we will need this knowledge and convert it into Triton, which is Python, and you should already be familiar with Python. So, let's go to the code, and I have a very simple vector addition. We can see it here. Okay. First of all, how to do a vector summation. Usually the GPU is interfaced with a CPU, and the CPU has to first of all tell the GPU what is the data it is going to work with. So the CPU needs to have these vectors, it needs to transfer them to the GPU, then the GPU needs to do this vector summation, then the CPU has to copy back the information from the output from the GPU to the CPU, and then make it available to the program. This is what we are going to do here. So we are going to allocate 3 vectors of size n one called A, one called B, and one is the output vector. We initialize their items randomly, so the A of I is a random number between 0 and 100 excluded. Then we allocate memory on the GPU to hold these vectors, and then we copy them to the GPU. So we copy the A vector to the GPU and the B vector to the GPU. Of course, we don't copy the result because that's what we want the GPU to populate with the output. So we just allocate it on the GPU, but we don't copy our output vector on the GPU because it's made of random values. Then what we do is we launch the kernel. Launching the kernel means that we launch a program that the GPU should execute in parallel on multiple threads or multiple cores. Each of these threads should do a unit of operation, a unit of work that is independent from the others. Actually, they can be dependent on the others, but we will not be talking about synchronization. So we launch this kernel, and what we are saying in this line is launch one block of threads, and later we will see what are blocks, but you can ignore this one for now. What we are saying here is launch n threads, so n parallel operations with the following arguments. So the output where we want to save data, the input array A, and the input B, and the number of elements. Let's see what happens inside of this method. This method is following a particular syntax that is how to say, CUDA specific. So this global is actually added, it's like a superset of the C language where we have some additional keywords that belong to CUDA. So it's not really C, it's CUDA C. So it's a very simple method, as you can see, and the first thing that we need to do is CUDA cannot know what each thread should do. We should tell each thread what to do. So the mapping between the data and what each thread should do, it's up to us as software engineer. CUDA, what we'll do is when we ask it to launch n threads in parallel, it will allocate n threads and assign a unique identifier to each of these threads. In our simple case, we can see it like this. So it will assign the first thread the index 0. So we are asking, for example, imagine we have a vector of 8 elements. It will assign the first thread index 0. Here I call it 1, but it's wrong, but we can write another number here. So this will be actually thread 0, this will be thread 1, this will be thread 2, thread 3, thread 4, thread 5, thread 6, and thread 7. So let me delete this one so we don't get confused. And what we are saying is that the item that each thread should process is equal to its thread index. So this is the thread 0, so it should process the item with index 0. This is the thread 1, and it should process the item with index 1. This is the thread number 2, and it should process the item with index 2. And this is what we are doing in this line of code. We are saying which item each thread should process, which is exactly the thread identifier, so the thread ID. Later we will see why do we have this .x, but that's for later. Next thing that you should see is, okay, we are doing the output of the ith position is equal to the a vector at the ith position plus the b vector at the ith position. So it's a very simple summation element-wise. You may have noticed this if statement. Why do we need an if statement if we already know that we are going to launch 8 threads? And of course, I will be between, we already know that we are going to launch n threads, so I should of course be less than n, because each thread ID will be between 0 and n minus 1. So why do we need this if condition? This is needed because when you, CUDA, when it launches a number of threads, this number of threads is always a multiple of a unit, which is a 32 in the case of the CUDA. So if we have like 34 elements in a vector, and we ask CUDA to launch 34 threads, CUDA will not launch 34 exactly, it will launch 64 threads, so a multiple of 32, which is the warp size, by the way. What we need to do is we need to ask these threads, to only work we only need to ask the threads that have a corresponding element to work, and all the other that don't have a corresponding element, because the vector is not large enough for all of them, to not do anything. So do not enter this if statement. There is another thing that we should learn, which is actually the threads. Actually, when we have a group of threads in a CUDA programming model, but I believe also in other GPUs, a group of threads, of 32 threads, is called a warp, and these 32 threads will share the same control unit. So let's go back to the slide. So as you can see here, we have this yellow unit here in the GPU. And a group of threads will share the same control unit, which means that, what is this control unit? It's a part of the hardware of the GPU that is tasked with understanding what is the next instruction to run. Now, if the group of threads is sharing the same unit, it means that this group of threads will always execute the same statement at any time. They will always work in synchrony, will always work on the same instruction. It cannot be like this thread is working on one instruction and this one is working on another instruction. What does this mean on a programming level? It means that when we launch a group of threads, of course, CUDA will spawn more threads than we need if the number of elements of our vector is not a multiple of 32. This means that when this thread, they will first execute this operation, and each of them will have its own value of this thread ID. So they will execute the same instruction, but the data at each instruction may be different because each of them have their own registers, which means that they will always, for example, reach this statement here, and the first thread will have I equal to 0, the second thread will have I equal to 1, etc., even if they are executing the same instruction. This programming model is called single instruction multiple data. CUDA likes to call it single instruction multiple thread, doesn't matter for us. It just means that they will always execute the same instruction, but the value of the variables may be different. Then, after executing this statement, they will reach this statement here, the if statement. And of course, some of them will evaluate this statement to true, and some of them will execute the statement to false. Which also means that some of them should enter this if statement, and some of them should not enter this if statement. However, because the control unit is the same for all of them, they will be forced to enter this if statement, even if they should not. So how CUDA manages this control divergence? It will basically work like this. All the threads for which this if statement is equal to true will enter this if and will execute the instructions inside of this if. And all the threads that have this statement equal to false, so the condition of this if equal to false, they will enter the for loop because they cannot not enter it, because they should be always executing the same instruction at any time. But they will just not do any operations inside of this for loop. They will just sit idle. This is called the control divergence, and it can reduce the throughput of your program. So you want to minimize it. But you may be wondering, why doesn't the GPU dedicate a control unit to each core so that they can work independently from each other? Because the control unit is expensive to add in the chip area of the GPU. It's much more efficient to add more workers instead of adding a control units for each worker. So this is a design choice of the GPU, and it works fine. Okay, now that we have seen how a kernel works, let's move forward to another example. All right, the next example that we are going to see is the following. It's the same as before, so we are going to do a vector addition, but imagine that we have a very large vector. So imagine that we have a vector with 1 million elements. Of course, we could do like before, so we launch a kernel with 1 million threads. The problem is CUDA will reject it because I don't have 1 million threads to run in parallel. So how can we proceed in this case? Because usually we are working with very big matrices or with very big vectors, so we need to process a massive amount of data. So how to manage a parallel parallel computation when we do not have enough computation cores? One way is to divide the input vector into blocks of elements. For example, we may decide, for example, imagine our GPU only has 32 cores in total, we may divide our input vector into blocks of size 32, such that the first 32 elements are the first block, the next 32 elements are the second block, the third 32 element the third block, and the last 32 elements are the last block. In this way, we can ask the GPU to work on one block at a time. So we can say, okay, work on the first block, and after it has processed the first block, it can work on the second block, and then the third block, and the fourth block. This also allows the GPU itself to manage a subunit of work, because imagine now we have blocks of 32 elements, but we have a GPU of 64 cores. The GPU can also schedule 2 blocks at the same time because it has enough cores. So we need to give some granularity. We need to reduce increase the granularity of our data to let the GPU decide how many blocks to schedule. This is the reason we introduce blocks inside of CUDA. So let me make a concrete example, but with a very simple assumption. Imagine our GPU only has 2 cores, or let's say 4 cores actually. So we have n is equal to 8 elements, 8, and we have 4 cores in total. So what we can do, for example, is divide this vector into groups of either 4 cores or even less. Let's say two elements at a time. So this is the block number 1, this is the block number 2, this is the block number 3, and this is the block number 4. We can ask CUDA to launch a kernel that is made up of 4 blocks and where each block is made up of 2 threads. So when we launch the CUDA kernel, we can show the code now. We ask the CUDA, where is the instruction? This first instruction tells CUDA how many blocks we have, and the second part of this in this symbols tells how many threads we have for each block. In our case, we want n divided by the block size number of blocks, where the block size in my picture is 2. So how many blocks we will have? We will have a number of blocks. So the number of blocks is n divided by 2, where 2 is the block size. So this is the block size. And this will be equal to 4 blocks, each of size equal to 2. And this is what we are doing here. So we are saying that the number of blocks is, okay, the ceiling, because it may not be a multiple of the block size n, of n divided by the block size, and this tells how many blocks we have, and this will define our grid. It means the grid is basically telling how many blocks we have, and then each block is made up of block size number of threads. Then the problem is, how do we assign the work to do to each of these threads? When we launch a kernel like this, with this configuration, so the number of blocks and the number of threads per block, CUDA will do the following job. It will assign this block, each block an index called the block ID, where the block ID of the first block is 0. So let me write here. So this will have, the first block will have a block ID equal to 0. And in each block, it will assign a thread ID. And the thread ID of the first thread of each block will be the thread 0, and the second thread will be the thread number 1. The second block will have a block ID equal to 1, and the first thread of this block will be the thread number 0, and the second thread of this block will be the thread number 1. The third block will have a block ID equal to 2, and the first thread will be the thread number 0, and the second thread will be thread number 1, etc. until the last block, which will be equal to 3. This will be thread number 0 and thread number 1. The problem is now, based only on the index of the block and the index of the thread, how can we map it to what element of the vector each thread should work with? One simple assignment would be to just do well, you can see that in this case we need the this vector, this thread here to work with the element 0. This one should work with the element 1. This one should work with the element number 2. This one to the element number 3. This one 4. This one 5, 6, and 7. This 5 is so ugly, so let me write it again. How can we find the mapping given only the block ID and the thread ID? How can we find which element it should correspond to? Well, it's very simple formula. So you can see that the element, let's call it the element ID, which in the code I call it I, is equal to the block ID multiplied by the size of each block, which is block size, let's call it. Block size, yeah, I have it, block size, plus the thread ID. Because in the case of the first thread, this will be equal to 0 multiplied by 2 plus 0, which is 0. In this case, it will be equal to 0 multiplied by 2, which is 0, plus 1, and it will be equal to 1. In this case, it will be equal to 1, because block ID is equal to 1. 1 multiplied by 2 is equal to 2, plus 0 is equal to 2, etc., etc. And you can see that this formula works for all the threads. So the mapping, when we launch a CUDA kernel, we are telling the GPU how many blocks we want and how many threads there are in each block. But CUDA has no notion of how to map each. CUDA has no way of knowing how to map each thread into the element it should work with. That's up to us. And that's what we are doing here when we are creating this kernel here. So we are telling that each element, each thread should work with the ith element of the vector, where I is calculated as follows: the block ID to which this thread belongs multiplied by the block size, so how many threads there are in each block, plus the thread ID. And this will tell the ith element this particular thread should work with. By giving, let's go back to the slides. By choosing the block size equal to 2 and having 4 cores, the GPU can choose to run 1 block or 2 blocks concurrently if it has enough free cores. So that's why we want to work with by block, because it allows the GPU to choose how it wants to parallelize the operations if it has enough cores. And we don't need to have n cores for n element vector. We can divide it into smaller blocks and let the GPU manage the scheduling. Let's see one last example and then we move on to Triton. Imagine now we want to do a matrix addition instead of doing a vector addition. Now, in a matrix addition, we have data that we can see on 2 axes. One is the rows and one is the columns. It's usually, we represent the vertical axis as the y-axis and the horizontal axis as the x-axis. By using the same blocked intuition that we used before, so dividing the data, input data into blocks, this is how we can divide the labor of our matrix addition into blocks. For example, we can divide our rows into blocks and call this one the block 0 and this one and the block 1 and this one is the block 2. The same we can do on the x-axis. So we can choose this one as the block 0, this one as the block 1 and this one as the block 2 on the x-axis, with the x is the column axis and the y is the row axis. We don't even have to choose the same block size for the rows and the columns. We can even choose to group together 3 columns and 2 rows instead of doing 2 and 2 in this case. We need to find, because as we said before, when we launch a CUDA kernel, CUDA will just assign IDs to the blocks and the threads in each block. Then it's up to us understanding how to map the ID of the block and its corresponding thread ID into the data element that this particular thread should work with. So in the case of matrix addition, we could say that each thread should work with one output element of the output matrix C. So it will become the sum of the A element plus the B element, and it should map it to the C matrix output matrix. So how to do it? Imagine we have 6 rows and we have 6 columns. One easy way would be to divide these rows into 3 blocks, each made up of 2 rows, and each column into 3 blocks, each block made up of 2 columns. CUDA will launch as many blocks as there are the combinations of the rows and column blocks. So in this case we have 3 blocks for the columns and 3 blocks for the rows. So it will launch 9 blocks. So this is the block number 00 because it's CUDA will identify the dimensions of the block based on the axis in which we have divided it. So we will call this the X dimension, the columns, and the rows we will call it the Y dimension. So it will launch as many blocks as there are combinations of X and Y's. In this case we have 9. So this will be the block 00, this will be the block 01, this will be the block 02, this one will be the block 10, 11, and 12, etc, etc. Inside of each block we will also divide the threads into X threads and Y threads along the 2 dimensions. So this will be the thread 0 and the thread 1 along the X axis in the X block, and this will be the thread 0 and the thread 1 in the Y in the block 0 of the Y axis. And each block will have 2 threads, and they will be identified as thread 0 and the thread 1. So let's look at how the launch grid works in this case. So imagine we have a matrix with num rows, number of rows, and num cols, number of columns, and we want to divide each row, the rows into block size number of rows and the cols block size number of columns. We define basically the number of blocks that we need is this one. So this is just a fancy way of writing the ceiling of the num rows divided by the rows block size, and this is just a fancy way of writing the ceiling of the number of columns divided by the cols block size. This tells us how many blocks we will have on the rows and how many we will have on the columns. The grid you can see here, which tells us how many blocks we have, is a tuple that accepts 3 values, which tells how many blocks we want on the X dimension, how many we want on the Y dimension, and how many we want on the Z dimension. We are not going to use the Z dimension because we only have a matrix. Then inside of each block, how many threads we want for the X dimension and for the Y dimension. As the X dimension, we have chosen the columns, so we are saying how many blocks we want the columns and how many blocks we want for the rows. And then inside of each block, how many threads we want for the column block and how many threads we want for the row block. This will define our launch grid, and what CUDA will do, it will just launch this following configuration. So it will launch as many blocks as there are combinations of X and Y's, and inside of each X and Y, it will assign a thread ID in such a way that the thread 0 on the X-axis, so there will be 2 threads on the X-axis and 2 threads on the Y-axis of each block. Now let's try to understand how to map, just based on the block ID on the X-axis, just based on the block ID on the Y-axis, and the thread ID on the X and Y-axis, how to map it to the one element of the output matrix. Let's look at the code. So first we can use the following formula to identify which row this element should work with, because each element of a matrix is identified by 2 indices. One is the row identifier and one is the column identifier. The row identifier, we can look at it like the block ID multiplied by the block size plus the thread ID. Let's see why it makes sense. So in this case, for example, this thread will work with the row 0 because the block ID is on the y-axis is 0 and the thread ID is 0, so it's a block ID multiplied by the block size, so 0 plus 0, it will be 0. So this element will be working with the row number 0. And which column it will be working with? Well, it will be working with the block ID 0 multiplied by the block size on the column, which is again 0. I mean, the block size is 2, but multiplied by 0, it will be 0, plus the thread 0, so it will be 0. This element here, it will be the block ID of the y-axis multiplied by the block size plus the thread. So it will be the element 0 on the row, and for the columns it will be the element 1. Let's see another one, for example here. For example, this element here. So this, how this thread will, which element it will be work with? Well, it will be the block size on the y-axis multiplied by the block ID on the y-axis multiplied by the block size. So it will be 1 multiplied by 2. So that will be our row. So the row number 2, which makes sense because it's the this is the row 0, this is the row 1, and this is the row 2. And the column will be the block ID on the x-axis, which in this case is equal to 1 multiplied by the block size, which is equal to 2. So 2 plus 1 is equal to 3. So this thread here will work with the element number 2, 3. And this formula now makes sense. So this is how we use the block ID and the thread ID inside of each block to map it to which element this particular thread should work with. So as I said before, CUDA has no notion of knowing which element this particular thread should work with. This is up to us just based on the block ID and the thread ID that CUDA assigns. Then we make sure that the row index is less than the number of rows and the column index is less than the number of columns. Why? Because as I said before, when we launch blocks and threads, CUDA will round up that number to a multiple of 32 in the case of the threads. So, which means that some of these threads should not work with any data. So we make sure that all the threads that should not have the corresponding element to work with, they should be just sit idle inside of this if statement. But the one that have it, they should go enter and do some job. So we calculate the index of the element of the matrix that this particular thread should work with as follows, which is the row index multiplied by the number of columns plus the column index. This is just another way of writing or for example, this is just another way of writing A of row index call index. But the way we allocate arrays in C or C++ is a flattened array where all the rows are one after another. So we need to identify the element inside of the array based on its row index and column index. And this is the formula that we use to identify it. If you have never worked with arrays in C++ or C, then it doesn't matter because later we will see tensor layouts and this will be much more clear. But if you have already worked with, then you already know how to index an element inside of a multidimensional array in C++. And then we compute the output as usual. So I know that this has been a lot of information. So what should we remember from this? The first thing that we should remember is that we decide how to divide the work on whatever matrix we are working with or whatever thread we are working, whatever vector we are working with. We tell CUDA how many blocks we want and we tell CUDA how many threads we want in each block. Based on the identifier of the block ID and the thread ID, we should come up with a strategy on how to map it to a subunit of work. So which part of the matrix or which part of the vector that particular thread should work with. Now the next step for us is to understand the tensor layouts because we are going to work with the tensors and we need to understand how the tensors are laid out in the memory of the GPU or in the CPU as well actually. So we need to understand what is the row major layout and the column major layout, what is the stride, etc. and convert all the knowledge that we have about CUDA into Triton so that we can then code with Triton our kernel. So let's go. Alright guys, finally it's time for us to explore tensor layouts. Now, why do we need to explore tensor layouts? Because before we have seen some examples of CUDA kernels, and when you give a matrix to CUDA or to a CUDA kernel or a vector to a CUDA kernel, CUDA will not give you the entire matrix like in Python where you can access each element by its index. CUDA will just give you a pointer to the starting element of that particular matrix or the starting element of that particular vector. Then it's up to you to calculate the memory address of all the remaining elements. So suppose that we have a simple vector. In PyTorch, this simple vector could be the following, which is a vector of shape 7, because it's a tensor with only one dimension, with shape 7, which is the number of elements in the first dimension. For now, ignore this property called the stride, and later I will explain it. What is it? How this tensor will be saved in the memory of the CPU or in the GPU. It will be saved as follows. Suppose that the starting address of the first element is the address 100, and suppose that each element is made up of a floating point of 16 bits. So it means that each element will occupy 2 bytes. So the start address of the second element will be the address 102, and the third element will be 104, and the fourth element will be 106, etc, etc, etc. So this is exactly what you get when you in C you get you allocate a vector or a matrix with malloc. So when you allocate in C a vector or a memory with malloc, C or the memory allocator will just allocate enough memory to store all the elements, and it will give you a pointer to the start address of this memory. Then it's up to you to understand where each of these elements is stored in that block of memory. And this is, to do this, we introduce a property called stride. The stride tells us how many elements we need to skip to arrive to the next element in the particular dimension. In this case, for example, in the case of a vector, we only have one dimension, which is the x dimension. Or the columns dimension, you can think of it. So this is the first column, this is the second, the third, the fourth, fifth, etc, etc. So in order to arrive from one element to the next, we just need to skip one element. So to go from here, we need to just increase our pointer by one element, and then to go here, we need to increase again pointer by one element, etc. This allows us to do a for loop on this tensor. Let's look at a more complicated case, like the matrix. So the matrix is two-dimensional. And suppose we have the following matrix, which is made up of 6 elements with 2 rows and 3 columns. So the shape of this tensor will be 2 by 3, because we have 2 rows and 3 columns. How this matrix will be saved in the memory? In the memory, it will be just a flattened matrix. It means, and this is called the row major layout, but there is also another one called column major layout that we will not be discussing. So how it will be stored in the memory is as follows. It will be the first elements of the first row. So the elements of the first row followed immediately by the elements of the second row. So that the memory address, imagine this is the memory address of the first element is 62. To go to the next element, we need to increase the memory address by the number of bytes that each element occupies, which is 2 bytes. So the address of the second element will be 64, the third element will be 66, and the next row will start immediately after the end of the first row. Let's introduce this property stride. So the stride is what? The stride tells us how many elements you need to skip in each dimension to arrive to the next element of that dimension. For example, imagine we want to we want to get the element, so all the elements of the first row. So let's call this tensor here, let's call it T. So T of 0 and this basically, this indexing here says, give me all the elements of the first row. So in the first row, select only the first row and give me all the elements of that row. How does this indexing work? Well, by starting from the pointer to the first element, it will select only the first row, and then it will move the index here one element after another. So it will select the first one, the second one, the third one. How does it know that it needs to move one element by one element? Because in this dimension the stride is 1. So the stride tells us how many elements you need to skip to arrive to the next element in that dimension. Imagine now that we want to get the T of, let's say, 0 and 1. Well, in this case, let's say T of 1 actually, and all the elements of the first row. It will, first of all, it needs to skip some elements from the first dimension. It needs to skip the element 0 because we are not selecting it. We only want to select the element 1 of the first dimension, which basically means the row with index 1. So because it will start from the first pointer to the first element, it needs to know how many elements to skip, and how many elements to skip is given by the stride. So the stride tells us how many elements you need to skip to arrive to the next element of the first dimension. So in this case, it will take the pointer to the first element, skip 3 elements, and it will be starting with the second row, and then inside this row it will go through the second in the index of the second dimension, in which the stride is 1, so it will just go one after another, and it will return only this part of the memory. So to rehearse, the stride is just a number that tells us how many elements you need to skip in each dimension to arrive to the next index in that dimension. So it means that to go from one row to the other, we need to skip 3 elements. To go from one column to the other, we need to skip 1 element. Why is the stride useful? Well, the stride is useful because it allows us to reshape tensors very easily and without doing any computation. Let's see. Okay, imagine we want to reshape a matrix. Imagine initially the shape of this matrix is 2 by 3, so we have a 2 row by 3 columns, and we have a stride calculated as follows. It means that to go from one row to the other, you need to skip 3 elements, and to go from one row to the other, you need to skip 3 elements, and to go from one column to the next, you need to skip 1 element. So you need to jump by 1 element. If we want to reshape it into this shape, so 3 by 2, basically we want to have 3 rows and 2 columns, we can reshape it without actually changing its memory layout, just by changing the stride. Because look at this physical configuration of the tensor, and we can access this same tensor as this shape or as this shape exactly by using the same physical view. Because to go from one row to the next, here, the stride is 3, so we need to skip 3 elements. It means that the starting address, the starting element of the second row, is given by the start pointer plus 3 elements, so exactly here, the second row will start. And each element of the second row is one after another, because the stride of the second dimension is 1. So you can see that to get the second row, we can just start from here and then go one after another and get all these elements, which is exactly the second row. Suppose we want to obtain the second row of this view here, of this shape, of this reshaped matrix. How to do that? Let's look at the stride. The stride now is 2. In the row, it means that to go from one row to the next, we need to skip 2 elements. So if we want to select this row here, we go from the starting point of the memory, so this start pointer, we skip the first 2 elements, because the stride says that to go from one row to the next, you need to skip 2 elements. So we arrive here, and then we select exactly 2 elements, which are one after another, because the stride in the second dimension is 1. So the stride allows us to reshape the tensor without changing the physical layout on how it is stored in the memory. Moreover, the stride also allows us to get the transpose of a matrix without changing the shape of how it is stored in the memory. So without changing the arrangement of the elements in the memory. And this is very cool, because we can view the same matrix as without the transpose, and also the transpose version of the matrix without changing anything in the memory. So it comes for free just by working with the index and the stride. So to transpose the matrix along 2 dimensions, we just need to swap the stride along these 2 dimensions that we want to transpose. So in this case, for example, imagine we want to get the transpose of this matrix. We just need to swap the strides. So if we want to get the second row of the transpose matrix, how to get that? Well, we always have the pointer to the first element where the tensor is stored, so at the beginning of where the tensor is stored in the memory. And it says that in order to go from one row to the next, we need to skip 1 element, which is correct, because as you can see, the second element is exactly the second element also in the memory. So we just skip by 1, and we get the starting point of the second row. And then to go from one element to the next within the same row, we need to skip 3 elements. So the second element of the second row will be after 3 elements after the first element of the second row. So after 2, we need to skip 3 elements. So we skip this one, we skip this one, and we arrive to this one, 8, which is exactly the second column of the second row. So basically, the stride, as you can see, allow us to do two things. One is it allow us to reshape the tensor without having to reallocate it in another configuration in the memory. Secondly, it allows us to transpose a matrix without having to rearrange the elements in the memory, which is great because moving memory around is expensive. And rearranging the memory is expensive, so it's great that this stuff comes for free, basically. Another thing, okay, for example, if you try to, you know that in PyTorch there are two methods to reshape a tensor. One is called the reshape method and one is called the view method. After transposing a matrix by swapping the stride of the two dimensions that you want to transpose, you cannot reshape for free the tensor anymore. Because the tensor, basically, what is the stride? The stride, how it is computed. The stride is just the, let me show you with a concrete example. The stride is just the product of all the shape after in the future dimensions. So the stride of the 0th dimension is just the product of the elements in the shape of the future dimension. So the stride of 0 is just the product of all the shape starting from the index number 1. It's not easy to see with the 2D matrix because we don't have enough elements, so let's do it with the 3D matrix. So this is a tensor with the 3 dimensions, so it is a shape of 2, 4, 3, which means that we have 2 matrices. Each matrix is made up of 4 rows and and 3 columns. The stride is calculated as follows. So the 0th dimension stride is just the product of 4 by 3. And this 3 here comes with the product of just a 3 with 1, because we don't have any future dimension of the 3. So when we transpose, this stride property is lost, and we cannot, after transposing this matrix by swapping the strides, we cannot do further reshaping operations. So basically the tensor is not log contiguous. So this is a very advanced property. It doesn't matter if you know it or not, but if you are curious, basically in PyTorch you cannot view a tensor after it has been transposed, because PyTorch to transpose a tensor will just swap the 2 strides, but it loses the stride property, which is basically the stride will not be anymore the product of the future shapes. So this is not anymore 2, this should be 2, for example, and this should be 1. But after transposing, this property is lost, so you need to actually reallocate the tensor if you want to reshape it after it has been transposed. Doesn't matter if you remember this, it's just a curiosity. Anyway, so what is the stride used for? The stride is used for 2 things. First of all, it is used to understand how to index this tensor. So just by having a pointer to the starting address of this tensor, we can index this tensor however we like, so we can access any row, any column. Moreover, it allows us to reshape this tensor for free, so without rearranging the elements inside the memory. And third, it allows us to transpose the tensor however we like, just by swapping the strides of the 2 dimensions that we want to transpose. Now that we have seen also how the tensor is stored in the memory, we can finally go to see Triton and see some examples. Alright guys, now that we have seen how tensors work, tensor layout works, how CUDA works, now we can see some examples of Triton kernels to see how Triton differs from CUDA. Now, if you go on the Triton website, you will find some tutorials, like in this section here. And let's work one tutorial together to understand how Triton is different from CUDA. So if you go to the tutorial, there are many examples. So first of all, the code that I will be coding for flash attention is based on this tutorial here, fused attention, that you can see here, but with some modifications because I simplified the code a lot. I removed, for example, the FP8 implementation. I also, for example, this code here on the fused attention only works in the backward pass only for the causal attention, while my code will work for the causal and non-causal attention. Another modification I did is, instead of using the exponential 2 that they use here to make things faster, probably because the exponential 2 is implemented with a faster unit, I use the original implementation of flash attention, which used the exponential with the base e, etc., etc. So I simplified my code as much as possible to make it simple to follow instead of making it optimized. So for sure my code will be slower than the fused attention that you see here, but mine should be more comprehensible, more easy to follow. Anyway, let's go to the vector addition tutorial. And if you go to the vector addition tutorial, there are some examples on how to do a vector addition with Triton. This should allow you to get into the mindset of how to write kernels with Triton. Instead of writing first the kernel and then calling it, let's do the opposite. So let's see how to call this kernel and let's explore how it works. So I have already copied the tutorial vector addition from the website. So let's look at, first of all, what we want to achieve. We have an input vector x and an input vector y, and we want to compute the vector addition, which means that with the torch we want to do the following operation, and also we want to do the same operation also with the Triton by calling this method add. And then we want to compare the two vectors output, and they should be equal, or at least their difference should be very, very small, because of course there is always some rounding error in case you are working with floating point numbers. The size of this vector is 98,000 elements. And we want to work in a blocked way. So as you remember before with the CUDA, you can do vector addition by spawning a lot of number of threads, each doing one operation. But when the number of threads that you have is not enough, then you need to divide the input vector into blocks. And this is what we are going to do here. So let's look at this add method. So this add method basically will first of all allocate the necessary memory for the output vector. Then it will compute the launch grid. The launch grid tells Triton, just like in CUDA, how many kernels we want to, how many blocks we want to launch, how many blocks of threads we want to launch. If you remember, in the CUDA kernel, we specify how many blocks we want and then how many threads we want for each block. In the case of Triton, we tell how many blocks we want, and then we don't force how many threads to launch. It will be Triton that will choose how many threads to launch. We just tell what each group of threads should do. So in this case, for example, we divide our number of elements, so n, so which is 98,000, into blocks of size block size, which is initialized as 1024. This is basically saying to calculate the grid size, you do the ceiling division. So basically this means ceiling of ceil of n elements divided by block size. This is the meaning of this one. So how many blocks we want. Now, what each block should do is inside of the kernel. So let's go to the kernel, and when we launch the kernel, we can specify that the launch grid in this square parentheses, and then in the round parentheses we specify the arguments of this kernel. So let's go to the kernel. We see that Triton will not give us access to the tensor x. It will give us a pointer to the first element of this tensor, and this takes us back to the tensor layouts. So the reason we studied the tensor layouts and the strides and all the stuff is because Triton, this code, this add kernel will run on the GPU, and the GPU does not index tensors like PyTorch by using all the dimension and with the broadcasting and all this fancy stuff. The GPU will just give you the pointer to the first element of this tensor in the memory, and then it's up to you to compute all the indexes of all the elements that you want to access. So this xptr is the pointer to the first element of the x vector. This y pointer is the pointer to the first element of the y vector. Then we have the pointer to the output vector where we want to store the result of this matrix addition. We specify how many elements our vectors have and what is the block size, so how many items each block should process, which may not correspond to how many threads each kernel will have. You may be confused because, in Triton, in CUDA, we specified how many threads each block should have. So the granularity that we manage is the thread level. Here we are saying it's a group of threads that should work with this quantity of data. then it's up to Triton to optimize the number of threads that it will actually use. Actually, there are tricks, there are ways to say how many threads we actually want by specifying the number of words, but we will see that later. For now, just remember that this thread, this kernel here, will process a number of elements in the input vectors. How many elements? Block size number of elements. First of all, we need to identify which block we are. In CUDA, we use the variable called block id.x to identify the identifier of the block, which tells us which group of elements we should be working with. In Triton, you do the same by using program id. And in CUDA, the block ID can be along the X, Y, and the Z axis. In Triton, these are called the dimension 0, 1, and 2. Here we have one-dimensional data, so we only use one axis to specify the block index. So we get the block index, which is the PID. In Triton, this is called the program ID. It's more intuitive to think of it as the program, like this is a kind of a program that is running in parallel with other programs that will have different program ID. And based on the program ID, we can understand what is the starting element this program should work with. So this blue block of threads should work with. And to get that is just the PID multiplied by the block size. So the PID 0 should be working with the element that starts from the element 0. The PID 1 should start with the element 1024. And the PID 2 should start from the element 2048. So it should skip the first 2048 elements and start with the element with index 2048. Next, we define how to load these elements based on the pointer in which of the X and the Y vector. To do that, we specify a list of offsets with respect to the starting address that we want to load. So because each program in Triton works with a group of data, so not one single element, but a block of elements, we need to understand which elements to load. So the offset of these elements. In the case of the program ID 0, it will load the block start, so 0, plus the elements from index 0 to 1024 excluded. With the program element 1, this basically will result in a vector that is well, the program start with PID equal to 1 will be 1024, then 1025, 1026, 1027, etc., until 2047. With the program number, let's say 2, this offsets will be the elements 2048, 2049, blah blah blah, until 3000 and something. Now we also, as you remember, when we create, when we launch a grid, the number of threads is not always based on the number of elements in the block or the number of elements in your vector. It is always a multiple of a base number, which is usually 32. Which means that the grid, this program, may have more threads that it needs. So some threads should not be doing anything, so should not be loading any data and should not be computing any summation. So this is why we need this mask. This means that if all these offsets that we are loading should be at most up to n elements, because imagine you have not 2000, imagine you have a vector of 2060 elements, which means that this offset for the third program of this kernel will load the offset that go from 2048, 2049, blah blah, 2060, and then also 2061, 2062, etc., etc. But we said that we only have 2060 elements, so all the elements of 2061, 62, etc. until 3000 and something, they don't exist. So we need to tell somehow that all the threads that are working with these elements should not load anything. That's why we need this mask. This mask tells load among all the offsets that this block should work with only those elements that actually exist, for which this mask is true. Then we load the elements of this current program, which is a group of elements defined by these offsets. and only the one that for which this mask is true, so only the one that actually exists. All the others should be ignored, and we can also specify what it should load in case this the mask is false with another parameter, but we will not see that here. We also load the group of elements of the y vector, and then we compute the output x plus y. So if you remember previously in CUDA we did something like this, like the output of I is equal to the x of I plus the y of I. So we did it one element at a time because each thread was working with one index. Here we are working with a group of elements. So this x is a group of elements, is a block of elements at most of size block size. Actually of size block size. And this y is a group of elements from the y vector. And we are computing the output group by group. So this is summing a group of elements of x with the corresponding group in y and writing it in output. Then we need to restore this output. We need to store it in the output tensor, output ptr, that you can see here, which is a pointer to the first element of the output vector. And we say that where should we store this output vector, which is of size, shape of this vector here is block size. Where should we save it? Well, in the same offset to where which we loaded x. So if this program work with the index 2048, 2049, etc., etc., then all this output should be written in the same offset, 2048, 2049, etc., up to 3000 and something. Using the mask as well, because we don't want to write all the values of this block size, because maybe we don't have enough elements, so only write the one that are actually present in the vector. So the reason we need the mask is because CUDA will launch a number of threads that is always a multiple of a base unit that may not be a multiple of the vector size that we are working with. So we need to find a way to tell some threads to not do anything for those that the data is not available. So let's rehearse what you have seen so far. In CUDA, the program that we write is at the thread level. So each thread, what it should do. In Triton, it's this block of data. We work with a block of threads. What data this block of threads should work with. All right, guys, finally the moment has come. So we are going to code the flash attention forward pass right now in Triton. But let's rehearse the algorithm. So the goal of the attention mechanism, specifically in Triton, in flash attention, is to compute the attention output, which is we want to compute the output of the following formula. So the query multiplied by the transpose of the key divided by the square root of the head dimension, all we apply the softmax, and then all multiplied by v. Now in this video, we will be coding the forward pass and also the backward pass. But before coding the backward pass, we need to understand how the Autograd works. We need to understand what is the gradient, what is the Jacobian, how to derive the gradient of the softmax operation, how to derive the gradient of the matrix multiplication operation, etc., etc. So that is going to be another part of the video. For now, let's concentrate on the forward pass. Right now we have some tools. So we know that we have this thing called the GPU that can parallelize operation among multiple cores. We know that in CUDA we can parallelize operations by writing a program that is the definition of what each thread should do, or we can follow the Triton programming mode, which is telling in Python what each group of threads should do. The mapping between what each thread should do and which element that should thread work with is up to us, to the programmers. And the same happens in Triton. We tell how many blocks of threads we want, how much data each block of thread should process. So that's the block size that we saw in the vector addition. But then the mapping between the elements of the vector and the identity of each group of threads, so the program ID that we saw, is up to us. And the same will happen when we code flash attention. Let's see what can we parallelize in this flash attention. So first of all, this code that you see, the forward pass of the flash attention, takes as input query key and value that is a matrices of n by d. However, usually in a transformer network, we don't have only one sequence made up of d dimensions, we have many sequences made up of d dimensions. And this d is the lowercase d, which is the number of dimensions dedicated for each head, but we don't have only one head, we have multiple heads. So the algorithm that you see here is what each head should work. So each head of each batch should do. Moreover, we have seen before when talking about block matrix multiplication that we can parallelize the computation of the output, because this output block here depends on the query 1 and all the keys. This one here depends on the query group block of query 2 with all the keys. And this one here is the query 3 with all the keys, etc. So because this one only depends on the block query 1, and this one only depends on the block query 2, they can work independently from each other by sharing, of course, the keys. Another thing that we need to understand about Triton is the shared memory. So in the GPU we have the high bandwidth memory, and which is the kind of the RAM. So when you buy an A100, they tell you that it has 40 gigabyte. That's the amount of memory in the high bandwidth memory, so the DRAM. So let's look at actually the structure of the GPU, which is here. We have this DRAM, which is the big memory that the GPU has, and then each streaming multiprocessor, so it's let's call it a block of threads, actually also have a shared memory. So inside of the GPU, actually we have these streaming multiprocessors, and these streaming multiprocessors have a part of memory called the shared memory, which is much smaller than the DRAM, like much smaller. What changes between these two memories? The access to the DRAM is very slow, and the access to the shared memory is very fast. So one thing that is different between CUDA and Triton is that whenever you load some information in CUDA, you are loading that information directly from the global memory. Because when we launch a CUDA kernel, first of all, as you remember in my C++ code, we first copy the tensors or the vectors from the CPU to the GPU, and they reside in the global memory of the GPU. Then we load these elements directly from the global memory. But the access to the global memory, usually it's much slower. So what happens with the flash attention is that the flash attention computation in its, the attention computation in its naive version, the one that we can do with the torch, is very slow because the access to the global memory is very slow. So we want to use as much as possible the shared memory. So we want to reuse the elements loaded from the global memory into the shared memory, so that we don't need to access the global memory every time to load elements from the vectors or the matrices. And this is what happens also in Triton. So in Triton, whenever you load some data, you are copying the information from the global memory to the shared memory. Then whatever operations that you are doing is done on the shared memory. And then when you store the information, you are copying the data from the shared memory to the global memory. This makes it much faster. So we always work with the elements that have been loaded in the shared memory. And this shared memory, basically, it's shared for all the threads that belong to the same block. In Triton, we have an abstraction level that doesn't make us work directly with the threads, so we always work with a group of threads that belong to the same block that share this shared memory. So in Triton, we are copying information from the global memory to the shared memory, we do some operation with it, and then we store back to the global memory. And this is what we are going to do with flash attention. Now let's review the algorithm of flash attention. So in flash attention, we have to go an outer for loop that is among all the between all the keys, and then an inner loop that is between all the query blocks, and then an inner loop that is through all the key block. In the original flash attention algorithm, the flash attention 1, the outer block was on the keys and the inner block was on the queries. This made it less parallelizable. Why? Because the outer loop is on the queries, and we have seen before that the output of this attention can be computed independently for each block of queries, so it's much easier to parallelize. So this outer for loop, actually we don't have to run a for loop, we just spawn many kernels, each working with one iteration of this outer for loop. So each working with a different query block of this outer for loop. And the inner for loop is something that we have to iterate through. So each Triton kernel will work with one query block and then iterate through all the key blocks. And inside of this key block, we have already seen the operations that we are going to do, which we explored before. And at the end of this for loop, we need to store back the output in the high bandwidth memory. And this is how we are going to work. Another thing that we should notice is that this query key and value are n by d, so as I said before, but usually in a transformer model, we don't have only one sequence, we have many sequences, so we can also parallelize on the number of sequences that we have in the batch, because each batch can work independently from each other. And inside each sequence has multiple heads, so each head also can work independently from each other, because that we know from the attention is all unit paper. That's what's the meaning of head, what's the meaning of multi-head attention, so that each head can compute the attention independently from each other. So we will also parallelize along the head dimension. And moreover, if you look at this definition of the query block, we can also split the query into blocks, and each query block can work independently from the other query blocks in producing one output block. This is how we are going to parallelize. So we are going to parallelize each sequence in the batch. Inside of each sequence, we are going to parallelize each head, and inside of each head, we are going to parallelize each query block. So how many programs we will have working in parallel at most? It will be the number of batches, so the number of sequences in the batch, so the batch size. It will be the batch size multiplied by the number of heads multiplied by the number of blocks that we will divide the query sequence into. So let's call it the, I don't know, block size Q. The block size Q. All right, now that we have seen this one, let's go actually code it. So I have already introduced a little bit the differences between my implementation of the flash attention and the one that you can find on the Triton documentation, which is, first of all, I don't work with FP8 because I believe this is unnecessary for our explanation. It's, of course, much faster because the recent GPUs also support FP8. Second difference is that in the flash attention on the Triton website, the backward pass is only implemented for the causal attention, but in my case I implemented for the causal and the non-causal attention, even if it's slower. And later I want to give you an exercise on how to improve it. And the third difference, main difference, is that I make explicit use of the Softmax scale. So I actually use the scale when needed. Another difference is that in the online Triton computation of the flash attention is this exp is not really e to the power of x, but it's 2 to the power of x, and then they compensate it with by using the logarithm. However, because probably the implementation of 2 to the power of x is faster than the e to the power of x, but in my case I retain the original exponential because I want to follow the original algorithm to make it simpler to visualize the code along with the algorithm as in the flash attention paper. So I know I have created a lot of hype, so let's do it. Let's start by creating a new file. Let's call it program.py. Just like before when I introduced Triton, I will start by coding first the code that will use our kernel, and then we code the kernel, and we will only be coding the forward pass of the kernel. So let's start by importing what we need to import, which is just the torch and the Triton. And secondly, let's start by, let me check, okay, the copilot is already off, so I don't have to worry about that. Let's start to implement the code that will test our implementation of the Triton and compare it with the naive implementation of the attention mechanism. So we create our query key and value sequence for testing, which is, if you remember, it's a query is the batch size. It has the dimension batch size because we have multiple sequences. Each sequence has a number of heads, and it's made up of seqlen tokens, and each token is identified by a head dim number of dimensions. If you this is because we have already split each token into smaller tokens, each with its own head dimension. If you remove the num-heads dimension, then you concatenate all the dimensions of this head dim. We initialize the query key and the value sequence by using a normal distribution. This code I already took from the tutorial of Triton, so it's nothing different. And we require the gradient because we want to compute the gradient with respect to query key and value, and we will see later why, because we want to implement we want to test also the backward pass, even though we will not be coding it now. So the first thing that we do is we define our softmax scale, which is, as you remember, the formula is query multiplied by the transpose of the keys, and then divided by the square root of head dimension, so dk, or the head, sometimes it's called. And then we need to compute this one. We can already compute it. This is 1 over the square root of the head dimension. And then we also define do, and later we will see what is this, but this is basically we will be needed for the backward pass. Don't worry if you don't understand what is do, later we will see it. Let's do the naive implementation of the attention, which is very simple, which is first we define the mask, and we use this mask only if the attention we are computing is causal. So as you can see, we pass this parameter called causal that tells if we want to compute the causal attention or the not causal attention. And the D type, which is float 16, because we want to work directly with 16-bit floating point numbers. We will not be working with FP8 just because we don't want to implement. My implementation is actually not as fast as the one in the tutorial of the Triton website, but I believe it's much more easier to comprehend. So we define the mask. We compute the product query multiplied by the transpose of the key divided by the square root of the head dimension. So that's why we are multiplying by softmax scale. If the attention we are computing is causal, then we use this mask that we have computed. So we replace all the points, all the dot products where this mask is equal to 0 with minus infinities, and then the softmax will replace this minus infinities with zeros, because then we are applying the softmax, and the softmax is applied by rows, just like the normal attention we compute. Okay, the second thing that we do is we want to, so the output is the product of the output of the softmax with the V. So this is the reference output on the naive implementation of of the attention mechanism. Then we want to we want to also derive the gradients of the output with respect to the inputs. And in this case, it's the V, the K, and the Q. Later we will see what are we doing here. Then we want to compare this reference implementation with our Triton implementation. So let's do it. So our Triton implementation will be implemented as a class called Triton Attention that we will call using this method called apply, and later we will see what is this method, in which we pass the query key and value if we want to compute the causal attention, the softmax scale that it should be using, and it should produce some output, which is the output of the softmax multiplied by V. Then we can run also the backward, and this backward will be the same backward that we will compute with the Triton attention, and then we compare. Okay, and then we can compare the result of our implementation, so this Triton attention.apply, with the reference implementation, which is this one here. And they should be, we use the function allClose, which basically compares the elements of two tensors and make sure that their absolute difference is no more than this one. We are not using the relative distance, we are just using the absolute distance between the two elements, which corresponding elements of two vectors. This implementation that we will build will work with the causal attention and also with not causal attention, while the one that we saw in the website of Triton only works with the forward pass actually works with the causal and non-causal, while the backward pass only works in the case of the causal attention. Okay, but it's highly optimized, the one online. So if you want to learn a little more tricks on how to optimize Triton kernels, there is a lot of knowledge there. Anyway, guys, now let's try to implement this Triton attention, at least the forward pass. So let's go to implement this Triton attention class. Okay, here, every time you want to introduce a new operation into Torch, you need to you need to implement your operation by deriving from this Autograd.function class. So every operation in Torch, actually, if it's the Softmax or it's the I don't know, the relu or the zwiglu or whatever there is, it is always implemented as a function, is a class that derives from this function. And it should provide two methods, one called the forward pass and one called the backward pass. The forward should produce the output of this operation, and the backward should compute the gradient. Of the loss with respect to that the input of that function. And later we will see how that works. For now, let's concentrate on the forward pass. To implement the forward pass, we need to create a static method that is called forward, which takes as input one thing called the context. So as you know, in the Autograd, when training neural networks, we have the forward pass and the backward. When computing the backward pass, we need to reuse the activations of each of the computation nodes during the forward pass, and this context basically allows us to save the information for the necessary activations that we will need during the backward pass. And later we will see in the Triton, in the flash attention algorithm, what information we need to save in order to compute the backward pass. For example, what we will need to save. During the backward pass, we will need to recompute on the fly the query multiplied by the transpose of the keys for each block, but we don't want to recompute the normalization factor or the maximum value for each row, so we will save those two values. And actually, we will not save two values, we will save one value with a trick called the LogSumExp trick that we will see later. Anyway, this context is just a kind of a storage area where we can save some stuff that will be necessary for us to recompute the backward. And you can save whatever you like. Then we have the input of this operation, which is the query key and value, which is 3 tensors. The causal, if we are going to compute the causal attention, and the softmax scale that we should apply based on the 1 over the square root of the head dimension, which we could also compute it on the fly, actually, by the way, by checking the shape of this, but okay, it doesn't matter. Anyway, so the first thing that we are going to do is to extract the shapes of these objects and make sure all the shapes are what we expect them to be. So the shape of the query key and value is a batch size by number of heads by sequence length by head dimension. We make sure that the head dimension matches for the query key and value. They should match because each vector should be of the same size. And then we declare we pre-allocate the output vector, so where we should save our output. So as you remember, the output in the attention mechanism has the same shape as the query key and value sequence, where the query key and value sequence, I want to remind you, is not the query key and value of the input of the attention, which is a sequence of tokens, but it's the output already of the WQ, WK, and WV, because flash attention is not concerned with optimizing those matrix multiplication, but only the output of the WQ, WK, and WV. So we pre-allocate the output tensor where we will store this output, which has the same shape as the query key and sequence matrix. Actually, no, not true. Actually, it has the same shape as the query, but it may not be the same as the key and value. Why? Because there is this thing called cross attention, where the query key and value are transposition, are different projection through WQ, WK, WV, not of the same input sequence, but of two sequences. So cross attention happens when we have a query that comes from one sequence, and the key and value come from another sequence, and they pass through their own WK and WV, and they may not have the same sequence length. So the shapes of the output of the attention only depends on the shape of the query sequence, not of the key and value sequence. This happens during cross attention, but usually in language models we always work with the self attention, so that should not happen, at least in the causal language models. Then we have the stage, and later we will see what is this stage. Basically, the stage, it's just a number that tells if the operation that we are going to do later is for the causal attention or for the not causal attention. And then we need to define our launch grid. The launch grid tells us how many parallel processes we need to be launched by Triton. Actually, they will be launched by CUDA, but we always work with the Triton as an interface to CUDA, so by Triton. So in Triton, as I said before, we want to parallelize along the batch dimension. So each sequence in the batch should work independently from each other. Not only inside of each sequence in the batch, each head should work independently from each other. So at least we have a batch size multiplied by number of heads programs. And for each of these programs, we have another dimension called we divide the query into blocks of queries. So as you remember, when talking about a block matrix multiplication, we don't work with the query as the original matrix query matrix. So where each query is one vector or one token, we work with group of queries. So each block of queries is a group of tokens in the query sequence. So we are saying that we want to launch a number of kernels or blocks of threads or a group of threads along 2 dimensions. So just like the CUDA kernel can be launched along 2 dimensions, X and Y, here we are launching programs along 2 dimensions. One dimension that tells us which head of which batch we are going to work with. So which head of which batch element are we going to work with, and inside this we are going to say, okay, this is a sequence, which group of queries are we going to work with, so overall, and the group of queries is what is the sequence length divided by the number of queries that we want to group together. So the block size Q tells us how many queries are there in each block of queries. So this is cdiv is just the ceiling division. So it is equal to, let me write it here. This is equal to ceiling of sequence length divided by the block size Q. This tells us how many blocks of Q we have. So let's rehearse. We have a tensor that is Q, that is batch size by number of heads, and each flash attention algorithm will work with the following: the sequence length head dimension. Moreover, we have seen that the flash attention has 2 loops. One is the outer loop among all the query blocks, one is the inner loop along all the key block. We have seen that the query block can work independently from each other, so we can spawn as many programs in parallel as there are number of blocks of Q, because they can work in parallel. So this grid tells us how many programs there are that can work in parallel. Then it will be the GPU that, based on its resources, will decide how many programs actually to work in parallel. If it has enough resources to make them all work in parallel, wonderful. If it doesn't have enough resources to make them work in parallel, it will launch them sequentially, one after another. And the last dimension is, this is like the Z dimension in the CUDA launch grid, and we don't want to use it because we don't want an additional level of parallelism. All right, this is our launch grid. So we will launch a number of programs, that is this one, a number of programs of parallel programs or number of parallel kernels, and each kernel in Triton work is a group of threads, which is batch size multiplied by number of heads multiplied by number of blocks of Q. So how many blocks we have we divided the Q sequence into. Okay, let's continue. So we will see what is this one. So this M is another matrix that we will need, and it's the LogSumExp for the backward pass, and we will see at the end of this video what is, not at the end of this video, but at the end of the forward pass, what it's needed for. But basically this is, you can think of it as the maximum for each row. To recompute the query multiplied by the key in the backward pass, we should also have, if we don't want to recompute the maximum for each row and the normalization factor of the softmax, we should save 2 things. One is the maximum for each row, and one is the normalization factor. However, by using the LogSumExp trick, we can only save 1 value, which is the, as you can see in the algorithm of flash attention, it's this stuff here, which is let's see here. it's this stuff here. So this Li, which is the maximum for each row, plus the logarithm of the normalization factor. And basically, when computing the backward pass, we need to recompute on the fly this block here. So this query multiplied by the transpose of degree. But to apply the softmax, as you remember, we need to have the maximum for each row and the normalization factor. So we don't recompute them during the backward because we have already computed them during the forward, so we save this information. But we don't need to save these two information separately. We can aggregate it into one single value called Li, and later we will see how we can use it. All right, so we have defined also this one, and we can proceed further. So now we launch our grid, our kernel. Don't be scared, it's gonna be a little long, so here. So we are launching the kernel for the forward pass by defining what is the launch grid, so how many of this program should run in parallel at most. We are passing the query, we are passing the key, we are passing the values, we are passing the softmax scale, the M, which is the information that we need to save for the backward pass. It's actually the L in the code of the pseudocode of the flash attention algorithm. Here I call it M, I think because also in the original code it was called M. The O, where our kernel should save its output. And then, as you remember, we don't get all the nice access by indexing tensor like we are used to in Torch. We only get a pointer to the starting element of Q, a pointer to the starting element of K, and to the starting element of V, and then we have to figure out all the index in the memory of the other elements. How to calculate the index? We need the stride, because the stride tells us how many elements to skip to go from one dimension to the other. And that's why we are passing the stride for each dimension of each tensor. Actually, in our case, we are only working with Q, K, and V that are actually of the same D type and of the same shape, so we should not need actually to pass all the stride for each of these tensors. Because they should have the same strides. However, in the original code, I believe they were passing it, so I kept it. So the stride will allow us to index these pointers, so to understand, to access the elements of this tensor just by using its starting, the pointer to the starting element, and then the strides we will be able to index any element we want in the tensor. Then we pass the information of these shapes, so the batch size, the number of heads, the sequence length, and the head dimension, and which is the same for all of them. And then the stage. The stage indicates if we are going to compute causal attention or not causal attention. So let's not implement it, and let's continue writing this method. So then we need to save some information that will be needed for the backward pass, which is this context variable that I told you before. So we save some information for the backward pass, which is the query key and value, which are the tensor for which we want to compute the gradient during the backward pass. And then we need to store also this M tensor and this O tensor. Then we need to also store the causal variable. So because if we computed the causal attention during the forward pass, then during the backward pass we need to have this information, because we need to mask out the things that we don't want to contribute to the gradient. But we will see that later when computing the backward pass. For now, let's concentrate on this attention forward. So we need to implement this forward kernel that you can see. So underscore attention underscore forward method. Now a Triton kernel is just a Python method with a particular decorator called triton.cheat. So we copy and paste the signature. So this is what makes a method become a Triton kernel. And as you can see here, we pass the query key and value matrix along with other information, the M matrix. So please don't confuse the M matrix with the mask that we will apply on the fly. We will generate it on the fly because we are only concerned in this case with causal attention or not causal attention. We do not accept custom masks here. Then we pass the strides of all these tensors, the batch size, the number of heads, the sequence length, the head dimension, which is the shape of each of these tensors. and the block size Q and the block size KV. The block size Q indicates how many queries we want to group together to make one block of the Q matrix, and the KV indicates how many keys and values we want to put together to make one block of the K and V matrix, which is what we do when we do block matrix multiplication. This stage is a number that indicates if it's a causal or not causal attention we are doing. So it will be 3 in case it's a causal and 1 in case it's not causal. Okay, the first thing that we do is to verify some information. So we verify that the block size of the KV is less than or equal to the head dimension. To be honest, I don't think we need it with my code because I removed most of the constraints. So this check was also present in the original code, so I kept it. But it all depends on how we are. Later we will see what is the auto-tuning process, and later we will see what variables we are going to auto-tune for, and how many stages we will choose, how many warps we will choose, etc., etc. So let's leave it for later. You can comment it or you can keep it. It shouldn't matter. The first thing that we do, as I said before, we launch a grid. So a grid is a series of programs where we will have some identifiers. Like in the CUDA, we had an identifier for the blocks on the x-axis and on the y-axis. In Triton, we get this identifier for the programs. We launched sequence length divided by block size Q, number of programs along the 0th axis, and the batch size multiplied by number of heads along the first axis of the grid, of the launch grid, which will help us identify which part of the query we are going to work with in this program, in this kernel, and also in which batch and on which head this program should work with. So that's what we are going to do now. We are trying to understand what part of the input we should work with based on the IDs of the program, which corresponds to the block ID in CUDA. So that's me copy. So the program ID 0 indicates, it's this stuff here, tells us which part of the queries, so which block of the queries we are going to work with. Why do we have a block on the query? Because as we saw before, the output can be computed independently for each block of the queries, while each block of the query has to iterate through all the key and values. So this is what will tell us what is the index of the block of the queries we are going to work with in this particular program. Then we can understand also which index, which batch, and which head this program is associated with. The program ID number 1 is the product of the batch size and the number of heads. It means that we will have as many programs on the axis number 1 as there are indicated by this product. So this product lets us understand that this product will tell us which batch and which head this particular program is associated with. So to get the ID of the batch, we just divide this number by the number of heads and it will give us the head index. And to get the head index inside this batch, we just do the this number here, modulus the number of heads. Okay. The next thing that we need to do, okay, first of all, when we pass a tensor, because as you can see here, the Q parameter to this attention forward method is a tensor, because it's the input of this function, forward function, and this forward function is called here when we do attention.apply, and it's this Q stuff here, and this Q stuff here has been created as a tensor. So when we pass a tensor to a Triton kernel, it's not really a tensor, it is a pointer to the first element of that tensor in the memory. Now we need to understand, because now we know which batch we are going to work with and which head we are going to work with, we need to index this tensor to select the right batch and the right head inside of the right batch. Which means that basically we have this Q tensor, so we need to do some sort of like this, some stuff like this, like a Q of the index batch and the number of heads indicates which head we are going to work with, so it should be index of head, and we need to select everything that is inside these indices. So we need to enter the tensor at the right location where the particular sequence length and head dimension for this batch and for this head starts. For that, we need to generate an offset in which we need to move this tensor from, because this pointer is pointing at the beginning of the entire tensor. So we need to move in the batch size dimension and in the number of heads dimension. To do that, we generate the following offset, which will tell us where this particular batch and where this particular head starts in this tensor. And to do that, we need to do the strides. We need to use the strides. So what we are going to do is we're going to create the QKV offset. Should be the sequence length, which will be the index batch multiplied by the stride for the batch dimension, which will tell us how many elements we need to skip to get to the next batch. And it's based, and we multiply it by the index of the batch that we want. So for the 0th batch, we don't skip anything because we are already pointing to the first element of that batch. But if we are at the batch 1, we will skip that many number of elements. Plus, we also need to skip some heads. How many heads we need to skip based on which head we are going to work with. And what tells us how to go from one head to the next? The stride of the head dimension. So we multiply the index head, so the head that we should be working with the stride Q head. All right. Then we select, now Triton helps us with a new function that I think it was quite recent, that helps us index element inside of a tensor without having to deal with all the complex indexing maths that can be confusing for beginners. So I will be using a few methods to help us with this indexing. And this function is called makeBlockPointer, and it's this following. So basically, this makeBlockPointer takes as input a vector and a pointer, not a vector. It takes as input a pointer. In this case, we are saying create a block that has the following shape, that is sequence length by head dimension. So let me do it one by one, actually. I don't want to confuse you guys with all this stuff all together. Okay, so there is a pointer that is right now pointing at Q plus QKV offset. So right now it is not pointing at the first batch, but it's pointing exactly to our batch, so the batch that this particular program should be working with, and inside this batch to the particular head that this program should be working with, which is basically saying that we are pointing to a tensor that is as follows. So we are pointing to the following tensors, which is the right head, the right batch and the right head, and then we are selecting everything inside. So it's pointing to the first element of this particular tensor. This particular tensor, because we have already selected the batch and the head, it is a two-dimensional tensor with the following shape, because the following dimensions are sequence length and head dim. So we are saying, take this pointer, which contains a tensor of the following shape, sequence length and head dimension, and I'm also giving you the strides of these dimensions that are in this pointer. So the two dimensions that we need are the sequence dimension and the head dim dimension, which is this one, for the Q tensor. And in this query tensor, we want to select a block of queries based on the block of queries that this program should be working with. So I think I need to probably use the iPad, otherwise it can be very confusing to visualize. So let's do it actually. So let me see if I can create another here, and let's use the iPad. All right. Okay, so we have a Q vector, a Q tensor, because this construct we will be using it for all the other tensors. So if you understand it for one tensor, you understand it for all the others. We have a Q tensor that is a batch by number of heads, then the sequence length, and then the head dimension. with the following line. So this line here, so when we create a Q plus QKV offset, we are already selecting the right batch dimension and already the right head dimension, which means that we have already forwarded our Q to not point to the first batch and the first head, but to point to the exact batch that this program is working with and the exact head that this program is working with, which basically means that right now it is pointing at a tensor that is made up of these two dimensions. Now, inside of this tensor, we also need to select the right block of query that this program should work with. And this dimension here, so the sequence dimension, is all the queries. So we need to select the right queries. So we need to skip some queries. How to skip some queries? Well, we say that we need to skip block index multiplied by block size Q number of queries, because they will be processed by another program that will have this number here. The program ID will be different. So we are selecting with this line not only inside of the queue the right index and the head, but also the right position in this dimension, in the sequence length dimension, that will point to the starting point of the exact query block that this particular program should be working with. This is what is happening. And we are also creating this block. Basically, later we will see how it can be used to create a block of the shape. We are telling what is the size of this tensor. So this tensor has two dimensions because we are pointing to the beginning of the right query sequence. So it has only two dimensions, the sequence dimension and the head dim dimension. So it's the last dimension. And we are already pointing to the right beginning of the sequence dimension because we have already skipped some queries. Why we are skipping some queries? Because these queries will be handled by another program that will have a block index Q to some other values. This order, actually I don't know what is this order. You can try to put 0, 1 and 1, 2. I think it's some optimization that Triton does. I have read the online documentation and I couldn't find anything about it. So this is something that I will investigate, but actually even if you put 0, 1, it doesn't matter. So I think it's something that you tell Triton if you want the transposed of this block or you want the not transposed version of this block. And later we will see actually how we can transpose the key block without doing any transpose operation. Actually, we will just change the strides like we have seen before. So now this make block pointer is not something that is necessary, but it makes our life easier when we will index this particular pointer. So we can treat this pointer nearly in the same way when we work with the tensor in PyTorch. We will be able to skip one, increase one index in one dimension without having to do the computation of the strides. Later, when doing the backward pass, I will not use this one and do all the pointer indexing by hand, so you can check the differences of indexing a tensor by using a make block pointer and not by using it. Anyway, to rehearse, what are we creating? We are creating a pointer to the right index in the batch, to the right index in the head dimension, and we are already skipping some queries based on the block index Q. So this pointer is already pointing to the right block of queries that this particular program should be working with. Let's look instead at the V and the K block now. So let's copy the V block now, which is similar to the query, but we are not going inside. We are only indexing by the index batch and the index head. So what this one, actually, let me write it here, is already skipping this amount of queries. This is what we are indexing with this make block pointer. So we are in the right batch, in the right head, and we are skipping some queries. Here, we are just indexing by batch and by head. So we are doing a V of index batch, index head, and we are not selecting, we are not skipping anything because you see this offset is equal to 0 in the first dimension, in the second dimension. So we are not skipping anything on the sequence length, and we are not skipping anything in the head dimension. Alright, so let's look at the k-block pointer, and this is different because, as you know, when computing the flash attention algorithm, we need to have access to a block of queries and all the block of the key transposed. So when accessing the key, we shouldn't access it like we are accessing Q. We should invert the two dimensions that we want to transpose for, and that's very simple with make block PTR, and you can see it here. We say that we want to point to the right index and to the right head, and the tensor inside of it. So let me write it here, so later I can explain it line by line. So what we are doing here is go to the K tensor, select the right batch, select the right head, select everything that is inside. So it's a tensor of 2 dimensions with the sequence length and the head dim, because you can see here sequence length and head dims, etc. But we don't want first sequence length and then head dim. We want first head dim and then sequence length. So we want to transpose it. How to transpose it? We just say that you need to read this tensor with the 2 strides transposed. So we are saying first use the stride of the dimension, and then use the stride of the sequence dimension, and the shape of this tensor is not sequence head dim, it's a head dim sequence, and it's a block of KVs. Why we are not putting directly the sequence dimension here? Because we want to skip block by block later. So we are not selecting all the sequence length in the sequence dimension, we are just selecting a block of KVs. And later we will use another method to go to the next block. So I hope that by showing you the indexing like this, it's a little easier to follow the indexing. So for each tensor, we are going in the right batch in the right head dimension, and for the query, we are skipping some query blocks because each program will work with a small different query block. But for the key and value, each program needs to iterate through all the key and value. So we just point it to the first key and value block, and then we will advance by one block by one block by one during the for loop that we will do later. Then in the output also we can make a tensor, block tensor. This basically creates a pointer just like in the query key and value case, in which we select the right index batch. So what we are doing is we are indexing by batch, we are indexing by head, and we are selecting everything that inside. No, we are not selecting everything inside. We are skipping also in this case some blocks of queries. Because as I said before, the output has the same shape as the query. So this particular block, this particular program that will have this particular block index Q will only work with one block of the queries, which will produce only one block of the output matrix, and we need to select exactly that one. So we can point this pointer exactly to the point where we should start writing. So let's skip also in this case block index Q multiplied by block size Q rows. So we select exactly the block that our program, this particular program, will produce. When I speak about this particular program, I mean the program that is identified by this program ID in the x0 axis and this program ID in the first axis, because each of these programs will run in parallel, hopefully, and each of them will have a different value for the block index Q and index batch head. Okay, now we have pointed our pointers to the right position, where they should either read some information or they should either write some information. By using make block pointer, these pointers can also be treated directly as tensors. So that's why we specify the shapes of these tensors, because Triton right now provides some methods to work directly with blocks of to work directly with pointers like we are accessing tensors. So we can index them like tensors. All right, so basically just Triton doing some calculation for you based on the strides, so you don't have to do it by hand. But later when we do the backward pass, we will avoid using make block pointer, and we will see the indexing done by hand. All right, as you know, we are processing a single block of queries. So let's go back to the algorithm, otherwise we lose the sight of what we are doing. So let's go here and let's show my iPad. All right, so as you know, each program we will parallelize along the query block dimension. So each program will work with a different query block. And then we need to do a for loop on all the key and value blocks. Right now we just moved our pointers to the right position to select the right query block that we should work with, and to the beginning of the keys and values block that we should work with, based on which index and which head this particular program should be working with. Alright, now that we have pointed our pointers to the right position in which our program should be working it inside of the big pointers that are inside of the big tensors that have the batch dimension, the number of heads dimension, the sequence length dimension, and the heading dimension, we have, because we are pointing to the right batch and we are pointing to the right head, these tensors have become two-dimensional tensors. So they only work on they are only tensors on the sequence length and on the head dimension. Now we need some more information that we will use later. The first information that we need is the offsets of each query inside of the current block of queries that this particular program should be working with. And that is given by the following line. So let me copy and paste, which is this one. So the offsets of the queries are the, first of all, they are how many of them block size q, because each block of queries is made up of a block size q number of queries. What is each query? It's a token. And it's on the head dimension is the dim dimension is not all the embedding of the token, but a part of the embedding of each token, which part? The part corresponding to the head that this particular program is going to work with. So we are generating the offsets that will load this particular number of this particular queries from the big tensor that contains all queries. And we know that our queries start at the block index q multiplied by block size q position. So if this is the program number 0, they imagine block size is equal to 4. They will be the query with index 0, 1, 2, and 3. But imagine we are the program number 3, which means that we need to skip 3 multiplied by 4, so 12. So it will point to the query number 13, 14, 15, and 16, etc., etc., etc. All right, and we do the same for the key and values. Initially, the key and values is a range of keys and values that we need at each iteration. And at the beginning, because our pointer for the k and v is pointing to the beginning of the sequence of key and value for this particular batch and for this particular head, we are pointing to the first block of key and value. So we are not skipping anything. In the query case, we are skipping because our program will only work with one single block of queries. In this case, we don't skip anything because we need to iterate through these key and values. So we are pointing to the first block of key values. So imagine block size kv is equal to 4. So this stuff here will be equal to 0, 1, 2, and 3. All right, now we need, as you remember, inside of the flash attention algorithm, we need to compute a block of query multiplied by the transpose of the keys. And to each of this block, we need to apply the softmax star. If you remember what is the softmax star, it is the softmax of without the normalization. So while computing the softmax star, we also actually compute the normalization factor without applying it, and we apply the normalization factor at the end. So for each block of query multiplied by transpose of the keys, we need to have the maximum for each row in this particular block and the normalization factor for each row. So that's why we need these two following statistics, which is this one. And this is basically a block, it's a block of numbers, based on how many queries we have in our block of queries. Each one initialized with -infinity, just like in my algorithm that I showed before. So let me go back to the slides in case we forgot. Or actually, you can also check the flash attention algorithm. We initialize it with -infinities. So far we are creating this stuff here. So we are initializing the mi, we will be initializing the li, and we will initializing the o. And then we will show the inner loop here. And this is exactly the algorithm that we have seen before. So we initialize m with minus infinities. Now we initialize also the else. So let me go back to the code. All right. So the else are initialized with this number here. So here. In the O blocks, as we can see from the flash attention algorithm, the O block is initialized with zeros. So that's why we initialize a block. This is the output block that this particular program will compute, which is based on the position in the batch and the position in the indexes. So it is one block of the size block size q. So how many queries there are in this block by head dimension. Which, if you want to visualize it, let's go back to the slides. It is equal to one block of this matrix here. So it's one block of the output matrix. So one row of blocks, one block of rows. Okay, so let's go back to the code now. All right. So now we have initialized a little stuff here. So the output, the mi and the li, where mi is the maximum for each row in this particular query block, and the li is the normalization factor for each of the items in the query, for each of the rows in our query block. Now we need to do the for loop, the inner loop in the flash attention algorithm. We will create a separate method that will run the inner loop. So let me copy it here, and I am following the same structure of the code that you see in the tutorial of the Triton website. So basically, if we are running the causal attention, or even if we are not running the causal attention, we make this for loop, and then we will make another for loop. And I will show you why. So let me first write it, and then we will see. So this function here will be the inner loop. This inner loop needs to go through all key and value blocks one by one. And for each query and value block, it needs to fix the previous calculated block of the previous softmax star block. So basically what we are doing here, we will need to create a function as the following, where we are going to iterate on all the key value block. We will need to compute the query multiplied by the transpose of the keys using the query block that is fixed for this program, and the key block is the one that we are iterating it through. And for each of these queries, we need to calculate what is the maximum for each row. We need to compute the softmax star, so the softmax without the normalization factor. We need to keep the statistics L, which is the normalization factor that we will apply at the end of the iteration of the for loop. And at the same time, we need to update the output. So as you remember, the output is P11 multiplied by V1 plus P12 multiplied by V2, but we need to fix the previous P11. So to fix that, we need to, every time we sum to O to the output, we need to fix the output of the previous iteration, and then we introduce the P and V block of the current iteration. So here the author of the code for the one that you see on the Triton website decided to split this for loop into two steps. Why? Because in the causal attention, we need to when we have a causal attention, we have a group of we don't want the query to attend keys that come after it, while in the non-causal attention we let all the queries attend to all the keys, which also means that we will need to have some kind of if statement inside of this inside of this for loop through all the key and values, in which we need to check if this particular query that we are working with comes before or after the key and value, in case we are doing the causal attention. So instead of iterating through all the key and values, also in the case of the causal attention, by splitting it into two steps, we are saying first let's iterate through all the key and values for which the index is smaller than the current queries block. And for this, we need to compute the attention in the case of the causal and non-causal case. Then, for all the elements on the right of this block, so for which the key index is more than the Q index, in the case of causal attention, we don't need to compute anything because it will be masked out, because in the softmax it will become zeros. So it will not contribute to the output, so we don't even have to compute it. This is why we split this for loop into two steps. So first we iterate to all the parts that are left to the diagonal of the query multiplied by the key matrix. So for all the values for which the query index is less than the key index, then we skip all the parts to the right of this diagonal in case we are working with the causal mask. But in case of the non-causal mask, we compute the left part and the right part of this diagonal. Alright, don't worry, when we recode this for loop it will be more clear, so I just wanted to give a little introduction. So let's go code this inner loop. What will this inner loop do? It will work with this particular query block that we have found, so this Q block. It will, why? I don't see the Q block because I didn't load it well. Yeah. Let's load it. So we need to load the query block actually. We forgot to load it. So as you remember in Triton, we load data from the high bandwidth memory to the SRAM, so to the shared memory by using the load statement. And we are telling load the query block that we should be working with, because this pointer Q block PTR is already pointing to the right block that we should be working with. So it's already skipping all the blocks that other programs should be working with. And it will load a tensor of size of block size Q head dim, so the right block of queries. And we pass it to this inner loop, to which we pass the output, so where it should write this output, the Li and Mi, which are the statistics for the rows, and so the maximum for each row of each query, and the Li, which is the normalization factor for each query. And the query block, this program should be working with the beginning of the key and value block pointer, because we need to iterate through them. So we just point it to the beginning, and then inside the inner for loop we will iterate through them. Then the softmax scale that we should use when computing query multiplied by the transpose of the keys. The block size, so how many queries we have in each block of Q, and how many key and value we have in each block of KV. This is a stage that tells us what if we are on the left side of the diagonal or on the right side of the diagonal, so it will tell us if we need to apply the causal mask or not, based on where we are, and if we need to apply the causal mask. The offset Q and the offset KV are just the offsets of the query and key inside of each Q and KV block, which is a list of indices that tells us how many queries we have. And then the sequence length, the entire sequence length, because in the for loop we need to iterate to all the sequence length block by block. So block of KV, block of KV, block of KV. All right, let's write this method. Let's write this method, and later we actually need to continue this method again. So let's go, and let me go here. All right. So this method we have already seen the signature, so it's just another kernel, so it can be called by the first kernel. And this is something you can also do in CUDA. You can actually call one CUDA kernel from another CUDA kernel. And then we, based on the stage of this inner loop, we decide what we need to do. So when we are using a causal attention, so we only want to apply the attention to the queries for which the index is less than or equal to the key. So we only want the query to never attend to key and value that come after it. Then we pass the value 3 for the stage parameter. Now, when we, in the causal case, this will become 4 minus 3, it is equal to 1. So what will happen is that we will only work with the range of keys and values that are from 0 up to the current block of Q. So all the keys that whose index is less than the index of the queries we are working with. So to the left part of the causal mask. Let me draw it. Otherwise, I think it's gonna be very difficult to follow. So let's do it actually. So let's open a new one and let's go here. All right, so we have been using this one before, so we can do it again. Clear page. All right, in this now I want you to think of the following matrix as a block matrix. So let's draw it in pink because I have been drawing it all in pink. We know that in the rows of this query multiplied by the transpose of the keys, we have the queries, blocks of queries. So we are not watching one single block, we are watching all the blocks right now. So this is the query block 1, this is the query block 2, this is the query block 3, this is the query block 4. Each of this query block is made up of multiple tokens of queries. And then we have the key blocks. Let's do it like this. Very ugly, but okay. Key 1, key block 2, key block 3, key block 4. When calculating the attention, when you calculate the causal attention, so like with the causal mask, you want only the query to attend to keys that come before it. So when we apply the causal mask, this stuff here will be made up of zeros. This stuff here will be made up of zeros. This stuff here will be made up of zeros. And this stuff here, and this stuff here, and this stuff here, all made up of zeros. We never have to mask out anything when we are in this case because, well, when we are in this particular scenario, actually. In this particular scenario, we don't need to mask out anything for sure. Why? Because all the keys in this block, so in this block of keys, will have an index that is smaller than the index of the corresponding queries, in case the block size of the query and the key matches. So imagine each query is made up of 3 queries. So each block of query is made up of 3 queries. So this is the query number 0, 1, and 2. This is the query number 3, 4, 5. 3, 4, 5, yeah. This will be the number 6, 7, and 8, and this will be the query number 9, 10, and 11. In total, we have 12 queries. We will have the same indices also for the keys in case we choose the same size for the blocks. So this key block here will be the key number 0, 1, and 2. This will be the key number 3, 4, 5. This will be the 6, 7, and 8, etc., etc., etc. Now, what happens is that in this case, as you can see, the key indices of the keys are always smaller than the indices of the queries. So we don't need to mask out anything, even in the case of the causal mask, because we are sure that in this case, all of these dot products will never be masked out. Also in this case, all these dot products will never be masked out, and also in this case, will never be masked out, will never be masked out, and will never be masked out, and in this case, however, along the diagonal, some of the queries will be will have an index that is bigger than that of the keys, and some of them will not have an index that is bigger than that of the keys. Because these are blocks of queries and blocks of keys, some of them need to be masked out and some of them don't need to be masked out. So we are dividing our for loop into multiple steps. The first step that we are doing is all to the left of this diagonal, in which we don't need to mask out anything. Then we will see another step here in which we need to mask out, and then everything to the right of this we will not even compute in the case of causal attention, because we already know it's made up of 0, so it will not so the product query multiplied by the transpose of the keys after the softmax will be made up of zeros. So if you look at the flash attention algorithm, so this stuff here, the contribution will be 0, because we are multiplying 0 with v, it will be 0, so we don't need to change the output. So why even compute this part of the matrix if we already know it's not going to contribute to the output? So we just skip all those iterations. And this is why we are splitting the for loop. I hope now it's much more clear. All right, so let's go back. Okay, so we are now to the left part of the diagonal in case of the stage number 1. In the case of the stage number 2, it's the part exactly on the diagonal, so in which we need to do some dot products and some other dot products we don't need to do. And then for the non-causal attention, we just go through from 0 to the sequence length without doing this multi-step. Because we don't need to mask out anything. So this is why we have this stage. This tells us what is the lower and higher index of the key block that this particular stage should be working with. All right. Now, this function here, multiple of, is just telling Triton that this number here is a multiple of this number. So Triton can make some optimizations. So the stage 1 happens when we are doing a causal attention. So stage number 3 in this function, and 4 minus 3 will become a 1. So imagine we are in the causal attention. We will go through the key and value block that are to the left of the diagonal with respect to the query block that we are working with. In the case we are doing not causal attention in this first call to the inner function, the stage will be 1, so the 4 minus stage will be equal to 3, so we will execute this part of the if statement, so we will go through all the key and values. In case for the causal attention only, as you can see here, we will do another iteration here that will only be done along the diagonal, in which we need to mask out something and we don't need to mask out something, because inside of each blocks there will be some keys that have the index below the index of the query and some that have above the index of the query. So only in the causal attention we will call this function twice. The first time with stage equal to 1, and the second time with stage equal to 2. And the second time we will only iterate through the group of key V blocks that are exactly on the diagonal of the matrix query multiplied by the transpose of the keys, the big matrix that is made up of all the blocks. All right, now that this should be clear, let's proceed further. So let's, because we need to do the for loop, the inner for loop of the flash attention, let's go and load the first blocks of key and values, which is exactly the one that the key and V blocks are currently pointing at, which is the 0, 0 block. So we define the pointers, basically. We point the key and value blocks to the first key and value block that this for loop should be working with, which will be based on the stage. So if it's the first call to this function, they will be pointing to the first block in the case of the causal and not causal. If it's the second call to this function, which only happens in the case of the causal attention, they will be pointing exactly to the key and value block to the diagonal. All right, then we need to make the for loop. So let's loop over all the for loop. So let's do it. So loop over the key and value. And what we do is, okay, we let the compiler know that this number here, the start kv, will always be a multiple of the block size kv, because we will be moving from one kv block to the next kv block, block by block. So we let the compiler know that this number here, start kv, is a multiple of block size kv. It doesn't change anything from a logic point of view. We are just giving some hint to the compiler so it can do some other optimization that Triton does. Now, the first thing that we see in the flash attention algorithm is we need to compute the product of the query. So this is the particular block of the query that we are working with the current kv block in this iteration. So let's do it. So we compute k and v. So we load the query have already been loaded by the caller of this function. We have loaded it here. We have already loaded the query, but we need to load the current block of k. So we load the current block of k, indicated by the k pointer, and we do the matrix multiplication of the current block of query, the block of query with the current block of k, which is already transposed, because when we loaded this k, when we defined the k block pointer, we defined it already with the stride changed, so we are reading the tensor already transposed. So we are doing the query multiplied by the transpose of the keys, basically. Okay, now let's do here, this part here, basically saying, okay, if the stage is 2, when the stage is 2 is when we are exactly on the diagonal. We know that some of the queries will have an index that is bigger than that of the keys, and some of them will have an index that is smaller than that of the keys. So we need to apply the causal mask only in this case. So basically what we do is we define the mask that we should be applying. So the mask will mask out all the values for which this mask is not true. So when this mask is true, when the index of the query is more than the index of the k and v's. And we apply the softmax scale. So as you remember, here we only computed query multiplied by the transpose of the keys, but we also need to divide by the square root of head dimension, and we do it here. And then because we already computed the product, we can calculate the maximum for each row, and then we subtract, because when later in the flash attention algorithm we have another operation which is which I call the softmax star. And as you remember, the softmax star needs to do each element of the S matrix, so the query multiplied by the transpose of the keys, minus the maximum for each row. So we can already compute the maximum for each row. And we can also, before computing the maximum for each row, we need to mask out all the elements that will be masked out in the stage number 2, which is along the diagonal. And how to mask out? We just replace with -infinity before applying the softmax all the values for which the mask is false. So right now we have computed what? We have computed the query multiplied by transpose of the keys. We have masked out in case we need to mask, and when we need to mask, only when we are along the diagonal. In all the other cases, we don't need to mask out anything. We just multiply by the softmax scale, and then we subtract the Mij. The Mij is the maximum value for each row, because we need to compute the softmax star operation, which is the softmax without the normalization, which in the flash attention algorithm is exactly this operation, which will produce the Pij. Okay, so let's go here. So now we can compute the Pij block, which is this stuff here, which is the exponential of the query KV block variable here, which have already subtracted the m. So we have already subtracted this mi at the previous instruction. So now we can just apply the exponential. And this is what we are doing here. Okay. Then we need to compute the sum of the rows for the normalization factor. So for the current block, we will have a list of we will have the Pij block for the current KV block. To compute the normalization factor for the softmax, we need to keep summing up these exponentials, and later we will fix the exponentials, the normalization factor that we computed at the previous step, but we will do that later. So now we just computed the normalization factor for the current block, which is just the sum of all the values on a single row. Which is the same as what we did before here, as you can see here when I show you the algorithm. So for each block we do the row sum, as you can see here, of the P matrix. What is the P matrix? Is the exponential of the S minus M. And for now we didn't apply the correction to the previous block. That's it. So we computed the Lij for the current K and V block, and then we computed the correction factor for the previous block. So the correction factor for the previous block, if you remember the formula from the paper, is this one, is the exponential of the previous estimate of the maximum minus the current estimate of the maximum, which is exactly this one. So the previous estimate of the maximum minus the current estimate of the maximum. We will see later why Mi is the previous estimate of the maximum and Mij is the current estimate of the maximum, because it is coming from the current block that we are computing. Mi is the, let's say, the one that it is the one of the previous iteration, because later we will override Mi with Mij. But I'm just following the flash attention algorithm so far. So I'm computing the correction factor of the previous Li, which in the flash attention algorithm is, let me show you this stuff here. So it is this stuff here, this one here. Okay, and then we apply it. So apply the correction factor. So we apply it. So we apply the previous Li with the correction factor plus the current Li, which is the one coming from the current P block, the one that we computed with the current K and V with the current iteration. And right now we are doing this operation. So Li is equal to the previous Li multiplied by the correction factor. All right, and then what we need to do, okay, we need to, as you remember, the formula is we calculate the P block and then we need to multiply by the V block. So we need to load the V block. So let's load it. We load the V block based on the pointer of the V block to which this to which the pointer V is pointing to at the beginning of this iteration. In case we are in stage number 3, so in case we are doing, for example, not causal attention, it will be pointing to the first KV block, V block. And then, okay, here there is just a type conversion, so we make sure this is in floating point 16. And then we compute the output block. So we are computing the following. So we just take a V, P multiplied by V, and we add it to the output. And this is what we are doing here. We take P, we multiply it by V, and we add it to the O block. Let's go actually to this line one by one. So first of all, we need to fix the previous output block with the correction factor that we have here. So we can fix the previous block with this alpha term here, which is the correction factor for the previous block. And so we just fixed the previous block for now, but we didn't add the new PV. So to add the new PV, we do the dot product of P and V, and this third argument tells the dot, not dot product, it's actually the matrix multiplication, tell this matrix multiplication to use this element here as the accumulator. So this is exactly the same as doing P block multiplied by the V block, O block plus equal to P block multiplied by the V block. This is just optimized because anyway this dot function here needs some place where to store the intermediate results, so why not just store it where it should actually go. And because it the matrix multiplication is just a dot product and the dot product is just a repeated sum, this accumulator will be this dot will keep summing the result to this block here, which will exactly result in this instruction, like we have done the matrix multiplication separately and we added it to the O block. So this is that's why this argument is called the accumulator. All right, so we have also computed the output, and then we save the new estimation of the maximum for the current iteration, and it becomes mi. So at the next iteration we can use it to calculate the correction factor. And then we have finished for the current block, and then we can move on to the next block. So we advance our K and V pointers by one block of K and V. We advance it differently because we know that the V block is a pointer to a tensor of shape. Let me write it here. This is a tensor of shape sequence length head dim. So we need to increase the sequence length by 1 kV, the block size kV, while the K block is actually the K transpose block. So we need to, and it is a transpose because we have exchanged the strides and the shape. So it is head dimension sequence length. So we don't change the head dimension, we just advance the sequence length by sequence block size kV. So basically we are just going to point to the next block of K and to the next block of V. I hope you were able to follow the algorithm of the flash attention. I try to use the same names, I try to use the more or less the same logic, and always writing the formula that I am referring to. So hopefully you didn't get lost. I think the only difference that there is between the flash attention algorithm as written on the paper and this code is probably this alpha, which is the correction factor, but I hope it's easily understandable. Anyway, then we just return the O block. So O block Li, which is the normalization factor for each row in the current output block, which is also a Q block because we are working with one Q block independently from the other programs, and Mi is the maximum value for each row, which will be needed for the backward pass, because when in the backward pass we will compute the Q query multiplied by the transpose of the key block on the fly. We need to also apply the softmax, but instead of recomputing this stuff, which we already computed during the forward pass, we just save them and reuse them during the backward pass, which will save us some computation. Now I know it's time to talk about the LogSumExp trick because we are going to use it. So let's go back to the old method. So let's go here. All right, so we have computed 2 calls of this function in case we are working with causal attention. In case of we are computing causal attention, we call this function once to work with all the query blocks that are to the left side of the diagonal of the query key matrix. Then we do another call of this function to work only with those blocks of keys that exactly lie on the diagonal of the query key matrix. Because in this case, some of the values need to be masked out and some of them do not need to be masked out. Moreover, by doing this, we can avoid computing the dot products for all those values in the causal case for which the index of the key is higher than the index of the query, saving some computation, because anyway they will be resulting after the softmax in zeros and they will not contribute to the output. So it should be faster. Okay, now let's go back to this method here, so the calling method, and there is one last thing that we need to do, which is we need to compute the LogSumExp, and now I will show you what is it. So in order for the backward pass to recompute the softmax without having to recalculate the normalization factor and the maximum value for each row, we should be actually saving 2 different stuff. One is the maximum for each row in the query block, and one is the normalization factor for each query in the query block. However, there is a trick, and the trick is, okay, it's not really called LogSumExp trick because the LogSumExp trick is used for another purpose, but let's call it LogSumExp trick number 2. So the LogSumExp trick number 2 is something as like this. So let me open the slides. So when we do query multiplied by transpose of the keys, we get a matrix that is made up of dot products, so something like this. Like this is one dot product, so let's call it query 1 transpose the key 1, query 1 transpose the key 2, this is a query 2 transpose the key 1, and this is a query 2 transpose the key 2. Then we need to apply the softmax, right? So the softmax is what? Is the let's write the formula of the softmaxes for each of these vectors. So this is a vector and this is a vector because we applied it by rows. For each of these vectors, it will modify element-wise each element as follows. So the softmax of xi is equal to the exponential of xi minus, oh my god, I didn't leave enough space, so let's move this stuff here, back. And this stuff here, little left. All right, it will be the softmax of the exponential of each element minus the maximum for the current vector to which we are applying the softmax, divided by the normalization factor, which is the summation over all possible j's, where n in this case is equal to 2 because we have each vector is made up of 2 elements, of the exponential of xi minus x max. Now, imagine we already have x max and we already have this summation. In the flash attention algorithm, in the forward pass, this stuff here is called Li and this stuff here is called Mi. What we are going to save in the code you can see here, we are saving actually not Mi and Li separately, we will be saving Mi plus the logarithm of Li. So we are going to save Mi plus the log of Li. So what will happen is that when we will compute the backward pass, we need to recreate this matrix here on the fly, which means that we need to recompute the query multiplied by the transpose of the keys, and then we should apply the softmax. To apply the softmax, we should need this stuff and this stuff here. But we have only this stuff here, so this is the Mi plus the logarithm of Li. So when we're computing the softmax, we will compute the following. So we will compute the softmax as follows. We will define, let's call it a new softmax. So let me use another color here. We will apply the softmax as follows. So softmax of xi. Let's call it the softmax 2 because it's I don't want to confuse it. Softmax is equal to the exponential of each element minus, we will subtract this value here. the one corresponding to the current row to which we are applying the softmax. So it will be the exponential of xi minus mi minus the log of li. If we expand this expression, this will become the exponential of, because the exponential, the sum of the exponential of the sum is equal to the product of the two exponentials. We can also write it like this, so it will be the exponential of xi minus mi divided by the exponential of the log of li, which, guess what? It is equal to the exponential of xi minus mi divided by li, which is exactly the normalization factor, and we also have mi. So instead of saving two values, we save only one value, and when we apply it, the exponential's properties will take care of actually also normalizing each value to which we apply it. If you don't remember the properties of the exponential, it is very simple. So the exponential of a plus b is equal to the exponential of a multiplied by the exponential of b, and the exponential of a, not exponential, it's the exponential, a minus b is equal to the exponential of a divided by the exponential of b. And this is the trick that we're using. So that's why we don't need to save two different values, we just need to save one value, and then when we apply it, it will automatically be take care of normalizing because of the properties of the exponential. All right, let's move forward. So we have also created this value that we will use during the backward pass. Now, as you remember, in the flash attention algorithm, we don't normalize each block while computing it, we normalize the output at the end. And this is exactly what we are going to do here. So we normalize the block at the end after we have computed all the normalization factors that we need for all the rows that belong to the current output block. We save this mi, so we save it, this mi is what? Is the normalization factor and the maximum for each row that we will need for the backward pass. So we need to save it in a tensor that we will use during the backward pass. So we need to understand which tensor is this, and it's the tensor that we called M, which is a tensor of a batch size, num heads, and sequence length dimensions. So we need to select the right point in this tensor to select to where we should save these mi values. So we need to select the right batch size index and the right number of head index. So we advance this pointer by the following offset, which is m plus the index batch head, because each index, the index batch head is what? Is the index of the current program that includes information about which head we are working with and which batch we are working with. Because each of these, for each batch and for each head we have a sequence length, we can skip a number of sequence length based on which index is, what we are doing is basically we are skipping for each batch and for each head we will have a sequence length, because each token in the sequence has a maximum value and each token in the sequence will have a normalization value. So based on the current combination of batch and head, we can skip a number of sequence length that other programs will process. So because in this tensor we have the sequence length as the last dimension, and we have what is the combined index of the batch size and number of head size, we can skip a number of sequence of length based on the combined index, which is given by the program index number 1, which is the index batch head that we have here. And this is why we skip here a sequence length number multiplied by the index batch head. This m is pointing to the first element of the entire tensor. So we are skipping the heads and the batch based on the combined index batch head that this particular program is working with. And then we have off skew. Off skew is because each of these kernels, the attention forward method, will work with one query block. each query block has some indices for the exact queries it includes. And this is given by offSkew variable that you can see here, which is how many blocks of queries we need to skip because they will be processed by other programs, plus the range of queries that this particular, that a particular block of queries has. So imagine this particular program is working with the queries that go from, I don't know, from 12 to 16, then this will be 12, 13, 14, 15. So the normalization factor and the maximum value for each row, we only have that for this indices of queries, so 12, 13, 14, and 15. And that's why we need to also skip the number of queries that this particular program worked with, which is already included in this offSkew variable. All right, so now we can store the MI, so because we have the pointer to where it should be saved, and we can also store the output, which was computed by our inner for loop. And this, guys, is the forward step of the flash attention. Now we should go forward, which is we should compute the backward pass. We also have all the ingredients for computing the backward pass because we have already seen this trick, which is the LogSumExp trick. So we already know what how to use it to compute the query key block during the backward pass on the fly. What we miss to understand the backward pass? Well, we need to understand first of all, what is the backward pass? Why do we even need a backward pass? We need to understand what is the Autograd of PyTorch, how does it work, how to compute the gradient, what is the gradient, how to compute, what is the Jacobian when computing the gradient on the backward pass, do we even need to compute that? So we need to derive all the formulas of the backward pass by hand. So if you are in for the challenge, let's continue. All right. So now, before looking at the flash attention's backward pass at the algorithm, we need to understand why we even need a backward pass. And to understand why we even need a backward pass, so before looking at the Autograd of PyTorch, we should be looking at what are derivatives, what are gradients, what are Jacobians, so that when we talk about derivatives, gradients, and Jacobians, we don't feel lost. So I will do a very fast, let's say, rehearsal of what these topics are. Now, what is the derivative? When you have a function that takes as input a real value and outputs a real value, we talk about derivatives, which is defined as follows. The derivative of the function with respect to its variable x is defined as the limit for a step size that goes to 0 of the function evaluated at x plus h, so x plus the step size, minus f evaluated at the x at x divided by the step size. So intuitively we are saying is the ratio of how much the output change for a small change for how much the input has changed in the function. This also gives you the intuitive intuition of why the gradient is the derivative is also the tells you the inclination of the tangent line of the to the function at the point in which it's evaluated. I will use also the following notation to denote the derivative. So the derivative, I am used to write it as like this, so f prime of x, but it's also possible to write it as a d of f of x with respect to dx, or d of y, where y is the output of the function with respect to x, and they are all equal to the same thing, which is the definition above. If we invert this formula here and we take h to the left side, we can also write the follows. So if we want to evaluate the function at the position x plus h, we can also evaluate it as f prime of h, so the derivative of the function in the point x multiplied by h, which is the step size, plus f of x. This is actually also how we derive the Euler rule for computing the differential equations, but that's not the topic of today. So this h, we can also call it delta x. So f of x plus delta x is more or less, because here we have a limit that says when this only happens when h is very, very, very small. So that's why we put this more or less, approximately. So f of x plus delta x is more or less equal to f prime of x multiplied by delta x plus f of x. This you can also read it as follows, that if by inverting this formula, if x changes by a little amount, and this little amount is delta x, how much y will change? y will change by this exact amount, which is the derivative of y with respect to x, so dy with respect to dx, multiplied by how much x has changed. So this dy dx tells us how much y will change with a small change of x. If we multiply with the actual change of x, it will tell us by how exactly y will be affected. I don't want to stay too much on this, but I would like to use this intuition to introduce the chain rule. Because imagine we have a function of a function. So imagine we have z is equal to f of g of x. We can think of x being mapped into a variable y through the function g, and then y being mapped into a variable z through the function f. If x changes by a little bit, and by a little bit I mean delta x, how much y will change? Well, y will change by delta y. What is delta y? Delta y is the derivative of y with respect to x multiplied by the step size of x. But if y changes, it will also affect z, because there is a direct mapping between y and z. So how much z will change for a small change in y? Let's see. So if y changes from the old y by a small step delta y, then z will also change by some delta z, and this delta z is the dz on dy multiplied by delta y. If we replace this delta y with the delta y that we have computed in the expression above, we arrive to the chain rule. It will tell us how z will be affected. So this is delta z. What is the effect on z for a small change on x? And it's the product of the two derivatives, the one of y with respect to s and one z with respect to y. And this is the chain rule that we study in high school. So it is, if you want to compute dz on dx, it is dz on dy multiplied dy dx. Which is very intuitive if you think about the following example. So you can think of z as the price of cars and x as the price of the oil. How much will a small change in the price of oil affect the price of a car? Well, the small change in the price of the oil will affect, for example, a variable y, which could be the price of electricity. So if how much the price of electricity will affect the price of a car, it's through the derivative of the price of the electricity with respect to the price of the car with respect to the electricity. So to get the effect of the price of oil on the price of the car, we just multiply the two effects. And this is the intuition behind the chain rule. Anyway, let's talk about gradients. So when we have a function that as input takes a vector and produces a scalar, we talk not anymore about derivatives, we talk about gradients. So imagine we have a function that takes as input a vector made up of 2 dimensions, but n dimension in general, and it produces a scalar. When do we have to deal with this kind of function? For example, loss functions. Loss functions are something that are always a scalar as output, and as input they take tensors. So, for example, imagine the cross-entropy loss. It will take a sequence of tokens, each tokens with its own logits, and it will compute one single number, which is the loss. So, how to view the effect on the output with respect to the input in this case? Well, if x changes by a little amount, and this little amount is not anymore a number, but it's a vector. So if changes the old x plus delta x is a vector sum, then the y will also be affected by what? Y will be affected by dy on dx multiplied by delta x. However, this delta x is not a number anymore, it's a vector, because x1 may change by a little bit, x2 will change by a little bit, x3 will change by a little bit, x4 blah 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 until xn will change by a little bit. So this is actually a dot product of this vector multiplied by this vector. Why a dot product? Because y will be affected by the change in x1, it will be affected by the change in x2, it will be affected by the change in x3 up to xn. And each of the contribution of x1 will be the partial derivative of y with respect to x1 multiplied by how much x1 has changed, plus the contribution of x2 will be the partial derivative of y with respect to x2 multiplied by how much x2 has changed, blah, 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 until the last contribution of xn. So, and the chain rule in this case also applies in the same way as in the scalar case. So the formula does not change also for the change rule here. I just want you to remind you that in this case we are talking about a gradient, and the gradient is just a vector made up of all the partial derivatives of the output with respect each of the input variables that are in the input vector. When we talk about a function that have as input a vector and produces a vector, then we don't talk about gradient anymore, we talk about Jacobians. So if our input x, the input x of this function changes by a little amount, and this delta x is a vector, then the output y will also change. And this output y will change by a delta y that is not a number anymore, it is a vector. And this vector is the result of this quantity dy on dx multiplied by delta x. Delta x is a vector. So this one has to be a vector, this one here has to be a matrix, and this matrix is called the Jacobian. It is a matrix that has as many rows, later we will talk about the notations, so it has as many rows as there are output variables and as many columns as there are input variables. The first row will be the partial derivative of the first output variable with respect to all the input variables. The second row will be the partial derivative of the second output variable with respect to all the input variables, and the last row will be the partial derivatives of the last output variable with respect to all the input variable in the input vector. Now let's talk about the notations. The Jacobian that I have written here is written according to the numerator layout. This is called the numerator layout, and there is another convention called the, not layout, sorry guys, it's called the numerator convention. And there is another convention called the denominator convention or notation, in which the rows are not the number of rows is not the equivalent to the number of output variables, but equal to the number of input variables. So the fact that I have, we choose to write the Jacobian as follows is based on a convention. You can also write the Jacobian according to the denominator convention just by transposing this Jacobian here. And also the formula for the chain rule changes accordingly. For now, I want to keep the formula for the chain rule just like the one for the scalar case, so that's why I am using this notation here. But later we can change between one notation to the other just by doing a transposition. Okay, now that we have reviewed what is a derivative, what is a gradient, and what is a Jacobian, let's talk about what happens when we take derivatives with respect to tensors, of a tensor with respect to another tensor. In this case, we talk about the Jacobian, but it's called the generalized Jacobian. So if we have the function that is as input takes a tensor of dx dimensions, where the first shape, this is kind of the shape of the tensor, so the first element of the shape is n1, the second element of the shape of the input vector is n2, etc., until n dx, and it produces an output tensor that has this shape, so m1, m2, blah, 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 m dy. In this case, the formula for the chain rule doesn't change, and if x changes by a little amount, so by delta x, which is a tensor, y will also be affected by how much? By dy on dx multiplied by delta x. And this is a tensor product. It will be a Jacobian. This is called generalized Jacobian with the following shape. So all the dimensions of the output multiplied by all the dimensions of the input. Alright, this is very abstract. For now, we will see actually a concrete case of this one, because we will be deriving the gradient of the output of a matrix multiplication, the gradient of the loss when computing backward pass with respect to each of the input of the matrix multiplication operation, and we will do it also for the softmax, and we will do it also for the attention. So I don't want to jump to too many topics. I just wanted us to get into the right mindset. So we know that derivatives when we have scalar functions, gradients when the output is a scalar, input is a vector, Jacobian when the input and output are both vectors, generalized Jacobian when the input and the output are tensors. The chain rule always works in the same way. Alright, let's talk about autogradient. I will do the scalar case and then we will extend it to the tensor case. So imagine we have a very simple computation graph. Why we have computation graph? Because we are talking about neural networks, and neural networks are nothing more than computation graphs where we have some input, we have some parameters, and we do some operations with this input and parameters. Suppose that you have an input A, and this input A is multiplied by a weight, the parameter weight is just a scalar, and it produces an output y1. This y1 is then summed up with another number called b1, and it produces y2. This y2 is then raised to the power of 2, so this is z to the power of 2 is just the power of 2 of the input, and it produces y3, and this y3 becomes our loss function. So it's a scalar. Now, what we want to do to apply gradient descent is we want to compute the gradient of the loss function with respect to each of the input of this computation graph. So each of the leaves of this computation graphs, what are the leaves? It's this node here. So the parameter nodes and the input nodes. And to do that, there are two ways. One is if you have access to the expression that relates directly the input to the output, so to the loss, then you can directly compute the gradient, the derivative in this case, because it's not a gradient, it's a scalar versus scalar. So in this case, imagine we want to compute the derivative of the loss with respect to W1. Imagine we have access to the exact expression that relates the W1 to the phi, which is our loss. We can compute it as follows. So we just derive this expression with respect to W1, which is 2 times, because this is the power of 2 of a function. So it is 2 multiplied by the function multiplied by the derivative of the content of this function with respect to the variable that we are deriving. So it will become the following expression. There is another way, which is by using the chain rule. So we can use the derivative of phi with respect to w1 is the derivative of phi with respect to y3, which is the previous output of the previous node, then the derivative of phi3 with respect to the output of the previous node. So and then multiplied by the derivative of y2 with respect to the output of the previous node, and then the derivative of y1 with respect to w1. If we do all this chain of multiplication, we will obtain the same result. And you can see that here, this stuff here is exactly equal to this stuff here. By doing this procedure here, we will note something. That is, I want to zoom out a little bit. Okay, to compute the derivative of phi with respect to w1, we are doing all this chain of multiplication. But what is each item in what is each factor in this sequence of multiplications? Well, this stuff here is nothing more than the derivative of phi with respect to y2. These multiplications here are nothing more than the derivative of phi with respect to y1. And all of them combined are the derivative of phi with respect to w1. What PyTorch will do, it will do the following. PyTorch will do the backward pass because PyTorch knows what is the computation graph that relates the output, so the loss function in this case, and the variable for which we want to compute the gradient. Right now we are talking about derivatives, so it's not gradient, but the mechanism is exactly the same. So PyTorch will say, PyTorch is like a person that knocks the door of this operation and says, hey, operation power of 2. If I give you the gradient of the loss with respect to y3, which is 1, because loss and y3 are actually the same, can you give me the gradient of the loss with respect to y2? Because PyTorch actually does not implement an Autograd system in the sense that it does not know the symbolic operations that led to the output. It just knows what are the functions that computed the output, and each function has a function. Each function is a class in Python that implements 2 methods. One is the forward step and one is the backward step. The forward step takes the input, so in this case y2, and computes the output y3. The backward step will take the gradient of the loss with respect to its output and needs to compute the gradient of the loss with respect to its input. How can we do that? Well, it's very simple, because PyTorch will knock the door as, let me copy it, this stuff here, otherwise it's not easy to go back and forth. So, okay, and let's paste it here. PyTorch will knock the door of this function here and will say, hey, if I give you the loss of the gradient of the loss function with respect to your output, can you give me the gradient of the loss function with respect to your input? Yes, the function can do it. Why? Because of the chain rule, this operator here, this function here, can just take the loss, the gradient of the loss function with respect to its output, multiply it by the Jacobian, or in this case the derivative of its output with respect to its input, and it will be equal to the gradient of the loss with respect to its input. Then PyTorch will take this one and knock the door at the next operator, which is this one, this summation, and will say, hey, if I give you the gradient of the loss with respect to your output, can you give me the gradient of the loss with respect to your input? Yes, this operator can do it, because this operator just needs to apply the chain rule. So it will take the gradient of the loss with respect to y2, which is provided by PyTorch, and by multiplying it with the Jacobian, in this case it's the derivative of its output with respect to its input, it can compute the gradient of the loss with respect to its input. Then PyTorch will take this output of this backward pass and will knock the door of the next operator, which is this product, and will ask again the same question. Hey, if I give you the gradient of the loss with respect to your output, can you give me the gradient of the loss with respect to your input? Yes, this will do the same exact job. It will take the gradient of the loss with respect to the output, multiplied by the Jacobian of the output with respect to the input, and obtain the gradient of the loss with respect to the input. And this is how PyTorch runs the backward step. It runs one operator at a time backwards in the computation graph, knocking the door of each operator and asking always the same question. If I give you the output, the gradient of the loss with respect to your output, can you give me the gradient of the loss with respect to your input? And each operator will just apply the chain rule to get this gradient, to calculate this gradient that PyTorch needs. Why PyTorch cannot do it by itself? Because PyTorch does not do symbolic mathematics. It does not have access to the exact expression that each function is computing. It just uses the function as a black box that computes forward and backward. However, with the Jacobian, we have a problem, and let's see what is the problem. All right. So up to now, we have been working with a computation graph that is made up of scalars, but the things that we have said, they work in the scalar case, but also in the tensor case. So let's go back, see what is our computation graph. We have seen that PyTorch will go operator by operator, asking always the same question. If I give you the gradient of the loss with respect to your output, can you compute me the gradient of the loss with respect to your input? And each operator can just apply the chain rule to compute that. Imagine now that all of these operators are working not with scalars but are working with tensors, which means that the derivative of the output with respect to the input of each operator is not a derivative, it will be a Jacobian, because the output will be a tensor, a generalized Jacobian, and the input will be a tensor. Which means also that this quantity here, so the derivative of the loss with respect to the input in this case, will not be a derivative, it will be a gradient, because the output, the loss is a number always, while the input in this case, y1, will be a tensor. So number output input is a tensor, then we talk about gradients. So this will be a gradient, and we will call it the downstream gradient that the operator needs to compute. This will be the upstream gradient that PyTorch will give to each of these operators. So the gradient of the loss with respect to the output of each operator. And each operator needs to come up with this downstream gradient by using the Jacobian. However, the Jacobian has a problem. Let's see. So imagine we are implementing a simple operation that is the matrix multiplication. And the matrix multiplication takes as input a X tensor, it multiplies it by a W matrix made up of parameters and produces a Y matrix as output. Suppose that X is, let's call it N by D matrix, W is, let's say, D by M matrix, and so Y will be a N by M matrix. Usually the input X is a sequence of let's say vectors, each with d dimensions. So you can think of it as a sequence of tokens. Each token is a vector made up of d dimensions. Usually we have many tokens. So suppose that n usually is at least 1024, at least in the most recent language models. We even have millions of tokens actually. So, and D is also actually quite big. Usually it is at least 1024 also. So also this one is 1024. D and M is also at least 1024. So we can actually become 2048, let's say. So I like the powers of 2, by the way. So the problem of the Jacobian is this: if we want to compute this downstream gradient by multiplying the upstream gradient with the Jacobian, this Jacobian matrix is huge, because look at the dimensions here. This will be a matrix that is, it will be, well, n by m multiplied, so it will be a generalized Jacobian, so it will be a tensor that has a shape nm. And then the input is x, so it is n by d. So how many elements it will have? Well, it will have 1024 multiplied by m, which is 2048, multiplied by 1024, multiplied by d, which is 1024. So it is at least, wow, it's billions, more than 1 billion elements. So it is impossible actually to materialize this matrix here in the memory, because in the RAM of the GPU, because it will be too big. So, but we need to compute this downstream gradient, because PyTorch needs it to continue calculating the gradient of the loss function with respect to each of the nodes in the computation graph. So how can we proceed? The first thing that we should notice is that this Jacobian is actually a sparse matrix. And I want to show you why it is actually is a super sparse matrix. Because if you look at the input, what is the effect of the input on the output? The input is a sequence of tokens. So this is the token number 1. It's a vector of some dimensions, 1024 dimensions. Then we have another token as input. Then we have another tokens as input. Then we have another tokens as input. And we multiply by the W matrix, which is made up of some columns. So this one is n by d, right? Yes. And the W is d by m. So d by m. This will produce a matrix that is n by m. So it will be also a sequence of tokens, each made up of m dimensions. So it will be a matrix like this. So this will be the first output token. This will be the second output token. This will be the third output token. And this will be the fourth output token. Now, this output row here is the dot product of this input row with all the columns. So the derivative of each of these dimensions with respect to the dimensions of all the other tokens will be 0, because they do not contribute to this output. So the Jacobian will have zeros every time we are calculating the derivative of this first dimension with respect to any other element of other tokens. That's why we always can come up with a better formula for computing this downstream gradient that does not involve the materialization of the Jacobian, because the Jacobian itself is sparse. So let's see how we can optimize this computation without materializing the Jacobian in the case of matrix multiplication, because we need it for flash attention. Alright guys, so before proceeding to the backward, watch the formulas of the backward pass of the flash attention, let's look at how to compute the gradient of the matrix multiplication operation with respect to its input. So imagine we are okay, PyTorch already have actually how to compute the gradient of the inputs of the matrix multiplication with the gradient of the loss with respect to the input of the matrix multiplication operation. But in flash attention, we are creating a custom kernel, which means that the custom kernel is fusing multiple operations into one operation. So when PyTorch will knock the door of our operator, it will ask our operator, which is the Triton attention operator that we have built, what is the gradient of the loss function with respect to q, k, and v, because that's the input of our function. So if we look at the code that we have built so far, you can see that our Triton attention will be a node in the computation graph that takes as input q, k, and v and produces an output. Then PyTorch will give us the gradient of the loss with respect to that output, so it will give us a do, so the derivative of the loss with the gradient of the loss with respect to o, and then we'll ask this class here, so Triton attention, to compute the gradient of the loss with respect to q, k, and v. Because we are fusing multiple operations together, so we are computing on the fly the softmax of query multiplied by the transport of the key, and then multiplying, doing the softmax and multiplying it by v to compute the output. We need to compute these gradients internally to compute this the gradient of the inputs. So, because in these operations that we are doing, fusing together, there is a matrix multiplication, we need to derive by hand the matrix multiplication, the gradient of the loss function with respect to the input of the matrix multiplication operation, so that we can provide it to PyTorch. That's why we need to derive this formula. I will derive it in a very simple way, and then we will do it for the softmax as well, because these are the two things that we need to derive by hand to derive the formula of the flash attention's backward pass. So let's start. Imagine we have a computation graph, a node in the computation graph called the matrix multiplication, and this node in the computation graph is doing a matrix multiplication. So it is computing the following operation: y is equal to x multiplied by w. Now, what PyTorch will give us as input when computing the backward pass of this node, PyTorch will give us the gradient of the loss, so it will give us d phi with respect to dy, so the output of this node, and will ask us to compute the gradient of the loss function, so the gradient of the loss function with respect to dx, and the gradient of the loss function with respect to dw. The easiest one to work with, and the one that I will be showing, and the other one I will not show in the video, but I will attach the PDF slide on how it is computed, because they are very similar in the way they are computed, so I don't want to make the video too long for unnecessary reasons. Let's compute the gradient of the loss function with respect to the input, so with respect to x. Alright, so how to do that by hand without materializing the Jacobian? Because as we have seen, we cannot just use the chain rule by materializing the Jacobian, which would be the easiest way, because the Jacobian is a very big matrix that cannot even fit in the memory of the GPU. So we need to find a smarter way. We exploit the fact that the Jacobian is sparse, so hopefully we will get a formula that does not involve the materialization of a very big sparse Jacobian. Let's see. So when dealing with this kind of derivations, I always recommend to make some example tensors. So suppose that x is a tensor of size, let's say n by d, where n, let's say n is equal to 1 and d is equal to, let's say, 3, and w is a tensor, also or a matrix, with the shape, let's say, d by m, where m is equal to, let's say, 4, and y will have as a consequence the shape n by m. So it will have the shape, 1 by 4. What PyTorch will give us? PyTorch will give us the following quantity. So it will give us this stuff here. So the gradient of the loss function with respect to the output of this operator, which is y. So it will give us a vector, or a tensor actually, with the following dimension, which is n by m. And we need to compute the gradient of the loss function with respect to x, which should be a tensor of shape n by d. Because when dealing with the gradient, it always has the shape of the input variable, because it's the output, which is a scalar with respect to each element in the input. So it has the same shape as the denominator. All right. So when dealing with these kind of problems, I always recommend to create example matrices and then work out what happens to the output, and then try to work out the gradient matrix. So let's do it. So let's see that how is the output computed? Well, the output will be a matrix that is 1 by 4 computed as follows. It will be the input, so 1 by 3. So let's call the input x11, x12, x13. It will be multiplied by another matrix w that has dimension 3 by 4. So it will be 3 rows by 4 columns. So it will be w11, w12, w13, w14, then w21, w22, w23, w24, w31, w32, w33, w34. If we do this matrix multiplication, it will be, well, it will produce the following matrix that is, okay, this is 1 row by 3 columns, this is 3 rows by 4 columns, so the output will be a matrix that is 1 by 4, so 1 row by 4 columns, so it will be, let me write it with a smaller, because otherwise it will never fit here, so let's do it like this. It will be x11 multiplied by w11 plus x12 multiplied by w21 plus x13 multiplied by w31. And this will be the first element of the output. The second element of the output will be x11 with w12, x11 with w12, plus x12 with 12 with w22, plus x13 with w32. This will be the second element of the output matrix. The third element of the output matrix will be, let me move this stuff on the left, otherwise it will never fit. So, okay, I think now it can fit. This will be x, I need also to watch this one, so x11 with w13, x11 with w13, plus x12 with w23, plus x13 with w33, and then we multiply the same row with the last column, so it will be x11 w14 plus x12 w24 plus x13 w34. This will be the output y. If we do the matrix multiplication, what PyTorch will give us, it will give us the gradient of the loss. So it will give us delta phi with respect to delta y. Because it's a gradient, it has the same shape as the denominator, so it has a shape that is 1 by 4. Let's call it, because we don't know what this value will be, they will be provided to us by PyTorch. Let's just give them generic name like dy11, dy12, dy13, and dy14, like this. Now, to compute the downstream gradient that we need to provide to PyTorch, we should be materializing the Jacobian, which is okay. Let's write the chain rule formula. So we need to provide delta phi with respect to delta x, which is equal to delta phi with respect to delta y. This is provided by PyTorch, multiplied by the Jacobian, which is delta y with respect to delta x. Now, instead of materializing this Jacobian, let's try to do this. Let's materialize it now, and let's do the multiplication of these two quantities to see if something simplifies. So this stuff here will be dy with respect to the x, which means the derivative of every output y with respect to every input x. How many output we have? We have 4 elements as the output, which is this stuff here. And we have 3 elements as input in the X matrix. So it will be as follows. I don't know how to... Let me copy it because my screen is not big enough. And I remember that X is X11 and XX2. So delta Y with respect to delta X will have the following entries. So the Y1 with respect to X11, and as you can see, Y1 only has one X11 appearing as multiplied by W11, so the derivative with respect to X11 will be W11. Then Y11, so this stuff with respect to X12, it will be W21. Then Y11 with respect to X13 will be W31. The second row of this matrix will be the derivative of the partial derivative of the second output, so Y2, with respect to all the X inputs, which will be the derivative, partial derivatives of this stuff here with respect to every X, which is W12, W22, I guess, and W32. Now let me check if it's what I'm doing is correct. Yes, because I've already done it, so I can always double check. And then we have the partial derivatives of this stuff here with respect to all the X, which is W13, W23, and W33. Then the partial derivatives of the last output, so Y4, with respect to all the X, which will be W14, W24, and W34. We obtain the following Jacobian. But this Jacobian, as you can see, is just equal to W transposed. So we don't need to materialize the Jacobian. We can just do the multiplication of whatever gradient PyTorch is giving us, multiply it by W transposed, and we will get the downstream gradient. So let me rewrite so we know what we are doing. So d phi on dx is equal to d phi with respect to y multiplied by dy on dx. But we have seen that dy on dx is just equal to W transposed. So this is equal to d phi on dx dy multiplied by W transposed, and this gives us the downstream gradient. So in order to provide the downstream gradient that PyTorch needs, we just need to take whatever gradient PyTorch will give us, multiplied by W transposed, and it will give us the gradient of the loss function with respect to the input X of the matrix multiplication. In the same way, we can also arrive to the formula for the gradient of the loss function with respect to W, and it is equal to X transposed multiplied by d phi with respect to dy. How to remember these formulas? There is a mnemonic rule, which is these are the only possible ways for this to have the shape of X and this to have the shape of W. Because this stuff here will have the same shape of Y, so it will be n by m. This stuff here will have shape of W transpose. W is d by m, so W transpose should be m by d. And the resulting operation of this matrix multiplication or tensor multiplication will be n by d, which is exactly the same shape as X. In this case, we will have that xt is the transpose of t, and it is n by d, so it's d by n, multiplied by d phi with respect to dy, which is a gradient, so it has the same shape as the denominator. So it has n by m. And the output will have shape d by m, which is exactly the the shape of W. So if to remember them, this is the only way this shape work out. Otherwise they don't work out. So this is a mnemonic formula on how to remember how to compute the gradient of the inputs of a matrix multiplication given the gradient of the loss with respect to the output of the matrix multiplication. And the inputs to the matrix multiplication are the input matrix and the parameter matrix W. Now we need to derive the gradient of the output of the softmax with respect to the input of the softmax, because that's another operation that we do in our fused attention, because we are fusing many operations together, which is matrix multiplication and the softmax. So this is the second ingredient that we need to understand the backward pass of flash attention. So let's do it. I will use, to make this derivation, I will use the same notation as in the flash attention paper. So first of all, let's write the title of this stuff, which is the gradient through the softmax. The first operation that we do in during computation of the attention is we compute the product of the query multiplied by the transpose of the keys. We do in a blockwise ways, means that we do it block by block, but it doesn't matter because the end result is the same. So we can write S equal to Q multiplied by the transpose of the keys, and then we apply the softmax to this operation, to the result of this operation, and we call this output P, which is the softmax of S. And after we have applied the softmax, we take the output of the softmax, we multiply it by V to obtain the output. So the output is equal to P multiplied by V. Now we need to understand how to, because as I said before, PyTorch Autograd works in the following way. PyTorch will treat our attention computation as a black box. So we will have a computation graph like the following. We will have a query input, a key input, and a value input, which are sequences of tokens, each one with some embedding dimension. These are fed to some black box called the attention, which is our implementation of the attention, which is the function that we started coding before. This will be fed as input to this node in the computation graph, and the computation graph will output an output tensor O. What PyTorch will give us? PyTorch will give us the gradient of the loss with respect to the output. So, as you remember, PyTorch knocks the door at each operator and says, if I give you the gradient of the loss with respect to your output, can you give me the gradient of the loss with respect to your inputs? And this is what we need to figure out. So, given the gradient of the loss with respect to the output, we need to understand how to compute the gradient of the loss with respect to WQ, the gradient of the loss with respect to WK, the gradient of the loss with respect to WV. However, there is no direct connection between Q and O or K and O, because there are two intermediate operations. So there is first a matrix multiplication, then there is a softmax, then there is an additional matrix multiplication. However, we have tools that allow us to understand how the gradient propagates through multiple operations when they are applied in sequence. And that's called the chain rule. However, we have seen that applying the chain rule in its naive way by materializing the Jacobian is infeasible. So we need to understand how to apply the chain rule without materializing the Jacobian. And that's what we are going to figure out for one of the operations inside of this attention computation, which is the softmax. And that's why we are going to do this derivation, which I promise is the last one that we will do. And then we will finally go to code the backward pass of flash attention. We cannot proceed directly to coding the backward pass of the flash attention, because if we look at the formulas on how it is computed, we will not understand how the derivation comes out. Okay, now we can start. So let me delete this stuff. Delete, and imagine for simplicity, now we apply the softmax to a row-wise to this S matrix. So each row is softmaxed independently from the others. So let's see what happens to one single row of this matrix. And for simplicity, I will call it S. So S is a single row of the S matrix. I could also call it S of I, but if I do it like this, we will have to carry over the index I. Okay, guys, just do it. We will carry over the index. All right, so let's call Si one row of the S matrix. So Si is equal to, let's say it's in tensor notation, PyTorch tensor notation, it will be like this. So from the matrix S, so from the tensor S, we take the ith row and all the columns. This is the definition of Si. I know it's very ugly notation, but it helps you understand. And this is a vector of size and dimensions. We apply the softmax to this vector, and we will obtain an output vector, and we call it Pi. Pi is equal to the softmax of Si. So as we have seen, the softmax operation does not change the shape of the input, it just changes element-wise each number. So the output will also be a vector of size r to the power of n. Now, what is the softmax? So the softmax is defined as follows. The softmax of, Pij, so the jth element of the Pith vector is equal to the exponential of the jth element of the Sith vector divided by a normalization factor that is computed as follows, with, let's say, not j, let's use k in this case, not even k, let's use L is equal to 1 up to n of e to the power of S I L. All right, so first of all, you may be wondering, the softmax that we apply during the forward pass of the computation of the attention is not really this softmax, because if you remember what we applied before, we were applying the softmax where each of the argument of the exponential is reduced by the maximum element in the vector to which we apply the softmax. So it was more or less like this. So Sij minus Si max, so the maximum element in the Si's vector, and also the argument of the denominator was reduced by Si max. However, we also proved that this stuff here is equivalent to the standard softmax without this reduction in the argument, because this reduction in the argument is only added because we want to make it numerically safe to compute, but it's equivalent to do it without, but from a mathematical point of view. On the computer, of course, it will become numerically unstable, but from a mathematical point of view, it is the same thing, which also means that doesn't matter how you compute the forward pass. If it's equivalent to another mathematical definition, you can always use the other mathematical definition to compute the backward pass. It will result in the same value. If you didn't understand what I said, let me give you a more simple example, which is, imagine you have a, do you remember the formula from high school? This one, so cosine of squared of x plus sine squared of x is equal to 1. Now imagine we compute an output y is equal to cosine squared of x, and then we need to compute the derivative of y with respect to x. It doesn't matter if you compute it as the derivative of cosine squared of x with respect to x, or if you compute it as the derivative of 1 minus sine squared of x with respect to x, because they will result in exactly the same result, because the two definitions are equivalent. And this is why we don't need to add this factor in the exponential, because the two definitions are equivalent mathematically. We just use the numerically safe one because when computed on the computer, we need something that is numerically safe, stable, that will not overflow. All right, now what do we want to obtain? So we want to obtain the gradient of the loss with respect to the input vector of the softmax, which is the Sith vector, given the gradient of the loss with respect to the output of the softmax, which is the Pi vector, and we can obtain that with the chain rule, multiply that by the Jacobian Pi with respect to Si. Now, the chain rule is always valid. Let's see what does this Jacobian look like. Alright, so this Jacobian will be the Pi with respect to delta Si. Well, we need to do it. Let's look at what each element in this Jacobian will look like. So the jth element with respect to the, let's say, the kth element. So we are computing we are looking at what each element in this Jacobian will look like, which is what is the Jacobian? It's each element in the numerator of the Jacobian derived with respect to each element in the denominator of the Jacobian in this fraction here. So we are saying for each element in the output vector derived with respect to each element in the input vector. This is what we are writing here. So how is the output vector obtained? Well, Pij, we know that it is equal to, by the definition of the softmax, is obtained as follows. So e to the power of Sij divided by the normalization factor, let's call it L, is equal to 1 to n e to the power of SIL, all derived with respect to SIK. So what we are trying to do is, we know that the P vector is, suppose it's a vector with the 3 elements. So this is a P1, this is a, well, P11, P12, and P13. The S vector will be a vector also with the 3 elements, so it will be the S11, S12, and S13. What we are trying to do is calculate what the Jacobian will be the derivative of this one with respect to all the input vector. Then the second row of the Jacobian will be the derivative of this one with respect to each of these input element. Then the third row of the Jacobian will be this stuff here with respect to derived with respect to each of the input element of the S vector. We are trying to understand what does the generic element in this Jacobian look like based on the j-date element of the output vector. So this j index refers to the output vector, and the kth element in the input vector. Alright, so what can happen when we do this Jacobian is that we have this one here is the derivative of a fraction of 2 functions. And we know from high school that the derivative of the fraction of 2 functions is as follows. So the derivative, let me write like this, of f of x with respect to g of x prime is equal to, with respect to x, by the way, is equal to f prime, of x multiplied by g of x minus g prime of x f of x, all divided by the g of x to the power of 2, like this. Now let's apply it here. So this will become, here we will have 2 cases. Either the variable that we are deriving with respect to, so this SIK, has the same index as the variable being derived. So either we are doing P11 with respect to S11, or we are doing P11 with respect to something else that has not the same index. So like P11 with respect to S12 or S13. So there are 2 cases that we need to consider. Suppose that we are deriving P11 with respect to S11, or we are deriving P12 with respect to S12, or we are deriving P13 with respect to S13. So we are deriving the element of the output with respect to the same element in the input with the same index. So in this case, this derivative will look like the following. So it's the derivative of f, so the numerator, with respect to the denominator that has the same index. So we are saying that in this case, j is equal to k. So the numerator with respect to Sij with respect to e to the power of Sij with respect to Sij will be e to the power of Sij. So because e to the power of x1 with respect to x1 will be e to the power of x1. So this is equal to, I am reducing the size now, e to the power of Sij. Then we need to multiply that by the denominator of the fraction, which is this summation here. So the summation over all possible L of e to the power of SIL minus the derivative of the denominator with respect to the variable being derived. So this denominator is the sum of all the exponentials of all the input elements. If we derive it with respect to one particular input element, there will be at least one term that contains that input element, and so all the other terms will result in 0. So the only derivative that will survive will be the e to the power of Sik with respect to Sik. So we write minus e to the power of Sik multiplied by the numerator, which is e to the power of Sij. All this divided by the denominator to the power of 2, which is this summation here. So L equal to 1 up to n e to the power of Sil, all to the power of 2. And this stuff here will be equal to, well, we can see that these two terms, this one and this one, have a one term factor in common, which is e to the power of Sij, so we can collect that. So e to the power of Sij multiplied by the summation minus e to the power of Sik. All this divided by the denominator, which is the power of 2 of this stuff here. So let me just copy and paste it, which is, let me rotate it also, because I don't know why I always write little, yeah. All right, and this stuff here is equal to, well, we can separate the two terms, so we can separate this term here and this term here, because the denominator is to the power of 2. So we can write it also as e to the power of Sij divided by the denominator, so which is summation of L equal 1 up to n e to the power of Sil multiplied by this stuff here. So this stuff here divided by the same denominator. So there's summation of L equal 1 up to n e to the power of Sil minus e to the power of Sik. I am Sik divided by the same denominator, Sil. Now this one can be written as, this stuff here is nothing more than the output element Pij, because this one is just the softmax applied to the Sij element, which we know that the output of the softmax applied to the Sij element is called Pij, because it's one element of the output vector, which we called P. So this stuff here is equal to Pij multiplied by this stuff here will be equal to 1 minus this stuff here. What is this stuff here? Is the output of the softmax applied to the Sik element, so it will be Pik. So it is equal to 1 minus Pik. Okay, and this is in the case the variable with respect to which we derive has the same index as the numerator in this fraction here, in this derivative here. The other case is when the two variables, so the output, the index of the output with respect to the index of the input are not the same. In this case, we will have another case. So we will have that j, let me write it again. So this stuff here, hope I can copy it all without. In the other case, in which s is not equal to j, not s, it's j not equal to k. So j is not equal to k. What happens? In this case, it will be, well, the derivative of the numerator, because we need to apply again this formula here. So derivative of the numerator with respect to something that is not the same variable, it will be 0, because it's like computing the derivative of e to the power of x1 with respect to x2. It will be 0. So it will be 0. So all the first term here will become 0 no matter what is g of x, minus the derivative of the denominator of this fraction here with respect to the variable sik, g prime of sik. So this is all the variable in the input, and we are deriving it with respect to one particular variable of the input. So only one item in the summation will survive. So it will be the item sik. So it will be e to the power of sik multiplied by f of x, which is the numerator in this fraction, which is e to the power, oh, we forgot a minus, e to the power of sij. Let me see if I forgot something. All divided by the denominator of this fraction here to the power of 2. So it is equal to the summation L equal 1 up to n of e to the power of sil all to the power of 2. I believe I didn't forget anything, so let's continue. So here also we can see that this one here is because, okay, let's separate it, minus e to the power of sik divided by the summation L equal 1 up to n of e to the power of sil multiplied by e to the power of sij divided by the summation L equal 1 up to n of e to the power of sil. This stuff here is nothing more than the softmax applied to the kth element of the si vector. This one here is nothing more than the softmax applied to the jth element of the si vector. So we know what these are. We know that we call them p minus pik pij. So in the end we have two cases. One is the derivative of this stuff here looks like the following. Each item in the Jacobian looks like the following. When the numerator and the denominator have the same index, so j equal to k, this stuff here is equal to, now this notation here is wrong, so I shouldn't be writing it with the equal sign, but doesn't matter, guys. It's, we are doing a little okay, so pij multiplied by 1 minus pik. Let me check. Yes. The other case is when the j is not equal to k, then this stuff here, let me write it like this, will be equal to minus pik multiplied pij. Now that we know what the two typical cases of this Jacobian look like, let's actually look at what this Jacobian look like in the matrix form. So this Jacobian will look like the following. It will be a matrix that is more or less like the following. It will be an n by n matrix where n is the size of the input vector and the output vector. And here, the first element of the Jacobian, as you saw, as you remember, the first row of the Jacobian in the numerator convention is the derivative of the first output with respect to all the input. So this first term here will be the derivative of p11 with respect to s11. So in this case, j and k match, so we know that it will be equal to p11 multiplied by 1 minus p11. The second element to the right of this one, so the element 1, 2, will be the derivative of P12 with respect to, the P11 with respect to S12. The J and K do not match, so we will be in this case here. So it will be minus P11, P12. The third element, you can check it by yourself, it will be minus P11, P13, blah, 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 until the end, which will be minus P11, P1n. The second row of this Jacobian will look like this, so it will be the derivative of P12 with respect to S11. The J and K do not match, so we are in this case here. So it will be minus P12, P11. Then the next element, it will be the derivative of P12 with respect to S12, so J and K match, so we are in the first case, so it will be P12 multiplied by 1 minus P12. Then this stuff here will be equal to, then the third element will be minus P12 with respect to P13, blah, 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 and until we arrive to the last one, which is minus P12 with respect to P1n, not with respect to, multiplied by P1n. And all the elements like this until the last row. The last row will be the first element of the last row will be the derivative of the last output element with respect to the first input element. So it will be the derivative of P1n with respect to S11. So the two indices do not match, so we are in the second case. So it will be minus P1n, P11. This will be minus P1n, P12, etc., etc., etc. Let me do also the third element since we are here. So minus P1n, P13, etc., 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 until the last element of the last row, which will be minus P1n, P1n, I guess. Oh no, that's wrong, guys, because the two indices match, so it should be P1n multiplied by 1 minus P1n. This is what the Jacobian will look like. Let's see if we can find a better how to generate this Jacobian with some pattern recognition. Let's write it in a different way. First of all, first thing that we can notice is that this Jacobian is symmetric. So you can see that this element is equal to this element. If you expand the third row, you will see that it's equal to this element. This one on the top right corner is equal to the one in the top bottom left corner. So this matrix is symmetric. The second thing that we can notice is that only the element in the diagonal are different. They have an additional term, because you can look at this element here. So let me write. This element here can also be written as P11 minus P11 multiplied by P11. The second element here in the second row, so the second diagonal element of this matrix, is P12 minus P12 multiplied by P12. So the element on the diagonal actually look like just like the other elements. They just have an additional term, which is P11 in the first diagonal element, P12 in the second diagonal element. So we can also say that this matrix here is the product of all the possible combinations of Pij with Pik, which we can obtain with an outer product, or even with the product of one column with the transpose of the same column. So if you do one column vector, for example, imagine P is a column vector, and you do P multiplied by Pt, you obtain all the possible combinations of products of these two vectors, because this will be one. I can do a simple case, so P11, P1, let's call it, P2, P3, multiplied by the row vector P1, P2, P3. This will generate all the possible combinations of products between P1 and the first vector and the second vector. Because this will be a 3 by 1, this is 1 by 3, so it will be generated 3 by 3 vector, and it will be equal to P1, 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 P2, P1, P2, P1, P3, etc., etc., etc. Moreover, we can see that in the diagonal, of the matrix, we have this additional term, P1 in the first diagonal element, P12 in the second diagonal element, P13 in the third diagonal element. I actually call it P1. It's wrong because I should call it Pi. That's why I didn't want to bring the I indices. So it's not really P1. It should be Pi. Pi, because we are doing it for the generic ith Pi vector. So let me fix the indices. Pin, Pi3. This is one. Pi and Pi. Okay, so this is Pi. Okay, we can obtain. So we can write this Jacobian here also as the diagonal matrix that in the diagonal has all the element of the Pi vector minus the P vector multiplied by the transpose of itself. So with itself but transposed, because we need all the elements to be kind of a combination of one element of P with itself, with another element of P, plus only on the diagonal we need this additional term, which are the elements of P, and all the elements of the output of this P multiplied by P transposed are negated. That's why we need this minus sign. So if you look at the flash attention paper, they give you this formula here. They say that if y is equal to the softmax of x, then the Jacobian will look like the following. Will be diagonal of y minus y transposed, where y is a column vector. All right, guys, I know this has been long, so let's take a pause, and we are going to now code finally. First of all, let's check the mathematics of the backward pass of a flash attention. We will see it briefly. I will not do any more derivation, but I will explain it, and then we finally switch to coding it. So let's go. All right, guys, now finally we can see the backward pass of the flash attention. So we will be looking at the algorithm, and if you look at the appendix of the flash attention paper, you will see this part B.2 where they derive the backward pass step by step. Now I don't want to do all the steps of this derivation because it's gonna be too long, but I want to give you all the tools necessary to understand it. Now let's start from what kind of how to say conventions they are using, notations they are using in this paper. So the first thing that we need to rehearse is the naming of what is the name of each matrix. As you know, in the forward attention, in the forward pass, we do the query multiplied by the transpose of the key, and the output of this we call it S. Then we apply the softmax to this S matrix, and it becomes the P matrix. The softmax is applied by rows. Then we take this P matrix and we multiply by a V matrix to obtain the output of the attention. Let's look at, for example, how the computation of the ith row of the output is computed based on the P matrix and the V matrix, so we can understand this kind of notation that they are using here in the paper. Because the way I read this formula here is the ith row of the output, which is a column vector, because when we write in linear algebra, whenever we write the name of a vector, it is always by convention a column vector. But the origin of this particular vector is actually a row of the output matrix. Let's try to understand what is the output row of a matrix in a matrix multiplication. Now, so that we can understand how to go from here to here. So let's write a generic matrix multiplication. For example, an A matrix. Let's say that it is the following. And we only write one row. Actually, let me zoom again. And I want to write smaller so we have enough space. So we make a matrix that has a row. Let's call it A1, A2, A3. And then we multiply, this will be a matrix with many rows, like this one, because we want to study the effect only of one row. And we multiply it by another matrix. Let's call it, this one is the matrix A, and it has, I don't know, let's say n rows by 3 columns. Then we should have another matrix B with 3 columns and some number of 3 rows and some number of columns, let's say 4 columns. So we call the first row, let's call it, let me zoom more, so it's B11, B12, B13, B14, then this one should be B21, B22, B23, B24, this should be B31, B32, B33, B34, etc. I know I am not very rigorous in my notation. I should have called all these elements with the capital letter A and the capital letter B. So this is the notation that you use when referring to a single item of a matrix. But please forgive me for this. So the output of this matrix multiplication will be another matrix that is n by 4. So it will be n by 4. So we will have 4 columns for each row of the output. I want to write the output in a different way. So I want to write it as follows, as a vector only. So the first output row as a vector, and want to understand what is each dimension of this vector. So because otherwise I don't have enough space to write it here. So the first, let's write it. So let's call it O. I want to write what is O of 1, which is the first row of the output, but written as a column vector. So O of 1 will be, here we should use the small letter O, of 1 should be a vector where the first dimension is the dot product of this stuff here, so the first row of the A matrix with the first column of the B matrix. So the first, let's say, dimension will be A1 with B11. I should also call this one A11, A12 actually, and A13, so A13, because we have many rows in the A matrix, so let me use the correct naming. So this will be A11 with B11, A11, B11, plus A12 multiplied by B21 plus A13 with B31, and this will be the first dimension of the first row of the output matrix O. The second dimension of the first row of the output matrix O will be the dot product of this row of the A matrix with the second column of the B matrix, and let me write here B. So it will be A11, B12 plus A12, B22 plus A13, B32. The third dimension will be A11, B13 plus A12, B23 plus A13, B33. The fourth dimension will be A11, B14 plus A12, B24 plus A13, B34. Now this is the output, the first output row of the O matrix, and it's a vector called O1, and this is the first dimension of this vector, this is the second, this one is the third, and this is the fourth dimension, and each of this stuff here is one scalar. So the output O1, which is the first row of the output matrix, can also be written as the first element, as you can see, is a sum of many vectors, where the first element is A11 multiplied, let me use a smaller this one, but I want to use a smaller. I can't change the size here. Okay, doesn't matter. So as you can see here, there is A1 multiplying a different B number every time. So this is a B11, B12, B13, B14. What is B11, B12, B13, B14? It is the first row of the B matrix. So it is equal to B1 and all the dimensions of the first row. Then plus, then we have the element A12 multiplied by B21, B22, B23, etc., etc., and this is the second row of the B matrix. So we use the tensor notation of PyTorch to describe this row, which is a B2 and all the dimensions of B2. So it looks, this is a vector scalar product, and plus A13 multiplied by B3 and all the dimensions of B3. This one can also be written as the summation over all possible I that go from 1 to 3, where 1 to 3 is how many columns there are in the A matrix, of Aij, well, A1, let's call this one J, actually, sorry, let's call it J equal to 1, and let's call this the generic ith row of the output matrix will be AI1, AI2, and AI3, each one multiplied by the corresponding row in the B matrix. So we can write it as Aij multiplied by B J, where Bj is the a row of B. We can also write it like this to indicate that this is a vector. And this is exactly what they do here. So the output, in the output matrix, when we do the multiplication P multiplied by V, the ith row of the output matrix, we call it OI, which is a vector, but by notation it is a column vector, where the elements of this column vector are actually the elements of the ith row of O. This is only by notation, guys. Is equal to the ith row of P, so the ith row of the matrix that is on the left in the matrix multiplication, multiplied by all the columns of the V matrix, which can also be written as the summation over all the elements of the ith row of P, so all the elements of the ith row of the first matrix, the one on the left in the matrix multiplication, multiplied by each vector in the V matrix, where the jth matrix here in V is each row of the V matrix. So, and Pij can also be written as Pij is what? Is the output of the softmax. So as you know, the output of the softmax is e to the power of L, the element input of the softmax. What is the element input of the softmax? Is the query multiplied by the transpose of the keys. So it's a dot product between one query and one key. And that's why you have this stuff here in the exponential. So this is the first step in understanding this derivation. Another thing that we have studied so far is how to derive the backward pass of the matrix multiplication and of the softmax. So now let's use it. In the matrix multiplication, let's rehearse the formula. So if given a matrix multiplication that is y equal to x multiplied by w, we know that given the gradient of the loss function with respect to y, so the output of this operation, we know how to derive the gradient of the loss with respect to one of the input of this function, which is the x or w. To get the gradient with respect to x, we need to take the upstream gradient, so the gradient with respect to the output, multiplied by the transpose of wt. And to get the gradient with respect to w, we need to do the xt, so the input transposed multiplied by the upstream gradient. This one is the formula that we didn't derive, and this one is the formula that we derived, but how to derive them is exactly the same procedure. In attention, we are doing the last product that we are doing is O equal to P multiplied by V. What PyTorch will give us as input during the backward pass is the gradient of the loss with respect to the output. And we need to use this gradient of the loss with respect to the output of the attention to derive the gradient of the loss with respect to Q, with respect to K, and with respect to V, so that it can then be used by the operators in the backward pass in the computation graph in the operations before. Okay, so but in order to arrive to the gradient with respect to query, key, and value, we need to derive the gradient with respect to each intermediate operation. So the last operation that we do is O equal to P multiplied by V. So the gradient with respect to O of the loss with respect to V, given the gradient of the loss with respect to O, it is exactly like computing the gradient of the loss with respect to X in a matrix multiplication. And we know that it is equal to PT. So just by analogy, guys, so this is our reference point, and I am just changing the names here, and you should understand what is the analogy here. So the gradient of the loss with respect to V, which is the matrix on the right, which is like computing it with respect to W, it is equal to just like this formula here. So the transpose of the matrix on the left multiplied by the upstream gradient, which in the paper they write it as this. So dV is equal to PT multiplied by dO, and it's the formula that you can see here. The other derivation is how to derive the gradient with respect to dP. dP is just like deriving the gradient of the loss with respect to the matrix that is on the left side of the matrix multiplication. So it is just like deriving the gradient of the loss with respect to X in the reference formulas, which is equal to the upstream gradient multiplied by the transpose of the other matrix, which in the notation of the paper they write it as dP is equal to dO multiplied by V transposed, and it's this formula here. How they compute this stuff here is exactly as above. So as this derivation here, they call Vj the jth row of the V matrix, and they write it as Pij multiplied by dO. How to arrive to this formula here? Well, let's do it. So let me write, let's see. Okay. Theoretically, we know that from this derivation here, so from this derivation here, or from this derivation here, we know that the ith row of the output in a matrix multiplication. First of all, let's simplify our life. Every time you see a transpose and you don't like work with the transpose in a matrix multiplication, just give it a different name. And then work with the different name, and after, when you have derived the formula, you resubstitute the transpose operation. In this case, we are doing dV is equal to P transpose multiplied by dO. Let's call P transpose, let's give it a name that we didn't use so far, so let's call it F. I always use F when it's available, so we call dV is equal to F dO. We know from above here, from this derivation here, or this derivation here is equivalent, that the output of a matrix multiplication, so the ith row of the, let's know the jth row, let's call it the jth row, dVj is equal to a summation of each element of the jth row of F of the first matrix. So we do the, let's see here, they do the sum by I, so let's do it by I. It's the sum over all possible I of the ith element in the jth row of the first matrix. So Fj I multiplied dot product, not dot product, this is a scalar vector multiplication, multiplied by a vector that is, let me check what was the formula, so it was the jth row of the other matrix, so in this case it should be the ith row of the other matrix, O of I, where I, this is the ith row of I, this is the jth row of the V matrix, and But also we know that f is not a matrix that we have. It's actually the transpose of p, which means that fji will be equal to pij, because in a matrix transposition you invert the two indices. So this is the summation over all possible i's of p, not ji but ij, multiplied by oi, and this should be equal to the same formula that you see on the right here. This allows you to compute one output row in the V matrix. Okay, and we know that Pij is just the output of the softmax. The output of the softmax is the input of the softmax to the exponential of the input of the softmax divided by the normalization factor associated with that row. So because we are iterating through the row of I, it will be the normalization factor associated with that row of OI. So we know that the formula for the P is equal to the softmax of S. Now the ith row of P will be the softmax of the ith row of S, and this is what is written here. We know from our derivation that the Jacobian with respect to the softmax operation, so if we have an input x and the output is y of the softmax operation, the Jacobian of this of the y with respect to the x is equal to the diagonal y, it's a diagonal matrix of the element of the vector y, minus y multiplied by y transpose. And we have also seen before that this matrix is symmetric. However, you may not understand this formula here, because we have seen from our, in the chain rule, we always write it like this. We always write that the downstream gradient, so the d phi of, let's say, dx should be equal to the upstream gradient, so d phi with respect to dy multiplied by dy and with respect to dx. This only works if you make this matrix here as in the numerator convention. The numerator convention is one of the two conventions in which you can create a Jacobian. So far we have always written it as the numerator convention. If you use the numerator convention, this is a row vector and this is a row vector. However, if you want to treat this stuff here as a column vector, then you need to take the transposed, or you need to make the Jacobian in the denominator convention. How to get this formula here? Because this formula here is basically doing the Jacobian multiplied by the upstream gradient, not the gradient upstream gradient multiplied by the Jacobian, and it's only because here we treat it as a column vector. And when you do you want to transform a row vector into a column vector, you take the transpose of both sides of the equation, and let's do it actually. So we apply the transpose to the both side of the equation. Okay. In a matrix multiplication, if you do A, B transposed, it become B transposed multiplied by A transposed. So the transposed is applied independently to each input of the matrix multiplication, but we invert the matrix multiplication, and if you remember, the matrix multiplication is not commutative. So what we do here is that we say, okay, it will be the d phi of dx, and here they call it dsi. So it will basically just become d phi on dx. If you treat this one as a column vector, so this one as a column vector will be equal to dy on dx as a column vector, as a Jacobian in denominator layout in this case, multiplied by d phi on dy as a column vector. This one is a column vector, this is a column vector. And this is what you see here. That's why the Jacobian is on the left side of the upstream gradient. What else we need? Well, I know that there is a lot of things here in this derivation, but I prefer actually going directly to the code, otherwise I think it's going to be too boring. So let's go to the code, and while writing the code, I go back to the formulas in which we can find the association of what we are doing and the formula in the paper. I think this is the best way. So let's proceed further. Alright guys, now we can finally code the backward pass. Before we code the backward pass, let's look at the algorithm of the backward pass as written in the paper. This is the paper Flash Attention 1. And because we will follow the structure of the code that is present on the Triton website, so it's not my idea to split it like this, but I simplified it so it's different than the one that you can find online, because mine is a simplified version and mine works with the causal and non-causal attention. So first, if you look at this algorithm, you need to you can see that we have an outer loop through all the K and V blocks and an inner loop through all the query blocks. However, as you can see, to compute the DQ, which is the downstream gradient of the loss with respect to the Q matrix, we need to have an iteration through all the Ks. And to compute each DK block, we need to have an iteration through all the Qs. So if we follow the loop like it is, it would involve writing to the high bandwidth memory, so to the DRAM of the GPU at every inner iteration. And that could be also, that is not so efficient. And also, if we don't want to write, it would require some sort of synchronization between blocks, which is also not very efficient. So we will split this 4 into 2 parts, because we can see that each DQ depends on a loop over the Ks, and each DK depends on a loop over all the Qs. So to compute DK, we will fix the kth block and iterate through all the Q blocks. Then we will do another iteration in which we fix the Q block and iterate through all the KV blocks to compute the DQ. This is what we are going to follow, and this is an idea that I took from the original implementation that is present on Triton website. Another thing that we can notice here is, where is it? Here. To compute the DQ and the DK, so a DQ vector and a DK vector, we need this element, this information here called di, and it's shared between the two. So we can pre-compute it, and then we can reuse it for the qith vector to compute the qith vector and the dk vector. What is this di? Di is introduced here, and it's the dot product of a vector that is the doi vector multiplied by o vector. So the first thing that we will do is do a loop over all the vectors in O and DO and do their dot products to compute this DI element. Then we will use this DI element, and actually, let me see. Yeah, and then we will use this DI element to update, to compute DQ and DK. And we will also have another two loops, one in which we fix the Q and we iterate through all the keys, and one in which we fix the keys and iterate through all the Qs. So let's start. So now that we know more or less the structure of the code that we are going. All right, so we start by writing this backward function here. Let me check. Yeah. Okay. So do you remember this is saved tensor? These are all the information that we save during the forward pass to compute the backward pass. Now, to optimize the memory utilization in Flash Attention, we don't save the query multiplied by the transpose of the key matrix, because that would be a sequence by sequence matrix that is too big to save into the HBM, in the DRAM during the forward pass, and then re-get it back from the HBM into the local memory. Because I want to remind you that in Triton, compared to CUDA, in Triton what we do is we load stuff from the high bandwidth memory in the shared memory, so the SRAM. We do all the operations there, and then after, when we call the store method, we save the element from the shared memory into the high bandwidth memory. So in order to not materialize this S matrix in its entirety, save it to the HBM and then re-get it back, which could be very slow, and secondly, actually it is very expensive, because usually right now we are computing attention on thousands and thousands of tokens. So imagine saving a matrix that is 5000 by 5000. That's a big matrix to save for each batch, each batch and for each head. So that would be really too expensive to save. So the idea in flash attention is to recompute what we can compute on the fly during the backward pass, because anyway, if we were to load it, it would be memory IO bound. So it's faster to recompute than to save it and restore it from the memory. This is the idea of a flash attention. Okay, so we saved some stuff during the forward pass, and now we can access it back during the backward pass, and this stuff is saved in the context, and this it's a kind of a dictionary that is made available by PyTorch. Alright, so we get back the query key and values, and as you know, PyTorch during the Autograd will just give us the gradient of the loss with respect to the output of our implementation of the attention, of our attention. So this is Triton attention, and then we need to compute dq, dk, and dv by using only the gradient of the output with respect to the loss with respect to the output. We do for some checks. So here I know I could optimize this code and make it even smaller by, for example, checking that here the stride that I am using, I actually inside of the code, I always pretend that the stride is the same. But doesn't matter, I just take the code from Triton and try to simplify it. My goal was to simplify it, not optimize it. So, all right, we create the vectors, the tensors in which we will store the result of this backward pass, which is the dq, dk, and dv. And as you know from what we have seen of the definition of the gradient, the size of the output of the gradient vector is the size of the vector with respect to which we calculate the gradient, because in the numerator is always a scalar, and we compute the gradient with respect to all the elements in the input vector. So the output, the gradient itself is a vector of the same size of the element by which we compute the gradient with respect to. So we get some information on the bed size, blah blah blah. And later we will see what is this number of warps and the number of stages. I will not explain it now. It's how PyTorch, number of warps is an indication on how many threads we want to launch in our grid, and number of stages is actually the number of stages that is used in software pipelining. We will see later what is software pipelining when we talk about the auto tuning. Then we define some blocks. In the original code, I think they call it a block KV1, KV2, Q1, and Q2. I think it was confusing. I call it a block macro and block micro because the thing that we will fix and the things that we will iterate from will be one, it's the query. So we fix the query block and we iterate through all the keys. And then we will fix the keys and values block and we iterate through the queries. The one that we iterate on is the micro one, and the one that we fix is the macro one. This is my the naming that I am using. Then we, as I said before, we need to pre-compute the DI elements that we saw in the paper before. So that's the first kernel that we are going to launch, and this kernel will have its own launch grid because later we want to optimize the tuning of this kernel. Later we will talk about the tuning with respect to its own parameters. So let me see, what are we going to do? So here, so the first kernel that we are going to launch is this pre-process kernel. This pre-process kernel will pre-compute all the DI elements that we need to compute. I remember DK and DV, DQ and DK. This DI element depends only on O and DO. So let's do it. And let's create another function called backward preprocess. What is the pre-process grid? This is the launch grid of this function, of this kernel, and this will be launched on independently for each batch and for each head, and moreover it will be work with a block size of vectors of O. What is this block? What is this number of vectors of O? It will be the block size macro, so on 128 vectors of O. So let me copy the signature of this function. This is here, so let's write it here. I think it's fine. Yeah. Okay, this function takes the matrix O. So it's a pointer to the matrix O, it's a pointer to the DO, and it's a pointer to the matrix D where we will store these DI elements. And we have one for each vector in the output. That's why the shape of this D is batch size, number heads, sequence length. It means it's one for each of the output element in the output of the attention, this DI. Where is it? Actually, it's not this one, it's this one. Yeah, like M. So it has the same shape as M, which is, as you can see, it is this size here. So batch size, number heads, and sequence length. M, if you remember, is the matrix that we saved during the forward pass, which includes the normalization factor of the softmax and also the maximum element, but in LogSumExp format, so that when we apply, it will automatically apply the maximum element for each row and also normalize at the same time, which I think I proved previously. Let me do it. So we write it like this. So we extract the index of this program. So this program has two indexes. Like identifier, this is equivalent to the CUDA identifier, and this is along the axis 0. So let's see what did we launch on the axis 0. So on the axis 0 of this launch grid, we defined what is the block of vectors of the O that this particular program will work with. And the second axis is which batch and which head inside of each batch this particular program will work with. So this identifies the block index of Q, so which group of vectors in the O matrix this particular program will work with. Here is called Q, I believe, because I copied it from the original code where they call it Q, but I could have eventually also call it O. So we define, so basically this means that we for this program, we need to skip some query vectors that have been already, or that will be, or have been already processed by other programs in parallel. So we will only block with a number of query vectors inside of O that have the following indices. So imagine that the query block size is, I think it's 128, the way we have defined it, but suppose it's 4 for simplicity. So this one will be, and the query vectors are how many? Are sequence length number of query vectors we have. So some of, imagine the query vectors are in total, they are, I don't know, let's say 64, and 32 will be managed by other programs. So this particular off-skew will be equal to 33, 34, 35, and 36. This tells me which query vectors or which vectors in the output O matrix among all the vectors in the O matrix this particular program is going to work with. Okay, so then we extract also the index of the batch, which tells us which batch and which head in each batch this particular program is going to work with, which is the dimension 1 of our launch grid. And then we define the offset of the dimension because we need to load all the dimensions of each vector. So these are the, it's a vector that tells which dimensions we need to load from each vector, and we will load all of them. So we don't divide on the head dimension we just divide on the sequence length dimension, the load among multiple programs. You will see in this part of the video, so when we are writing the backward pass, that we will not be using the make block pointer like we did during the forward pass. So this function here, we will work directly with indexing by using the strides. So let's do it. So let's load a single block of rows of O, which I want to remind you has the same shape as Q, and that's why we can call it block size Q. So the O block that we are loading is O. So the load function accepts a pointer to what it should load. Actually, not a pointer, it accepts an array of pointers or a multi-dimensional array of pointers in case you want to load a multi-dimensional data. So actually load also allows you to load two-dimensional data. In this case, we are going to load two-dimensional data, which is a block of rows of O, which should be a block, a tensor of the shape block size Q in this case, multiplied by the other dimension being head dimension. but we don't, we need to tell it where in this O matrix it needs to find this one. First of all, we need to skip some batches and some heads based on what the head and the batch that will be processed by other programs. So based on the index that this program will process of the batch and the head, we need to skip all the other batches and heads. Let's write the shape of this tensor. So the O tensor has a shape, block size, not block size, batch size, a number of heads, then sequence length, and then head dimension. Each block and each head will have sequence length multiplied by head dim number of items. So based on our index, we skip how many items? Our index multiplied by head dimension multiplied by sequence length. So what I mean is this: the batch 0 and the head 0 will have a sequence length multiplied by head dimension items. The batch 0 and the head 1 will also have the same number of items, and the batch 0 and the head 2 will also have the same number of items. So how many items, sequence length multiplied by head dimension, do we need to skip from the starting of the O tensor? It is equal to the index of the current batch and head indicator. So because this index indicates both the head in the batch and the head inside of each batch, because it's already the product of the head and the batch. So how many we skip indicated by this index. And after we point to this starting point of the current batch and the current head, we need to select a two-dimensional tensor where the offsets are indicated for the rows by offskew, and that's why we have this one, I don't know what this is called. This is the index semicolon index that tells all these vectors in offskew will with an additional dimension for the columns, and these columns will be the offs dim. So basically this will select a tensor of the following shape inside of this big tensor that includes batch size and number of heads. This is what we are doing. So we are saying select a tensor of this size inside of one that is made up of 4 dimensions by skipping the elements of all the batch and heads that will be processed by other programs. I always talk in terms of programs because in Triton these are called programs. In CUDA you would refer to them as kernels. Alright, so this one is done. I hope it is decently clear. Alright, so then we also load a single block of DO in the same way, because we are going to load a group of vectors from all the sequence length also from DO, and the DO has the same shape as O, which has the same shape as Q, and that's why we can use the block index, we call it Q because it's equivalent, because they have the same shape. Okay, and how to compute this DI element? Well, it's written in the paper. So if we go in the what is it, man? If we go here, it shows you how to compute the DI of each given a block of DO and a block of O. It tells you how to compute DI, which is the row sum, which means the sum of by rows. For each row we will have one sum. For each vector in the O matrix we will have one sum of the element-wise product. So this stuff here is the element-wise product of a DOI multiplied by OI. So it's not matrix multiplication, it's element-wise product, which means each element of one matrix with the corresponding element of the second matrix, and the output shape it will be the same as the two matrices, which must have the same shape. Okay, so we compute this DI block, which will have shape block size Q, because we will have one sum for each vector. Then, well, we need to store it somewhere, so we need to calculate where to store it inside of the D matrix. Well, the D matrix is, I remember correctly, has the same shape as M, so it should be batch size, number of heads, and sequence length. So we need to select the right batch and the right head and also the right position inside of the sequence length based on the block index Q that we have. Okay, so let me index. Okay. All right. Because we already, so we skip, again, just like before, we know that the D is of this size. Each batch and each head will have sequence length number of elements. So how many number of elements we need to skip from the starting of the tensor is sequence length multiplied by the combined index batch size head number. And plus we need to also skip some queries based on our block index queue, and it's already, this skipping is already done inside of offs queue, so we add offs queue. And then once we have computed the index where we should store this di block, why did I even call it d block? Let's store it. So let me, I didn't call it d block, I think it was already in the original code, but this is di. And this big matrix D is actually the matrix that includes all the di, one for each token in the sequence length. All right, so the pre-processing has been done. Now we need to do prepare the 2 for loops. As you remember, I said before, we will be doing 2 for loops. One in which we fix the query and we iterate through all the keys and values, and one in which we fix the key and value block and we iterate through all the queries. And while coding it, I will always show you the formula from the paper, so don't worry. Let's start with the next iteration. So first we create the launch grid for the next iteration. As the launch grid is always the same, so we first, because we need to keep one block fixed and iterate through all the other blocks. The block that we keep fixed will define how many programs we have that run in parallel. And the block that is fixed has a block size macro number of elements. That's why we create a sequence length divided by block size macro number of blocks, thread blocks, or programs in this axis. The axis 2 in this grid is, I could have used also the axis 1 indifferently. I think it was already done here in the original code. It's we will indicate which batch and which head inside of each batch we are going to work with. And just like the forward pass, we will also use a variable called stage that if the attention that we are computing is causal, it will be equal to 3, and if we are computing a non-causal attention, then it will be equal to 1. The first iteration, we will fix K and V blocks, and we will iterate through all the Q blocks in size of block size micro number of query vectors. So let's look at the signature. So we pass, we launch it as a launch grid because, and we have defined how many programs we have. So we have how many KV blocks we will have. It's the sequence length divided by the block size macro, because that's the block that we will keep fixed in this for loop in this function. And then we go through all the query blocks in size of block size micro, which I defined it as 32, and later we will talk about auto tuning and how to tune these values. All right, so I pass the query vector, the key vector, and the v vector. Sorry, not vector, tensors. Now the query tensor, k tensor, and v tensor, and they are pointing to the beginning of the tensor, which means that they are beginning to the first batch and the first head and the first token and the first dimension of the tensors. Then we pass the softmax scale, we pass DO, DQ, DK, and DV. M is the one that is needed to compute. As you remember from what we said before, we did not save the P matrix in the HBM because we want to recompute it on the fly during the backward pass. So the query multiplied by transpose of the keys, it's a very big matrix to save in the HBM and restore it, so we want to compute it on the fly. But we don't need to recompute the normalization factor and the maximum element for each row to apply the softmax. That was already computed during the forward pass and saved into this matrix M, which includes the LogSumExp of the maximum of each row plus the logarithm of the normalization factor. With the LogSumExp trick, we can just apply it and it will also normalize each value. Then we have the D tensor that we computed here with all the di values, one for each vector in the O tensor. Then we need to pass some the number of heads, the sequence length. the block size that we want to use for the KV, which is the macro block size, and the micro block size is always the one that we iterate on. I think using this name, it should be easier to understand which one we are iterating and which we want to keep fixed. So the fixed one is macro and the iterating one is the micro. Head dimension, and later we will see why we use a different block size to iterate from, because this is related to the number of stages that Triton can divide your for loop into, thanks to software pipelining. Then we have a head dimension. The stage indicates if the attention that we computed in the forward pass was causal or not causal. The number of warps and the number of stages, which we defined as fixed, but later we will talk about autotuning. So sometimes I repeat the same stuff over and over, so I should change that. Okay, let's write the signature of this function. Let's put it here. So we already described what is the signature of this function. Let's go directly to the meat. So the first thing that we need to do is understand the offset by which we need to move this query key and value. And the offset is given by the, first of all, we need to enter the right batch and the right head inside of each batch. We compute the index of the batch just like during the forward pass by dividing the program index, which is a multiplication of the index of the head and of the batch. We divide it by the number of heads to get which batch this program is working with, and to get the head we just do the modulus, just like in the for loop forward pass. The offset batch head indicates, let me check, what is it for? Okay, it enters the right batch and the right head. So what is the stride? If you remember correctly, the stride tells us how many items you need to skip in that dimension to arrive to the next index in the same dimension. So if we want to skip index number of batch, we need multiply it by the stride batch, which is how many elements you need to skip to arrive to the next batch. Plus we also need to enter the right head. So we multiply the index of the head multiplied by the stride of the head to enter exactly in that head in the tensor for each of the Q, K, and V matrices. Plus we also have, will be used for, if I remember, for M and D, because M and D only don't have the head dimension, so they are only batch size, number of heads, sequence length. So we just use the index batch multiplied by the sequence length, because for each batch and on each head we will have sequence length number of items, so you can think of it as the stride to move from one batch head to the next batch head. Or to the, yeah. So let's move the pointers. And this was, so we move the pointer Q, K, and V by the offset batch head, because we want to enter the right batch and the right head inside of these big tensors. And we do it also for DO, DQ, DK, and DV, because they have the same shape as a Q, K, and V, and DO also has the same shape as Q. So they have the same shape, so we move by the same offset. All right, so and then we move M and D to move them to the right starting point on which the sequence of the current head and the current batch and the current head starts. So they are pointing to the first vector of the sequence dedicated to the current batch and the current head. And the same is true for Q, K, and V, and the DO, DQ, DK, and V. Okay, then we load some other stuff. Because here we fix, in this iteration, in this method, we are going to do a for loop in which we fix KV and we iterate through Q. So we first need to load this block of KV, and we do it as follows. So we need to load a 2D tensor, so we need to define what are the ranges in the second dimension of each vector K and V that we need to load, and it's defined by this vector. Then we want to understand which KV block this particular program is going to work with. So this particular program is going to skip some KVs that will already be managed by other programs that may be running in parallel, and how to understand what this program should be working with based on the index of the program 0, which is defined on sequence length divided by the block size macro. And if you remember, block size macro is the thing that we fix. So it's telling us this program ID 0 will tell us how many block size macro KV are already being managed by other programs, so we shouldn't care about them. So we skip them. So let's go back here, and this is the number of vectors that we need to skip. So our KV starts from start KV. And how many we need to load them? Well, depends on what is the block KV. This block KV is equal to block size macro, so it will be 128 vectors. So we define our tensors, two-dimensional tensors that we will store in the SRAM, because in Triton every time you load something, you load it from the HBM into the SRAM. So we define where they should be saved in the SRAM, and they are initially zeros, and now we load them. So we load them as follows. We say that, okay, in the K tensor pointer, which is already pointing to the right index, to the right batch and to the right head, because that's something that we did here, we say we need to load the right sequence of keys, which should start from off key, because this already includes how many we should skip in the sequence length dimension. And for each of these vectors, we need to load all the dimensions in the head dimension, because the K, if I want to remind you, is batch, number of heads, sequence length, and head dim. Now, by using this line, we are skipping to the right B and to the right head. So it's like we already indexed here, and here we already selected an index. So right now, this K is pointing to the beginning of a tensor of 2 dimensions. And we tell, okay, we don't want all the sequence. We want some part of this sequence. Which part? The one that is indicated by this start KV. And how many of in the sequence length we want? Well, we want, I think it's easy to write it like this. So we can write it that from start KV to start KV plus block KV. So we want this number of tensor exactly at this location. And for head dimension, what do we want to select? We want to select all the dimensions. So we say that we want from 0 to head dimension, which is exactly this offs dim. Okay. We do it for the K block, and we do it for the V block. Here, I think I didn't change the comment. This should be block KV. And this should be block KV. Before it was called block KV1, right, like in the original code. I simplified a little bit the naming. I think this one is better, easier to follow, because in the original code they also do two for loops, but in the second for loop they do it backward just to not change the structure of the loops. But I think mine is more verbose but easier to understand, and probably less efficient. Mine is much less efficient. Then we have offskew, because we need to understand for each block of queries how many vectors we need to load, and it's indicated by this offskew. And how many are them? It's a block Q. Block Q in the color of this method was block size micro, so it is 32 vectors. Okay, now we need to access Q vectors and O vectors. Q vectors but already transposed, and the O vectors also we need to access them, because we are going to iterate through queries and O vectors actually also. Why? Because let's look at here, let's look at the formulas in the paper. To compute Vj, so to compute the dVj, that's what we are trying to compute here, we need to iterate through all the do vectors, and to compute dk we need to iterate through all the qi vectors, because the qi is a block of vectors. That's why we need, and why do we need to access q as a transposed? Because we need to compute, let me show you here, Pij transpose. To compute Pij transpose, we need the Q transpose, because the Pij would be the softmax of the query multiplied by the transpose of the keys. After we apply the softmax, it becomes P, but if you want the transpose of P, then you need to do query transposed K multiplied by query transposed. So that's why we access the query transposed instead of queries. And the way we access query transposed is just by playing with the stride. So let's do it like this, and I have also written the comment on why we can do it. So this is equivalent to accessing the query. What is this operation? What is this operation here? This is saying go to the query starting pointer to the query, which is already pointing to the right batch and to the right head for which this particular program should work with, and select a two-dimensional vector where you repeat the query starting point along the, in this case, along the columns, but we should be repeating it along the rows because we want to select rows of queries. However, if we want to select the query transpose, we just invert the two dimensions. So this is, let me actually show you without doing the query transpose. So let's do it simplified like this. So to access the query pointers without transposition, we can just do like this. Go to the query tensor and create a 2D tensor where in the rows you put the starting point of each query that you want to get, and replicate each of these pointers also on the column. That's the meaning of adding this dimension none. This is equivalent to when you do in PyTorch the unsqueeze, like you are calling offskew multiplied unsqueeze I think 1. So this is equivalent to adding the column dimension to this tensor and repeating all the values that are on the row on the columns. How many columns will be there? It will be broadcasted when we sum it with this tensor here. This is a combination of unsqueezing and broadcasting. So we are taking the query vectors indicated by offskew, and then we are, for each query vector, we are selecting all the head dimensions indicated by dim. If you invert this broadcasting, it will create the transpose of the query vector that you are trying to access. So this stuff here is equivalent to these two lines, so accessing query and then transposing. And it's something that you can do. I could write down what is happening at the pointer level. So basically you need to think of offskew as being a vector of pointers. We multiplied by the sequence stride, which tells us how many elements we need to skip to go from one query vector to the next, because each stride q will be the stride will be equal to, in the case that the head dimension is 128, the stride of the sequence dimension will be 128. It means that to go from one query vector to the next, you need to go forward by 128 elements, because I want to remind you that in the memory the tensors are always stored like flattened, like each dimension is flattened with the next dimension. So imagine you have 3 rows and 4 columns, but the first you will have the first 3 rows, then the first row, so the first 4 columns, then the next 4 columns, then the next 4 columns, row after row. It's difficult to visualize until you write it down. So how to write it down? Create a vector of offskew. So what is offskew at the beginning? Is a range that is from here, from 0 to 100, no, 0 to 32, 0, 1, 2, 3, 4, 5, 6, 7, etc., etc. We are multiplying each one with the stride of the sequence, so this will not skip any element. This will skip exactly 128 elements. This will skip exactly, implying that the head dimension is 128. This will skip 2 times 128 elements. This will skip 3 times 128 elements. And then we are adding also another dimension to this vector. So this will be a vector. Then you broadcast it on head dimension number of columns. And to each of them, you add one number. So it will become a vector like follow. Okay, let me just do it, guys. Otherwise, I think it's too confusing. Okay, so we have a vector that is as follows, so 0, then we have 128, then we have 2 times 128, then we have 3 times 128, etc., etc. We are adding how many columns indicated by offsdim. So offsdim has how many columns? It has a headdim number of columns. Please, for simplicity, let's pretend it's not 128 dimensions. Let's pretend it's 4 dimensions. So this will be 4. This will be 2 times 4. This will be 3 times 4. We are adding another dimension that is the dim dimension. Each one multiplied by the stride of dim, which will be 1 because it's the last dimension. Stride dim, so we are adding how many columns? 4. So we are adding 1, 0, 1, 2, 3, I guess. 0, 1, 2, 3, right? Also to this one, we are adding, oh my god, 0, 1, 2, 3. And also to this one, we are adding 0, 1, 2, 3. Okay. And then also to this one, we are adding 0, 1, 2, 3. So what this will select? This will select from the starting point of the pointer Q, it will select the element 0, then the element 1, then the element 2, and then the element 3, which is exactly the head dimension of the first vector that we should be selecting. Then it will select the element 4 from the starting point of the vector, the element, sorry, this one, let me write the result of this operation. So this one will be 0, 1, 2, 3. Then it will select the element 4, 5, 6, 7. Then it will select the element 8, I guess, 9, 10, 11. And then it will select the element 12, 13, 14, 15. So from the starting point of where this Q is pointing, it will select the first element right after this Q, the second element right after this Q, the third element right after this Q, etc., etc. And this will be the you can see that this will be the first query vector. This will be the second query vector. This will be the third query vector. This is the fourth query vector, because in the memory they are stored one after another. They are flattened. So in the memory they are stored like this. They are stored like the following. They are stored like this, one after another, so it will select all of them. And it will also create a virtual tensor with the right shape that we want to visualize it into. So as we saw before, when you work with a tensor layout in memory, you can always view it as whatever shape you like based on the shape that you want. And the reshaping is always free. It doesn't involve changing the arrangement of the elements in the memory. I hope now it's more clear. So now we can proceed further. Oh my god, it was quite complicated. So whenever I get stuck, I just draw things, and I think you should do it too, because that's the only way to learn. If you try to imagine everything in your head, it's always difficult. And we do the same job for the O vectors. In the O vectors, we don't access it as transposed, because we don't need it in transposed. Only the Q, we need it in transposed. Okay, it traced through the sequence dimension of the query. So we start from the query number 0. In the current, in the query we need to go through all the sequence length dimension, because only the key, we select the right key that we want to work with. So I want to remind you, here we fix the key and we go through all the queries. But the query we need to start from 0 until sequence length. So the number of steps of this for loop will be sequence length divided by block Q. So if we have 1000 elements in the sequence and the block Q is 32, it will be 1000 divided by 32. Bad choice of 1000, should be 1024, otherwise it's not divisible. So then we go through each block in this for loop and we load a block of Q, the first one indicated by our pointer, and at the end of the iteration we will move it to the next block of Q. Okay, we'll add also the LogSumExp values that are stored in the M matrix. because we want to compute on the fly PT. PT is the transpose of the softmax of query multiplied by the keys, but we want to not take a query multiplied by the transpose of the key and then do the transpose. We just already access Q as a transposed, so we can already compute a PT instead of computing P and then transposing it. So we load the offsets of the elements that we need from this LogSumExp matrix, which is the M matrix that we computed during the forward pass. And we access a block of Q at a time, the one we are currently working with in the iteration. Then we access a query key transposed already. So we do the, if you want to get a PT, P should be, this is actually not P because we didn't do the softmax, it's actually ST. But okay, if you want to get a PT, you need to get the softmax of ST. The softmax of ST is what? It's transpose of S. What is S? Is a query multiplied by the transpose of the key. So to get ST, you need to do key transposed, key multiplied by query transposed. So as you remember in the matrix multiplication, if you transpose the matrix multiplication, you need to also invert the two element in the matrix multiplication. So that's why we are doing a key multiplied by query transposed. This will give us S transposed. We are also scaling it with the softmax scale. Before we apply the softmax, we just need to do the exponential of each element minus its maximum divided by the normalization value. But with the LogSumExp trick, we just need to each element subtracted by the M value, which already includes the normalization factor. I think I already did the derivation of this, so we don't need to go through that again. Okay, so now we have the PT block actually. So in this formula, I should have written ST actually. Okay. Then when doing the causal attention, we also need to mask out some values. So as you can see here, so in this case the causal mask is applied after the softmax has been computed, because during this one is you are used to apply the causal mask before computing the softmax attention, but this is actually during the forward pass, because you don't want the normalization factor to be affected by the element that should be 0. But we already computed the normalization factor, so it cannot be affected anymore. So we can mask out after applying the software, because the normalization factor has already been calculated based on the fact that we applied the mask. And that's why we can apply it after applying the softmax. So the mask is always the same. So if the query is more than the index of the query, so the mask is true in this case for all the values that do not need to be masked. So all the values that do not need to be masked are these ones here, and all the other value will be replaced with the zeros. All right. So after we have the PT block already masked, we can calculate dv. dv, I will point to the right formula in the paper. So we load a block of DO. Why do we know to load a block of DO? Let's look at the paper. So how to compute the dv block. So the dv block is computed as the old dv plus, so a repeated sum, as you can see it's here plus equal. The old dv plus pt, so here pt dropped indicates the Pij after applying the dropout. In this implementation, we don't support the dropout, and also very few models actually use the dropout in the attention. So pt multiplied by doi, so a block of doi, and doi is the same block that should be also doi and ki, qi are referring to always the same block of rows in the respective tensors. That's why, because this inner iteration I indicates a block of Q and a block of O, but they are always referring to the same positions in the tensors, because DO has the same shape as DQ. So we go through the blocks of query and the DO simultaneously, because one is needed for dv, so for dv we need DO, and for dk we need Q. And that's why we compute the dv as follows, just like from the paper. So pt block multiplied by do, as you can see, it's a p transpose multiplied by do block. So we have computed the do block. Then we need to load the di element that we pre-computed initially, with the first call to the function called the attention backward preprocess, because we will need it for decay. So let's see. And how many of them we are loading? Exactly the same number of query that we load, because we load always the same number of block size micro number of vectors. Okay, I will copy some stuff and explain it step by step. So the next operation that we need to do is to compute this dk. To compute the dk, we need dst. To compute dst, we need to get dpt. So let's go one by one. Let's go from the end to the beginning of these formulas, so we don't understand where everything is used to where everything is created. So let's start from dk. If we look at the paper, dk is equal to the old dk plus ds transposed multiplied by a block of q. And this is what is written here. So it is plus equal means basically just the old plus the new. It's an incremental addition. So we increment the old k with some new stuff, which is this stuff here. So the softmax scale multiplied, because also there is a softmax scale, this tau here, multiplied by the matrix multiplication between dst block and the transposed of and q. And q you can see here, this q. But we don't have a q, we have a q transpose, so we take the transpose of q transpose and it becomes back q. Now let's look at this dst block. dst is calculated as follows. So in the formula of the paper we have ds. ds is here, it is here, and it is equal to a block pij multiplied element wise with dpi minus di. Now we don't need ds, we need ds transposed. So to compute ds transposed, this is an element wise multiplication, not a matrix multiplication, which means that when you take the transpose of this operation, you don't need to invert anything, you just need to take the transpose of the two operands. So to compute the st, we take the transpose of p, which is a pt, and we already have that, and then the transpose of everything that is inside of the parentheses, so this dpt minus di, where we invert the rows with the columns. So this dpt is what? Well, in the paper we know the formula for dp. dp is here, and it is equal to dp here, and it is equal to do multiplied by v transposed. So but we don't need the dp, we need the dpt, and in this case it's not an element wise multiplication, it is a matrix multiplication. So in order to get not a dp but dpt, we need to take the transpose of these two operands of this matrix multiplication, and in the matrix multiplication when you take the transpose, you need to also invert the order of the two operands. So we need to take the vt transposed, which becomes v, so the v block, matrix multiplied by the other operand, so doi transposed, and that's why we are doing the transpose of do. Right now I'm not going through all the single pointers, because I already told you how to check what a pointer is pointing to and what an offset is referring to. I hope that now you have a better understanding on how these pointers work in Triton, which is also the same way in which they work in CUDA, because in the GPU we only get a pointer to the starting point, to the starting address of the tensor, and then we need to work out all these indices. We have computed the dk block, so we go to the next query, to the next block of queries, and the next block of queries, because we are fixing K and V blocks, and we are iterating through all the queries. So we need to move the query transposed pointers by stride sequence, which means that how can we go from one query to the next, and we multiply it with the current block Q, which is a vector which indicates the pointers to the current element in Q that we are accessing. And we do it also for the O, and we use the block Q as element and the stride Q because the O and Q all have the same shape. Okay, after we have run the for loop over all the queries, we can store this dk and dv block. So we write it back as follows. And this is the end of our function, guys. So we save the dv block exactly in the position inside of the current. Okay, dv is already, I believe, pointing to the right batch and to the right head because we incremented it here, and also in the case of dk. Then we need to tell it in the sequence dimension where they should save this block of K and V, and this is indicated by this one. We say, and we create the pointers just like before, guys. Don't make me do it again. It's really easy if you write it down. Like you write this vector of key and values pointers, which is not pointers. Actually, they are a range of the of key and value that you need to take from the sequence dimension. You add another dimension that is the column, so you repeat each value in the columns, and then you add the dimension here for the head dimension. Anyway, after we have calculated the pointers where we should store the dk and the dv, we store them in the pointers of we store them in the dv we store them in the dv tensor and the dk tensor. What do we save? We save the dv block and the dk block, which is the one that we were incrementally changing in the for loop that we have written. Okay, now that we finished this one, we can go to the next function that will do the other for loop. So let's do it. Okay, so now we do the second part of the iteration, which is this one. So let me just copy it and then we describe it. Let's write it here. Okay, we use the same launch grid as before. Of course, we need to declare this function, and again, because the grid is defined for the block size macro for what is the thing that we keep fixed, and then we, in the side of the for iteration, we do steps of block size micro. In this case, we are fixing Q and we are iterating through K and V. Because we need to compute dq. Right now we have computed dk and dv. Okay, I believe the arguments are the same as before. So, and actually this is also the reason why in the original implementation on the Triton website, the author decided to use the same for loop but with different arguments, and I believe it was a little confusing, so that's why I just separated them. I just repeated the code twice. The goal of this video is to be as easy to understand as possible, not to be as efficient as possible. So let's go here. So let me copy the signature again, and we define this function here. Okay, so again, we need to first move the query key and value to the right pointers, which will point to the exact batch and the exact head that we are working with in this program. So let's do it. Let me check where is the code here. And the first part is exactly the same as the other for loop that we have written. So let's go here, and really I just copied, so it's exactly the same. So we check what is the index batch head. We move the query key value pointers to the right place. The DO, DQ, DK, DV point to the right place. The M and D to the right place, exactly like before. So I don't think I need to explain that again. And then we load a block of Q, the one that we will keep fixed. So DQ. Let me load a lot of stuff here actually. Okay, we define the offset that we will need to load the blocks of K and P in the head dimension because we are going to iterate in the K and V. We will access them as transposed blocks. So instead of accessing them directly as K and V, we access them as KT and VT. And you know that that's possible just by changing the strides. In this case, because we are treating them as 2D vectors, we treat the offs kv when you want to access k as just not transposed but k. You treat this offs kv as a row vector, a column vector. So you repeat on the rows each k offset that you want to access. In this case, we are repeating it as we are treating it as a row vector, so it will be repeated on the rows. It will be broadcasted on the column dimension. And that's how you can access the transposed version of K and how you can access the transposed version of V. Another thing that we are doing is we are loading the Q vector. Which vector? Well, based on offs Q, which is based on the start Q, which is based on the exact starting point in which this particular program should be working with, because this particular program works as 2 dimensions. The first dimension indicates which batch and which head this program should be working with, and the second dimension, which is the program index number 0, indicates which among all the sequence length, which query this particular program is going to work with. This is indicated by the index block. This should be actually Q. In this case, I forgot to change the name, so actually let me change it. So it's index Q because we skip some Q. How many Q we skip? Based on the index of the current program multiplied by how many blocks have already been processed by the previous programs. This will tell us inside of the sequence length what are the queries that this one needs to select. So that's why we use the start query plus the range that is block Q. So imagine the starting query for this program among all the sequence length is 100. Then this will load the query row 100, 101, 102, blah 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 until 100 plus block Q minus 1. This is the range that of the query vectors that we will load in this program. We load the block of Q by using Q plus the offset repeated on the columns. So we treat it as a column vector, but we broadcast it on the rows vector. Where each column will be one head dimension multiplied by the stride. In this case, we actually can also not multiply by the stride because the stride in the dimension, so the last dimension of the batch is 1. Because to go from one, actually the stride, how it is defined, the stride of the last dimension is always 1, because to go one element to the next element, you should move it by one element. So we load the DQ, which is the stuff that we are going to compute in this iteration, and then we have a DO that we need to load. And the DO, we use the same offset as Q because the DO and the DQ have the same shape and they work in the same way. So we load a block of Q and we load the corresponding block of O, of DO in this case, and the DO has the same shape as O, which has the same shape as Q. Plus we need to load also the M normalization factors, which are in the M matrix, which one the one corresponding to this particular group of queries that we are going to work with in this particular program. We start with the offsets, as you can see, the offsets are the first block of KV starting from the 0 position. So because we will iterate through all the KVs and we start from the 0 KV. So the key vector 0 and the V vector 0. And then we will move by block KV number of vectors forward at each iteration. I hope I didn't go too fast because most of the things that are written here are very similar to what we have already done in the other for loop, so I don't want to repeat myself too much. What it matters is actually the formulas that we will use, which is exactly the one in the paper. So we go through these blocks of KV. We load the first block of K transposed and V transposed, which is loaded like this as usual. You tell it what pointers, the elements you want to load, and what are the pointers of another element that you want to load, and it will load the block that you are asking Triton to load inside of the SRAM. So this stuff all reside in the SRAM, and also Q resides in the SRAM, and also DO reside in the SRAM. Then we compute the query multiplied by the transpose of the keys, because we need to compute the P block. So the query, the QK block is just the query in the current query block with the K transposed in the current query block and in the current key block. But we are access query the keys already as a transposed, so we don't need to transpose it. And anyway, even if we need to transpose it, it's just it's not a it doesn't require any computation to transpose a matrix. We just access it in a different way. Because in the memory layout, it's always stored kind of as a flattened array. Then we compute the P block, which is the output of the softmax. So each of the query key, we subtract the LogSumExp value for this block of queries. That's why for loading the M block, we use the offsets of the queries that we are loading. And as you remember, the M block already includes also the normalization factor, because each M is actually the maximum value for each row plus the logarithm of the normalization factor that when you apply with the properties of the exponential, it goes into the denominator. Okay, and then we apply again the autoregressive masking. Oops. What did I do? Let me go back to the code here. So we have the stage, this one. So when we launch the backward pass, stage 3 indicates that it's in the forward pass we computed the causal attention, and the 1 indicates that we computed the non-causal attention. So if we computed the causal attention in the forward pass, we also need to mask out these elements in the backward pass. So we check, we created the mask which tells us which index, this mask is true only for the elements for which the query index is more than the key index. And if this is true, then we don't mask, otherwise we mask. Let's compute the next operation, which is to compute dp and ds. Actually, let's compute directly dk, and then we explain it like before. So we start from the end and we go to where this stuff, what is needed to compute it. So if we look at the formula, let me check. This one we don't need, I think. Okay, let's go here to the iPad. Okay, what we are trying to compute here is dq. So dq, as you can see in the paper, is dq is equal to the old dq plus tau, which is the softmax scale, which is this stuff here, multiplied by the matrix multiplication between a ds and the k block. So the ds block is here, and the k block is the transpose of the kt block, because we are accessing k already as a transpose block. We could also access k directly as not a transposed block by inverting. If you don't want to access it as a transpose block, just do like this, like here, none. This will treat it as a row vector and broadcast along the columns. Otherwise, and also this one you need to change. So this one you should need to change, because this one you need to treat it as a column vector, the dimensions. But if you want to access it as a k transpose, then you just invert these two operations. I hope I didn't mess up anything. So let's move forward. So okay, we know that the formula for the dq is exactly the same as the paper one. But what is this ds block? Let's look at the paper. This ds block is coming from this stuff here. So this, I believe, this stuff here, ds, which is a pi, the p block, element-wise multiplication with the dpi minus di, which is dpi minus di. Now, what is this p block? The p block is exactly the output of the softmax, which we already have. What is the dp block? Well, the dp block is exactly DO multiplied by V transposed, which is a DO, which we already loaded, and it's here, multiplied by the transpose of the V, which we already load as transposed. And this is how we compute the DQ. Let's include, then of course we need to move to the next block of key V's. So we increment the pointers just like before. So we move to the next block of keys and values. And also we move the pointers, just like before. And then we need to store the result of DQ. And this way we only need to do one write to the HBM by dividing the for loop like the following. So if you look at the original algorithm, I don't know if the original algorithm actually corresponds to the implementation that they did in CUDA, but I don't think so, because it would not be so optimized. But in the original algorithm in the paper, they say that you need to go through all the keys, and then while going through the keys, you need to go to all the queues, and for each queue that you visit, then you need to write back the queue while you are updating it, which is not optimized. That's why we needed to do two for loops, one in which we fix the query and we update the keys, because each keys updated depends only on a particular block of queue. On all the blocks of queue, sorry, and then we fix the queries and we iterate through all the keys, because one block of queue depends on all the blocks of keys. And this is why we split, and this is the second loop that we have written. Now we have written everything that we need to for flash attention, the forward pass and the backward pass. So we should be ready to launch the kernel. I hope I didn't make any mistake in copying the code. So I don't think I will try to launch it, and if there is any error, I will just use my reference code, which I have already written, that I used as a copy. The only difference up to now between my reference code and the one that we have written is the auto-tuning, which I didn't explain. So let's talk about the auto-tuning. So the auto-tuning is also something that was already present in the original paper, and I kept it as is. I removed the auto-tuning for the backward pass. But in the forward pass, if you check, there is this code here that indicates the auto-tuning configuration for Triton. So Triton basically cannot know beforehand what is the best block size, or what is the best block size for the query, or what is the best block size for the key and values, or what is the best block size from another dimension that we have. We need to try based on the hardware that we are running on, based on the availability on the SRAM, based on the thread coarsening that Triton can apply. So I didn't talk also about thread coarsening. Basically in CUDA, you can choose if each thread does one atomic operation. For example, in a matrix addition, each thread is doing one addition of one particular element of the output matrix, or it's managing multiple elements. This is called thread coarsening, and I think, I didn't check the documentation, but I believe Triton does it for you based on the block size that you give it and the number of warps that you want. The number of warps is what? Is a block of threads of 32 threads that work cooperatively, running the same instruction always at the same time. The number of stages is more interesting. It's an optimization that Triton does. Basically, it is not loop unrolling. So actually, let's talk about software pipelining, because this is the last part that we need to understand from this code, which is the auto-tuning. So I believe that the most interesting part here is not choosing the block size Q and the block size K, because that is just kind of, you try whatever configuration works best based on the timing. Through CUDA, Triton will actually run all these configurations for you every time the sequence length or the head dimension changes, and for every pair of head dimension and sequence length, it will choose the best configuration that runs in the least amount of time. That gives you the best throughput, actually. So let's look at these num stages. What is it and how it works? So let's do it. Okay, so software pipelining is it's used when you have a kind of a for loop. So you have a sequential operation in which each iteration does not depend on the previous iteration. So the operations that you do in one iteration are independent from what you have done in the previous iteration, which is more or less what we have done before in our for loops. Actually, I believe there are, how to say, conditions in which this doesn't have to be true. So like the operations can depend on each other and you still can do software pipelining. So, for example, imagine you have the following for loop. For loop that runs from 1 to n, and first you load some data, then you load some other data, then you do a matrix multiplication, and then you store some data. So here you are reading data, here you are reading data, here you are computing some stuff, and here you are writing data. If we look at what happens at each iteration, we will see the following picture. Imagine our GPU is made up of a compute unit and a unit that is dedicated to loading stuff, so reading from the memory or writing to the memory. What we will see in the time scale is that at the first iteration, first we are reading some data and the compute unit is idle because we need this data. Then we are reading some more data and the compute unit is idle because we need this data. Then finally we have enough data and then we can compute this operation and the reading unit is idle. And then we are writing some data back to the memory and the compute unit is again idle. And then it will be idle for another 2 time steps until it has enough data to run the computation. So as you can see, this is not very efficient because at any point in time, there is only one unit working and the other is sitting idle. So one way to optimize this for loop is to do software pipelining, and you can tell Triton to do it for your for loops by telling it how many stages you want. So let's see how it works. So to pipeline a for loop means that, first of all, you need to convert all these operations into async operations. And in CUDA, at least in the GPU of NVIDIA, there are the async loading from the memory and the async load writing to the memory, which basically means that I spawn a load operation and when I check if it has completed when I actually need it. So I will spawn this operation and this instruction will return immediately and move to the next instruction. Here I will spawn a load iteration and this will return immediately and move to the next instruction. And then I can compute, but before computing I just check if these 2 operations have completed. So I can spawn immediately 2 reads and then I just check if they have completed. So with the software pipelining, what we are doing is we are pipelining operations of different iterations into a single iterations. So first, basically what we will do is we will do read the first matrix that we need for computing this matrix multiplication. Then at this next iteration, we read we read the first matrix of the second iteration and also read the second matrix of the first iteration. So I call it read A and read B, which indicates read the first matrix of the that we need, and the B means read the second matrix that we need. All these operations are asynchronous. Then I launch another asynchronous operation at the third iteration that says read the first matrix of the third iteration, and then read the second matrix of the second iteration. And then compute the matrix multiplication, because at the third iteration, this one and this one should have completed, but while computing the matrix multiplication, I don't keep the loading unit idle because they are still computing this, and this load. And this can only work if you can spawn async operations. So at the third iteration, I can compute this matrix multiplication by using this one and this one because they should have finished. But while I'm computing the matrix multiplication, I already spawned some async operations to load the data necessary for the second iteration and the third iteration. So at the fourth iteration, I will spawn the loading of the data for the fourth iteration, loading the data for the third iteration while computing the matrix multiplication of the second iteration because they should have already completed by now. Actually, it's not like we expect them to have been completed. There are primitives in the language or in the CUDA language to check if the operation has completed. So actually, before doing the matrix multiplication, we will actually check if the async operation has finished. So it's not like we just expect it to have finished with respect to time. This is like in JavaScript, you have these things called promise, I remember, and you can wait for the promise to be finished before you actually need them, but you can spawn as many promises as you want. In C#, I think they are called tasks, so you spawn as many tasks as you want, and then when you need it, then you just wait for them. Only the one that you needed, while the other are still running in the background asynchronously. This is the whole idea of software pipelining. Software pipelining, as you can see, only works when you have async operations, and also it increases the memory requirement for your program, because when matrix multiplication 1 is going to run, we may have enough data for the first 2 iterations plus half data for the third iteration, so we increase the memory requirement for the SRAM. Okay, and Triton will do this software pipelining for you. It will convert all the load, all the stores, and maybe also the matrix multiplication into async operations and do this pipelining for you. If you are confused by how it works, there is another easy solution to explain you how it works, because it's already something that we do in model training. It is called pipeline parallelism. So in pipeline parallelism, it works as follows. We have a very big neural network that does not fit in a single GPU. So imagine this neural network is made up of 3 layers, layer 1, layer 2, and layer 3. But this is so big and it does not fit entirely in one single GPU. So one way would be to put this each layer into one GPU. So we put, for example, layer 1 into GPU 1, layer 2 into GPU 2, layer 3 into GPU number 3. So imagine we have an input for this neural network. So we put it to the first GPU. The GPU 1 will process the layer 1 and generate some output, which will be transferred to the GPU 2, which will calculate its own output and transfer it to the GPU 3, which will compute its own output, and finally we will have the output of the neural network. The problem is, when you send the output of the GPU 1 to the GPU 2 for the GPU 2 to do its own thing, the GPU 1 now is free. So it is a waste of resources. We should keep the GPUs busy. So one thing that we can do is, instead of sending all the mega batch to the GPU 1, we send many smaller batches. How does it work? Imagine that we send the batch number 0, so batch 0, to the GPU 1. The GPU 1 will compute its output and send it to the GPU 2. So now the GPU 2 is computing the batch number 0. So now the batch 0 is not here anymore. But now the GPU 1 is free, so we send another micro batch called batch 1. Then the GPU 2 will finish processing the batch 0 and will send it to the GPU number 3. So now the GPU 3 has the batch number 0. And the GPU 2 now is free, so we transferred, and hopefully also GPU 1 has finished. So we transferred the batch number 1 from GPU 1 to GPU 2, the batches, and then the GPU 1 will be free. So we transfer. Here becomes 1, and now this one is free. So because it's GPU 1 is free, we can introduce another batch. So batch number 2, etc, etc, etc. So we always introduce, while moving one batch from one GPU to the other, we introduce a new batch at the beginning of the pipeline, and they shift by one position at every iteration. This will keep the GPUs always busy. There is only one problem of the pipeline parallelism, which is this bubbling effect, because to create this pipeline, you at the beginning of this, actually in the pipeline parallelism, you also have the problem of the backward step. So the backward step has to run exactly in reverse in the order in which you receive the micro batches. While in Triton, when doing software pipelining, you have the problem of the prologue and the epilogue, because you need to create this pipeline and to start the pipelining, and at the end of the pipeline you need to use all the stuff that is currently in the pipeline. So only in the beginning step and in the last step of this for loop, your all the units of this GPU may not be working simultaneously. What does it mean? It means that in order to use pipelining, you want the number of iterations of your for loop to be much more bigger than the number of stages in which your iteration is divided into. In this case, we have 4 stages. These are called stages. So you want the number of iterations to be much larger than the number of stages. All right, guys, finally, I have completed the video. I hope that you learned a lot from this video. I believe that we can run the Triton code, so let's run it actually. let's see, I copied everything. I believe we also put the code to test it, but we didn't put the main method, which we can copy right now. I hope there is no error, so I really hope there is no error. I really hope. So let me check if I am in the right machine. I am. So let's just run program, pray. If there is an error, I will just copy my own reference implementation, but I hope it works, because otherwise I forgot something. So I'm running my code on an H100 because my company has H100. If you have a smaller GPU, what you can do is you can reduce the sequence length. You can reduce the batch size. I think it's already 1. When we call it, oh no, the batch size, you can reduce the batch size, the number of heads, the sequence length. You can even put head dimension equal to 8 and the sequence length equal to 16. Let's check. Run backward, Triton backward, returned an incorrect number of gradient, expected 5, got 1. We probably forgot some return statement, I believe. Yes. So I forgot the return statement here. So in the backward pass, after running the last for loop, we need to return the stuff that we have computed. Cross finger again. Okay, passed. So the backward pass that is computed by Torch, it is equivalent to our backward pass up to 10 to the power of -2 error, absolute error. So when you, as you can see, this backward that we run here is different than the backward that we run here, because when you apply Triton attention, it will introduce a new computation graph in the computation graph of our tensors that will include this Triton attention operator. And when PyTorch want to compute the backward pass, it will just call the backward function of this Triton attention to compute it. And it will populate the grad value of all the tensors that are the input to this Triton attention. And this is how PyTorch Autograd works, guys. Thank you for watching my video, guys. It has been super demanding. I spent many months, first of all, to learn myself about Triton, about CUDA, about flash attention, etc. Also, I have a full-time job, so it's really hard to make videos like this. Like I need to dedicate, you know, the nights, the mornings, the weekends. I spent 3 days just to record this video because sometimes I don't like how I explain something. Sometimes I make a mistake, or sometimes I need to restart because what I'm doing is wrong, etc., etc. I believe there should be no big errors in what I have done so far, but for sure my notation is completely bad. Like, because all the mathematics I know has been self-taught by. I learned it by myself. So because I didn't learn it in academia, I have bad habits and I'm trying to get rid of them. So I use the very bad notation. Sometimes I call with the capital letter, sometimes with the lowercase, sometimes I just forget the index, etc. So I'm trying to solve these problems. I believe I have explained everything, so I should be, you should have all the knowledge to derive all the formulas that you see in the paper of the flash attention. And you should also have an internal image on how the attention calculation is working block by blocks. I know that I could have spent 20 hours explaining things better, but I also have a life and I also have a wife, so I cannot make a 100 hours videos. Also, there were some interruptions making these videos. I removed some wisdom teeth, so it took me at least more than 1 week to recover because it was so painful. So thank you guys for watching my video. I hope you learned a lot also this time. As you can see, Triton is something new. There is not much documentation, so something that I have said about Triton may not be totally correct because really there is very little documentation. So all the Triton that I have learned is by looking at the code written by others and try to understand it. I think that's it, guys. So I wish you a wonderful day and see you next time on my channel.